So Boumediene, thanks a lot, and thank you guys for being here, and thanks for your perseverance in organizing this despite the pandemics and everything. Boumediene, this is truly great, and for the community, I think it's very important that we keep it up with this event, because otherwise it would be difficult. So in any case, for the others. So if you looked at my talk in the recorded one, this has nothing to do, because, well, I tell you, Boumediene, he asked me to prepare a general introduction, colloquium style, and so that's what I tried to do. I apologize in advance, because for the experts there will be either repetition or things that you already know, or things that are too basic. But well, what I made an effort is in well, probably guessing what the others would be talking about, to make a link with other talks. And also, well, I will give the slides to Boumediene so that he makes them available to all of you. So I put tons and tons of references with either theoretical and methodological tools and advances, and also with applications. So so you will see at the end there are like seven or eight slides just with references. So for those who want to get into this field and they want to look at what it is about, is useful. It is obviously, and this is again another apology, is obviously biased by my interest. So that's why there is a significant selection bias here, and I apologize for those who I didn't cite, or well, I don't describe their work. I only have 40 minutes, so. Anyway, so let me get started. So let me start with a definition, or what my definition would be, of reservoir computing, and this is in a nutshell what I will be considering, and some of the bullet points that you see here is what I will be describing in the talk. So our reservoir computing is a learning paradigm, right, which is designed for the learning of dynamic processes. So this is, if you want, my own denomination for, or if you want, a collective denomination for learning dynamical systems, or stochastic processes, or input-output systems. So this is what I will call the dynamic processes. And the important thing, so this is as opposition to all these advances that we see not only in the scientific literature but also in the media, when we compare it with static learning. So all these things that have to do with neural methods for example, image recognition, or these classifiers, SVMs. So these are purely dynamic, something that moves in time, kind of learning paradigm. So we learned these things out of low dimensional observations, and this is very important for those of you who are in dynamics or into mechanics. So we don't observe, if we are doing here supervised learning, so the temporal traces that we have are not full-fledged state space observations of whatever dynamic process we are interested in the sense that, let me give you a couple of examples. If we are thinking of a real dynamical system, deterministic, think of the M-body problem. So we are looking at the planetary system. So the observations that we have is not for the entire dynamical system, all the planets, for example, and the sun. It would be just observations of one of the planets, and out of that we try to reconstruct the dynamical via supervised learning, as I will describe in a second. Or if we are doing stochastic processes, think, for example, of a market, right? So this is a huge dimensional stochastic system, in which, if you want, the different components or the dimension would be given, the real dimension of the system would be given by the market participants. So actually all we observe, for example, is temporal traces of a few indices, or a few prices or returns of given stocks, okay? So this is what I mean by low dimension observations. And what we use as learning paradigm is this part here, is state space systems, which is a very classical and venerable field. But what makes it reservoir computing is that we will impose that the state equation will be randomly generated, and we will impose linearity in the readout. And then when it comes to the learning part, well, this randomly generated part, we don't touch it. It's going to be not trained, not estimated, and it is only this linear readout that will be estimated. And we want linearity because, well, as you will see, typically the dimensions involved in here are huge. So training something which is not linear or separating ourselves from a linear regression is going to be difficult. And then there is a last point that I put in here, and which I will be telling you about briefly, is the availability of high performance hardware realizations. This is something that is historically very important, and is our colleagues in physics and engineering who truly gave this field a push just by thinking of problems that had to do with this dedicated hardware realization for these systems. So, well, before I change the slide, I will not be talking much about the stochastic part of this thing. It will be mostly deterministic, and then I will point at the talks that are coming later in the day or later in the conference that have to do with the other points. So the first point that I will be touching is this learning out of low dimensional observations, because you see, if you just take a random scientist and you ask him that you want to do this, so for example, to learn the planetary system just out of observing just one planet, it's surprising. I always found it surprising that you start with low dimensional observations, and out of that you can say something about something which is potentially of much higher dimension. So in order to convince you that that is reasonable, that is plausible, I give you an example that has to do with Takens theorem, and which in a dynamical systems conference doesn't need much explanation. But in any case, these are the hypotheses. So well, this is admittedly not going to be a planetary system, because the phase space is going to be a compact manifold and not a cotangent bundle like it happens with any mechanical system. And what we will be doing is we take a discrete dynamical system. Actually, it's going to be an invertible dynamical system, is this phi that you see here. And then the time evolution is given by this well, composition of this phi. Okay, and then what we observe is not the motion in phase space, is observations of it. Actually, one-dimensional observations of it, which are given by this observation map phi, omega, sorry. So this is what we have at our disposals in order to come up with, in order to learn dx, okay? So we observe the omegas of x, we want to learn dx, right? The motion in dx. So Takens embedding theorem tells us that that is actually possible, right? So there are these hypotheses that, well, you have to avoid these resonances and so on. But what Takens tells us is that, well, generically meaning for a generic observation in thinking of the C2 topology in the space of these omegas, then well, actually there is this embedding that you see here, and actually it's a very simple delay embedding that gives you well, what Takens tells us is that if your dimension is bigger or equal than this 2n+1 that you see here, well, what this map is actually a C1 embedding. That means, well, it's an injective immersion, and then the topology given by this immersion in the image coincides with the relative topology. So these things, that is the original dynamical system and its image in R2n+1. So notice that this is just a Euclidean space, or it's going to be a submanifold, an immersed submanifold, an embedded submanifold in this Euclidean space. So this map gives you a representation in here of the dynamics. A representation which is, if we are talking about embeddings, admittedly only topologically conjugate, right? So when it comes to even metrics are not potentially respected here, which will pose a problem when it comes to forecasting afterwards. But the important thing about this theorem is that it gives us a hint about learnability, in the sense that, look, if instead of working in the original space, the space of dx, we work on the space of the image by this phi, the dynamics is going to be, the dynamics in that image space is going to be given not by this phi that you see here, but by this capital F, which is given basically by this topological conjugacy by Takens delay embedding. So what is the relation between that and learnability? Is that when you are in that space, actually, in order to know how the dynamics is going to be determined, all we will need to learn is this little f that you see here, because since it is a delay embedding in this image space by Takens embedding, what is happening is that we just have a time shift in the coordinate, and it's only the last coordinate that will be a non-linear, potentially very complicated function of the previous coordinates. So if you want to learn out of observations of the dynamical system, the dynamical system itself, in this admittedly potentially different space, but conjugate up to homeomorphism, all you need to learn is this map, right? So, and that's something that we could do with neural networks, polynomials, or splines. Here we just would have to learn a function, right? So all this discussion is to convince you that what we are trying to do here is reasonable. So I give you observations, low dimensional observations, and actually just by learning a function out of what I have out of these observations, well, I could have a pretty good idea of how the dynamics looks like. So this is extremely classical. I don't need to tell you, and it has given rise to this, well, embeddology literature with very nice applications for forecasting. And but as I said, this is just topological conjugacy. So when it comes to forecasting, it has its limitation. Okay, so so here you see in this picture that I take from this reference that you have in here, well, you have the usual story. So you have Lorentz, you have a time series extracted out of one of the coordinates, and then you reconstruct it. And obviously these people are topologically conjugate, but from the metric point of view, they are not the same. Okay. So another 2 points that I wanted to bring up in the presentation, and which motivate some of the things that I will tell you later about, is first that all these things that I just said are not robust with respect to noise. So there are these very nice papers by David Brumhead and his collaborators back in the late 90s, in which he tried to do things like this for noisy systems, and well, it's not that yeah, it's not as nice as the theorem that I showed to you. And then the other thing is the fact that, well, if you let me go back to the previous slide. Here we said that, well, if you just use this theorem for learning purposes, all you need to learn is this function, right? A function that depends on 2n+1 variables, at least, m being the dimension of the phase space. So the fact that you only have a finite number of arguments in that function, or if you want the finite memory that this function exhibits, has to do with compactness, right? So if you go to non-compact phase spaces, or if you want more, more general mechanical or engineering systems, you are confronted automatically to infinite memory phenomena, and then you need something else. And that's why using state space systems or processes that depend on an infinite path is necessary. And that's why in the presentation you will see that I am using always semi-infinite inputs. I will not be using flows or forward-looking systems that as is traditional in dynamical systems or in mechanics or in control theory. I will be always working with semi-infinite inputs, and also in part because when you go to the stochastic setup that I will not contemplate here, you always work in stationary regimes, and that also imposes the use of this kind of semi-infinite inputs. So if you want, one of the goals of reservoir computing, like any learning goal when it comes to dynamical systems, is to devise learnable paradigms that, if possible, do better than tokens, okay? And if you want, what would be specific to reservoir computing is that they are easily learnable, okay? So this linearity in the readout that's what we will achieve. This is what we will achieve with it, okay? So okay, so I told you, we learn out of low dimensional observations using state space systems. So here you have the state space system, and that's what we will call a reservoir computing or reservoir computer, provided that this capital F that you see here, which is the state equation, is randomly generated or semi-randomly generated, and well, eventually it exhibits some sparsity features, right? So that's what is going to be particularly specific to reservoir computing. And then this H is the only thing that we will train, is this readout, is this observation equation. I will impose linearity on it, and that's what will be trained, okay? The F, I will generate it randomly, and then it's only the H that will be linear and will be trainable. There are some features associated to that, in particular the fact that we can do some statistical inference when it comes to that. Also this multitasking, but I leave it aside because it will come back later when I talk about liquid state machines. So just one word about relations with extremely classical fields. You see, we were talking about tokens, but now I showed to you a state space equation, a state space system. So you see, here you have an entire literature that goes back to Kalman. I see here a few great names that have been working on related problems, because you see, if I tell you that I want to learn a dynamical system as a state space system, that automatically talks to the classical realization problem that you have in control theory. So there are relations there, so that's why I wanted to at least mention them. There is also a relation with filtering theory, because these states that we have in here sometimes are the hidden states of models. So for those of you who are into financial econometrics or finance, so think of stochastic volatility models. These states are actually the volatility, right, that we do not observe and that we want to filter. And then let me mention something which is much more recent, but I think is very promising, and is the relation of all this with the theory of non-autonomous dynamical systems. Is much more recent, and then there are these very nice recent works by Gandhi Manjunath and Petertinho and even Herbert Jäger, who are regularly publishing works in that direction, and that in my opinion, it should be further developed because it's very promising and again, also mathematically very beautiful. So that's what, so if you want, there is this relation. As I said, we cannot truly use out of the box the results that come from this field, in the sense that, as I said before, we are always working in this semi-infinite inputs setup. And you see, most of control theory, for example, is forward-looking. If you do control, well, I give you a system in a given state, and then you need to, what you want to determine is how to choose the control so that you go from point A to point B. Here it is not like that. We are in a different setup, and that's why we need to work with this equistate property, this fading memory property, all this vocabulary that came with well, the semi-infinite input setup, and all these results need to be adapted to that setup. Also, the results that we obtain in the reservoir computing or recurrent neural network setup has nice implications for classical questions in control theory and in systems theory. So, for example, when it comes to the realization problem, some of our universality theorems, actually what they prove is that, well, there are systems that it's known since the time of Kalman that they cannot be state space realized, but actually these universality theorems show that, well, many systems out there, even though you cannot realize them as a state space equations, actually you can approximate them very well by those. So there is this, yeah, as bureaucrats like to say, cross-fertilization between these two fields, and it's something that is very nice to see. So let me give you an example of because you see, I told you what we want to do, right? But can it be done? So in the dynamical systems setup, there are recent advances in that context, and I invite you to listen to Alan Hart's talk right after mine, in which actually they prove something very similar to Teichmann's theorem using, well, if you want, the basic or the most basic reservoir computing paradigm. So what they proved, Alan and his advisors, is that well, actually you can construct an embedding which shares some of the properties of Teichmann's theorem. There are a few points that need to still be proved. For example, the genericity is still not there, but actually it's a very powerful result that shows that randomly generated systems or semi-randomly generated equistate networks, they share, at least when you restrict it to the attractor of this dynamical system that you want to learn, you have this embedding property, and in any case, I invite you to listen to Alan's talk right afterwards, and he will give us the details, I suppose. So right, there is another topic that is also extremely classical in systems theory and in dynamical systems, which is much related to what I just told you. So, so you see, we want to learn a dynamical systems with a state space system, right? So, so actually, you see, if something like that is possible, well, I said that not a dynamical system, out of the observations of a dynamical system. So we are in the same setup as before, right? So it is reasonable to assume that if something like that is going to happen, that is, if the states of a state space representation whose inputs are the observations of a dynamical system, this is what you have in here, then it is reasonable to believe that if that is the case, well, actually the dynamics of the states are going to be regulated, or they're going to be mastered by the dynamical system itself. So when that happens, we say that there exists a generalized synchronization between the dynamical system and the state space system. So, so this is again a very classical theory that goes back to the 90s, basically done by people working in dynamical systems, chaos, and physicists, and if you want words that may be familiar to you, you see when we have that the states are actually being totally determined by the dynamical system that you are observing, and whose observations you are using as inputs, then we are in a master-slave situation. So the master is the states of the dynamical system, and the slave are going to be the states of the state space system that we are considering. So there is a pre-recorded talk by Pietro Verzelli, and I think that he will be talking later on in the day about this. So I listened to his talk. It's very suggestive. Is very interesting. So I encourage you to listen to him too. So and this actually is very much related to also this theorem by Hart, Hook, and Dawes that I mentioned before, in the sense that the way in which this Tackins-like embedding that they come up with is actually a synchronization constructed out of the solutions of the equistate network. So and in order to give you a glimpse of that idea, let me show you the so-called synchronization theorem that was, well, you have it in these two papers by Kokarev in 96, and then there is Hunt and Art in 97. So they have a theorem like this. And well, what they say is that synchronization capital H that I showed to you in the previous slide exists if and only if actually the system flows, the definition of the system flow, you have it here, is basically, the system flow is you take a state space system and then you take a bunch of inputs, right, up to time t, and then, well, you just crank the state equation with those inputs out of a chosen initial condition, right? So what these people say, or they prove, is that a general synchronization exists if actually when you just crank the system flow and you make it go to infinity out of two different initial conditions, actually the initial condition doesn't matter, right? So so for those of you who have done reservoir computing theory before, you immediately recognize that this condition is what we call this state forgetting property. There is this paper by Herbert Jega a long time ago, in which he talks about this state forgetting property. He puts this into relation with this equistate property and the fading memory property. So these are things that I will shortly talk about later in a second. And so actually is having that state forgetting property that guarantees the existence of a generalized synchronization. And as I say in the last bullet point, again, there is much relation, as you will see, because Allan, he will give you the details of this thing he calls the equistate map. The equistate map is just one synchronization, and the conditions that he imposes on this well, on the equistate network that he uses to construct its equistate map, actually what they guarantee is that the equistate property and the fading memory property and in passing this state forgetting property hold, so that this generalized synchronization exists. Okay, so again, I emphasize that these are all extremely classical subjects. They are all, there are very close ties between them, and now they surface in a different light because, well, we have these different learnability goals with randomly generated systems. And for mathematicians, that makes it very interesting because we have things to prove and we have things to show. But I emphasize this link with previous topics that have been very well studied. So in the same vein, let me give you a few historical remarks for those of you who never heard about this. So I'm not going to give you the entire history of reservoir computing, but there are a few points that I wanted to mention. So when it comes to equistate networks, in the sense that we use a state equation like the one that you saw before with a linear readout, with the randomly generated connectivity matrix, that would be this capital A that you see here. And the first time in the literature that that setup appears is in this famous science paper by Herbert, Jagan and Harold, in which they not only introduce this, but they also prove that you can actually do very well when it comes to the forecasting, or if you want the path continuation of chaotic dynamical systems. And well, here they show that you truly can improve tackles, right? Because if you look at the abstract, they say that they improve by a factor of 2,400 in terms of forecasting accuracy with respect to previous techniques. These previous techniques are these nearest neighbors based on embeddology, okay? So they have also this application to equalization, which is for engineers actually is more important than what us mathematicians look at when it comes to dynamical systems. However, the defining equation of equistate networks, actually the earliest I found, or that we found, was in this ETH thesis in 1992, directed by Moshitz. So these are engineers, right? And then, well, there is no randomness here, but they set to prove the universality of these paradigms. Unfortunately, the proof was not right. It was fixed 2-3 years afterwards, but it is them the first who thought of such a recurrent framework for the learning. In their case, it was input-output systems. There are no dynamical systems here. And they identified also the importance of this fading memory property. So, something that had been introduced in, again, an extremely famous paper by Stephen Boyd and Leon Chua, in this contribution that you have in the screen. So these people are the first who mathematically characterized the notion of fading memory as a continuity property with respect to a weighted norm, right? So they place themselves in this full-fledged semi-infinite setup, not finite memory, and then they are the first who realize that fading memory. So I actually am talking about it, but I didn't define it. So fading memory is what the words say, right? So you have systems, input-output systems, such that when it comes to the output, the influence of the input fades out in time when you go towards the past. So when you look at the output, actually what happened much more recently is more important in the output than what happened a long time ago. So this is a very desirable modeling feature. And well, they mathematically characterized it. It shows up in many applications in finance, for example, or in engineering. And well, they are as I said, the first one who characterized it, and they linked it to a compactness property, which is extremely important when you prove universality theorems. So you are in an infinite dimensional setup where compactness is difficult to find, and then they realized that when you are in the fading memory setup, compactness, if you restrict yourself to uniformly bounded inputs, it shows up in there, and that's what has allowed some of us to prove universality theorems afterwards. So, but then the idea comes from much earlier. So there are these books by Wiener and Volterra, and then in the slides you have the actual sentences where they talk about it. So anyway, just look at the slides afterwards. And as usual, you know, science is a collective process, and we all build on what others have done before. So yeah, this Boyd and Chua paper is not an exception, right? there is another thread of literature that has to do with what is called liquid state machines. So these are people who came up basically with the same idea, but based on or motivated by features that are observed in neural systems, right? So they called it liquid state machines. There is this famous paper by Mash, Nachlega, and Markram, where, well, they introduced basically the same idea, calling it differently. And what they were after is something which we are all after, especially in these days, having to do with big data and huge volumes of information. Well, what they wanted is basically the possibility of doing online computations and also paradigms that are not exposed to the so-called catastrophic interference, in the sense that like neuronal systems or behaving systems, you see, think of ourselves when we're in the street, and then we need to adapt to all this well, new information that our senses are giving us. So you see, if our brain was a traditional Turing type machine, like the one that you have in A, well, we don't want to have to retrain our brain each time that we see something new. What we want is to incorporate online that information and to adapt to it. So that's what these people were after in these papers having to do with liquid state machines. And also multitasking. Well, as I said before, well, Markram is one of the top neuroscientists out there. And then, well, they were aware that one of the things that, for example, explains very well the energy efficiency of the brain is the fact that, well, you have these cortical columns, and then, well, I have it in the next slide, and then there is this division of information processing between cortical columns, and then the so-called readout neurons, right? And that makes that the information processing is done in an extremely efficient way. So if we think of the reservoir computing, well, these cortical columns, they would be this state equation, this reservoir system, and then what you do is you, out of the states of this big reservoir system, cortical column, then you have all these readout neurons that are trained or learned to do different tasks with the same amount of information. So I am running out of time because I'm, according to my chronometer, at 37 minutes, so I will have to stop. But I invite you to look at the slides for references having to do with, well, I just flashed at you all these things that have to do with physical implementations. If you happen to be interested in those, I'm telling you, is very beautiful science, very beautiful physics. It has to do with physical implementation of chaotic optical or optoelectronic systems. There is much interest out there in the industry. So I have been working, for example, with IBM in the creation of devices of this type, and they are truly investing a lot of effort in things like this, because well, if we manage to make them work, this would yield truly scalable reservoir systems capable of handling huge volumes of information. So it's a very big technological challenge, but it's worth them. Is truly worth the effort. And then, well, here you have like 5 or 6 slides full of applications, mainly to forecasting and to engineering applications. Some of them are a bit outdated. I have to say that because, you know, I'm an editor in one of these big forecasting journals, so reservoir computing is not still, at least in the usual sense of the word, forecasting literature. So we don't get many submissions having to do with applications to forecasting. But when people truly invest effort in using reservoir computing for forecasting, it truly gives unbelievable results. So there is this talk by Lyudmila Grigoryeva afterwards. I don't know if she will be talking about it or not, but there are these very well-known tasks where reservoir computing is very competitive, but of course it takes more effort than standard parametric models that people are used to and that are pre-programmed in Python, R, or MATLAB, right? So that's why it remains to this day a bit exotic, because probably we didn't invest enough effort to create the right toolboxes to do it, okay? And then, yeah, you will see that in the slides there are these two applications for Mackie Glass, and then I wanted also to talk about all these advances having to do with the learning and the forecasting of chaotic PDEs. There is this wonderful work by people around art. So, but for that you are going to have these two talks. One is by Jadid Patak on Thursday, and then there is Pantelis Vlachos from ETH who will be talking next Monday. So I encourage you to listen to those talks, because you will see their results are truly spectacular. There are also advances that have to do with randomness. There will be this talk by Josef later on, or my recorded talk that had to do with that. There is also bounds, because you see, once we are in machine learning, we have to worry about well, the entire learning program, right? We want to have risk bounds. We need to have universality theorems. We need to have approximation bounds. So these are things that we have worked on. Of course, I don't have the time to tell you about it. You just have here the references that have to do with that. So in any case, I wanted to, I hope that I gave you at least a glimpse of what the field is about. I encourage you to look at the slides for references, and of course you know how to reach me. So if you want to learn more, or you want to have precisions about the things that I didn't have the time to cover, just let me know. Just let me know, and I will be very happy to discuss that with you. So thank you very much.
Yeah, thanks a lot. Can you hear me?
I hear you, yeah.
Oh, yeah, okay,
yeah, I hear you.
Yeah, okay, yeah, thank you very much, yeah. So next is Allan Hart will be talking about, okay, I forgot to start, but thank you.
Do I just share my screen? Okay, so yeah, without further ado, welcome to my presentation on embedding and approximation theorems for echo state networks, by myself and my two PhD supervisors, James Hook and Jonathan Dawes. And this is based on a paper with the same title. So yeah, here's the table of contents. And the first thing we'll do is just jump into the definition of an echo state network. So I realize that in this, well, today, every talk is probably going to start with a definition that looks a bit like this. So I'll try and go through it kind of quickly. So to set up an echo state network, we have A and W in, which are this n by n and n by 1 real matrices, which we're going to call the reservoir matrix and the input matrix, respectively. And we've got this map, var phi, which is continuously differentiable, and it's a smooth component-wise squashing function with biases bi. So you can think of this as something like the hyperbolic tangent function applied component-wise. So we imagine if we have a sequence of observations from some system, UK, then we can create a sequence of vectors RK according to this recursion relation. So we're going to call these RKs reservoir states, and they depend on this. They depend kind of non-linearly on all of the previous data points, UK, UK minus 1, etc. So we have our sequence UK of observations, and this creates our sequence of reservoir states, which are the states sort of internal to the network. So here we have this thing called the echo state property. So here I've lumped the definition of the echo state property as well as a condition for it to hold. And basically says this: if the 2 norm of the reservoir matrix times the derivative of our activation function phi is less than 1, then if we have 2 different reservoir sequences, RK and RK hat, which originate from different initial points but are driven by the same time series UK, then they'll converge to the same sequence. And yeah, this was remarked by Jaeger and independently by Wolfgang Mass right at the sort of beginning of the development of echo state networks. So having computed these new reservoir states, R1, R2, all the way up to RK, what we want to do now is try to find some linear output vector W out such that W out times RK is equal to AK, where AK is some target we're looking to approximate. So essentially we're trying to approximate some target function by writing W out times the reservoir state. And we're going to try to approximate this target function by regressing against a set of like known targets, AK. And we've essentially set up a sort of regularized least squares problem here. So for the rest of the talk, what we're going to do is we're going to restrict ourselves to the special case where the targets we have available are just the next step in the sequence. So we're ultimately trying to learn the target function of next step prediction, which will allow us to forecast the future by essentially predicting the next step, feeding that next prediction back into the echo state network, using that to create the next reservoir state, and then using that next reservoir state to predict the next step, and then just proceeding recursively. So that sort of setup gives us this system of equations here, where we essentially end up with like an autonomous dynamical system. So we run out of training data and we're now just proceeding forward with this autonomous system, which should hopefully generate a prediction of the future trajectory. So here we have a kind of picture to sort of visualize what this might look like to make it look more like a sort of natural neural network. So by way of intuition, you can imagine this thing here is a trajectory of the Lorentz dynamics. We take a sort of, say, a one-dimensional observation of Lorentz dynamics at every time step via this observation function omega, which maybe just returns the x component of the Lorentz dynamics. We pass that into our echo state network. The observations are connected to the reservoir matrix here via these connections Wn, and then all of these connections here are represented by an adjacency matrix, which is the reservoir matrix A, and this is the training phase. And then in the autonomous phase, once we run.
Yeah, we don't hear you.
Run out of training. Run to the. Woo. Hello. Am I audible now?
Yeah, yes, you froze at some point. Yeah.
Okay. Yeah. All right. No problem. Okay. Cool. Well, yeah. I was only talking about this picture, which isn't like super important anyway. Okay. So we'll jump into the next slide, which is about the echo state map. So yeah. So here what we're doing is we're going to restrict ourselves to the case where the observations UK are scalar observations from a dynamical system. So here we go. So we're going to let M be a compact manifold and phi a diffeomorphism on M. And we're going to let omega be this continuously differentiable observation function on the manifold. We're going to assume our data UK is observed from a trajectory of a dynamical system evolving under phi, originating from some point x0. So we'll have this relation here. Then the reservoir state RK, given an initial state R0, is a function defined on the manifold and outputting a point in the n-dimensional real space, which satisfies this relation here. So this may look a bit abstruse, but essentially we can get this by considering how the reservoir states have to be related to each other, given the recursion relation we saw earlier. And what this does is this lets us prove the first sort of interesting result in our paper, which is the echo state mapping theorem. And it basically says this: as long as the 2 norm of the reservoir matrix is less than this thing here, so the min of 1 and 1 over the derivative of our evolution operator, then there is a unique solution f of this equation. So you can see f appears twice, such that for any initial reservoir state in our unit hypercube, the sequence of reservoir states essentially converges in the C1 topology to f as k tends to infinity, and we call f the echo state map. So we've included a reference here to a paper by Kokorev and Parlitz, because this f here is essentially the generalized synchronization of the sort that Kokorev and Parlitz define and discuss in their paper. So, okay, so to give you a sense bit of intuition as to what the echo state map kind of looks like, I have this video, which hopefully won't look too janky for you. So here what we have is we have the Lorentz dynamics on the top left, and we just allow those to evolve. And we assume that we're able to take scalar observations of the Lorentz dynamics. So in particular, we're just going to look at the x components, and we can see the x components evolving on the bottom. We feed the sequence of observations of the x components sequentially into an echo state network, and this creates a sequence of reservoir states. So we have these sequence of reservoir states. To visualize them, what we'll do is we'll project the reservoir states onto the first three principal components. So these are the three directions of greatest variance, which are all orthogonal to each other. And we can visualize the reservoir dynamics on this picture on the top right. So the echo state map F, or this generalized synchronization in the sense of Koparev and Parlitz, is this map that maps the Lorentz dynamics here to the reservoir dynamics here via this observation function, omega. And the echo state mapping theorem essentially states that F exists and it's continuously differentiable, so it's C1. But it looks like we have more than that. So if we look at the Lorentz dynamics and we look at the reservoir dynamics, we might conjecture that these two figures are topologically conjugate. So, you know, they both have dynamics that evolve around these two fixed points. They both look like a figure eight. So if they are indeed topologically conjugate, that suggests that this echo state map F is a topology preserving map from the Lorentz dynamics to the reservoir dynamics, and it's therefore diffeomorphic onto its image. And a map that's diffeomorphic onto its image is one that we call an embedding. So we're motivated to try to prove that this map F is not only C1, but is also a C1 embedding. So I'll jump back into the slides. And so here what we have is a simplified version of the theorem. The real version is quite long, and I sort of go into it in more detail in the long version of my talk. And it basically says this. Greater than zero, but on the other hand, we don't know what this probability is, right? So the probability could be arbitrarily small. And it's a bit disappointing because we found from our own numerical experiments and just looking at the numerical experiments in the literature that if you choose the hyperparameters of the echo state network well enough, then you basically always have an embedding. So we expect actually this should hold with either probability 1 or probability arbitrarily close to 1. So we have a conjecture in our paper which essentially says exactly that, that we have the echo state map is an embedding with probability arbitrarily close to 1. And here, yeah, I've cited the original paper by Takins and the actual formulation of Takins' theorem, which we include in our paper, is one proved more recently by Huke in 2006. Okay, so this next thing we're going to discuss is this universal approximation theorem for echo state networks. So to give you a bit of intuition as to where this is going, I have this picture here. So if you train an echo state network on a sequence of Lorentz observations with the goal of predicting the future, you end up with something like this. So here we have the validation data, which is the true future trajectory of the Lorentz dynamics, compared to the prediction in red of the echo state network trying to predict the future. And we could see early on that the prediction and the validation data followed each other very closely, which suggests that there might be some universal approximation property for echo state networks. Otherwise, how else would it be able to approximate the Lorentz system? And in, you know, other works, just any dynamical system you kind of want seems to be able to approximate it really well. Furthermore, there's another more subtle and interesting thing that goes on here. So after a while, the prediction data and the validation data diverge, which we expect because the Lorentz system is chaotic. So these small errors that necessarily have to occur are just going to accumulate and turn into large errors. But what we could have is a situation where the prediction data, you know, totally leaves the manifold and just flies away to infinity. But we see that this doesn't happen. In fact, the prediction data seems to stay on the manifold and it seems to retain dynamics that are topologically conjugate to the Lorentz dynamics. And this is not guaranteed by a universal approximation theorem, because just because we have an arbitrarily good next step approximation doesn't mean that errors won't accumulate and just fly away. So we have two interesting things here. One is a kind of universal approximation situation, and the second is a sort of topological conjugacy situation. And those two kind of observations are the next two things I'm going to talk about. So I'm mindful of time. I have 3 minutes left, so I'll just move through it really fast. So we have this theorem here, a random universal approximation theorem for echo state networks, and basically says this: if f is this target function we want to approximate, so the next step function, and we want to approximate in the C1 norm. So we want to approximate the function pointwise, and we want to approximate the derivatives as well. Then for randomly generated A and Wn, there exists a sequence of, or there exists a number of linear readout entries in our layer W out, such that the resulting echo state networks approximates f in the C1 norm. And to prove this, we basically just, most of the heavy lifting was actually just using this theorem by Hornick et al., which is a universal approximation theorem. And here I've cited Grigoryeva and Ortega and Gauthier et al., because they both have similar theorems, with JP also mentioned in his talk. So that's the universal approximation bit. And this next bit is going to be the topological conjugacy bit. So in order to ensure this topological conjugacy, we had to introduce this idea of a normally hyperbolic attracting submanifold, or at least bring it in. Obviously, we didn't indent this thing. So you may already know what this is, but to just give you some intuition, what you can do is you can envision a vector field V on the circle S1. And let's imagine we embed the circle along with the vector field insert R2 into the plane via this embedding F. Then it might look like this. So the embedded circle is this black loop with these black little arrows. So you can imagine if we approximate this vector field just on this black loop, then small errors could accumulate and just cause our approximated trajectory to just fly off the manifold and just go away. And then in the long term, essentially this extended vector field admits this black vector field on this black loop as a normally hyperbolic attracting submanifold. Okay, so I've got 1 minute left and I don't want to go over time. So basically, this allows us to create the ESN approximation theorem. So for randomly generated NWN, there is a choice of linear readout weight WL such that the autonomous echo state network has a normally hyperbolic attracting submanifold on which the autonomous dynamics psi are topologically conjugate to phi. So this is really saying that the red trajectory, which is represented by psi, should have the same qualitative behavior as the blue trajectory, which was phi, or phi is, if you like, the original Lorentz dynamics. Okay, so there we go. So it's 11 o'clock. So yeah, I won't go through the future work. Thank you very much for listening.
Yeah, thank you very much. Yeah, I think there were some technical problems with your connections, but people can watch the long lecture online. Yeah. Okay. Yeah, thank you again. Thank you. Yeah.
All right, cheers.
So now we can have this next speaker, Andrea.
Hello, can you hear me?
Yeah, we
Can
hear
you hear
you.
me?
We hear you. We hear you perfectly.
Yeah, cool. So share my screen. Can you see my screen?
Yes, perfect.
Cool. All right, so good morning, everyone. I'm Andrea, a PhD student from the University of Exeter. And in this 15-20 minutes, I'm going to talk about recurrent neural networks, non-autonomous dynamical systems, the echo-state property, and of course, multi-stability. I'll try to stay in my time slot. I will mainly talk about this paper here we published in Physically. So I'll jump directly to the second part of this talk. But if you are interested, you can check out the whole presentation, which is uploaded on YouTube. So I'd like to start talking about the eco-state property from a non-autonomous dynamical systems perspective. The eco-state property is a property that a reservoir computer must possess in order to function correctly. Here you can see a snapshot of the original definition devised by Jaeger, and it states that a recurrent neural network has the eco-state property if the internal state x at time n is uniquely determined by any left infinite input sequence. All right, so in non-autonomous dynamical systems, there are many different choices for the notion of a tractor. And this definition here in particular is a request on the structure of the so-called pullback attractor of the system, of the recurrent neural network viewed as a non-autonomous dynamical system. So here you can see this black trajectory, which is of course a discrete time trajectory. This black trajectory represents the pullback attractor of the system, the unique entire solution of the system, because this request on the pullback, on the structure of the pullback attractor is that the pullback attractor must be a unique solution of the system, or more precisely a unique entire solution, which means that it is also a solution well defined backward in time, roughly speaking. The eco-state property implies that given a specific input sequence, the recurrent neural network will produce a unique response, and it will forget any internal states and end up following a unique, although possibly complex attracting trajectory. So as you can see here, if we start at the same time to different initial conditions, the blue square or the red square, they will eventually converge to the black trajectory, getting closer and closer to each other. So we have this input-driven system, summarizing, that we can describe with this map G. The internal state of the system is thus a function of the current input vector U and the previous internal state at time k. And the presence of the input effectively changes the equations ruling the dynamics at each time step, and that makes a non-autonomous dynamical system, this one. So the eco-state property can be visualized as in this scheme here. We've got an input sequence U, and the system responds with this unique attractive trajectory for all initial conditions. Now it's clear that the eco-state property says something about the reliability of this system. We want the same behavior regardless of the particular initial condition, right? But it also seems quite too much restrictive to my eyes. And that's why we asked ourselves, why not many reliable responses? Is it really that essential, the eco-state property? And so we ended up with this idea to define an echo index of the system driven by a specific input sequence U. And this number quantifies the non-autonomous multistability, the degree of non-autonomous multistability under the action of the driving input. So we are basically considering those input-driven systems capable to produce for a given input sequence many let's say, attracting trajectories. And which one to converge to will depend on the initial condition, which is given by the specific location in phase space, but also the initial time, because as I mentioned before, the equations is changing at each time step. So also the initial time is important. So here I want to show you an example to make clear this point of many attracting trajectories. This is a task we found in the this paper here of Herzer, Legenstein, and Maas, which I'm going to briefly explain. There are two, the task is the following. There are two input sequences, the green one and the red one. And the neural network must learn to reproduce in output the green signal or the red signal according to the context given by an internal memory that the network must develop, which is represented by this value, which can be +1 or -1. Whenever the value here is +1, the network must reproduce the green signal. As you can see, the black trajectory here is the actual output of the network, which is following the green input signal. And as soon as it switches to -1, then the network switches to reproduce the red signal. And analogously, when it switches to +1, again, it starts to reproduce the green signal. So this internal memory is driven by some additional input pulses. And we decided to turn off these pulses, these input pulses, and run a bunch of initial conditions. And that's what we observed. As you can see, there are some initial conditions converging to the value of +1 and correspondingly converging to the non-autonomous attractor related to the green input signal, and other initial conditions converging to the non-autonomous attractor related to the red input signal. And that's how those non-autonomous attractors look in phase space in the first two principal components. As you can see, they look quite scrambled, but despite the aspect that they are extremely stable, since we run many initial conditions and all of them converged either to one of those two non-autonomous attractors. So we devised a formal mathematical definition suitable for modeling those kinds of non-autonomous attractors. And we ended up with this definition of what we call the uniformly attracting entire solution, which I'm not going to show you, by the way, the proper definition, because I think I will running out of time. But you can check for the all the details in this paper. So roughly, I'm just explaining roughly the idea. We consider those entire solutions, so those trajectories, also well-defined backward in time, which uniformly attract in space and time portions of phase space with positive Lebesgue measure. So informally, we can see uniformly attracting entire solutions as good non-autonomous fixed points. Always in this paper, we proved a kind of input-driven fixed point theorem for detecting those uniformly attracting entire solutions, which I'm going to briefly explain, which are the basic ingredients. So suppose you have a subset of phase space Q, which is compact, convex, as in this picture, and positively invariant for this universe of input sequences. Positively invariant means, roughly speaking, that if we get inside this red region, we get trapped inside and we won't escape as time flows ahead. So, so if this red subset of phase space is compact, convex, positively invariant, and it also holds this particular relation here, the supremum of the norm of the first derivative in space of the map G, which is the map describing the input-driven system, if this supremum is less or equal than mu, which is a constant less than 1, then it is possible to prove that for all input sequences in this universe of input sequences, the input-driven system admits a unique entire solution inside this red region. And this entire solution will be a uniformly attracting entire solution, which are represented here by this messy black trajectory. All right, so regarding the definition of the echo index, again, check the paper for the proper definition. I just want to say here that we say that a system driven by an input sequence U has echo index n if there exists a number n of uniformly attracting entire solutions, such that they attract the whole phase space except for a zero Lebesgue measure set. So let's focus on this picture here. On the vertical axis, we have our phase space x, and on the horizontal axis time. Black trajectories are supposed to be the uniformly attracting entire solutions. Blue arrows represent the vector field of the dynamics, suggesting a convergence towards these two black trajectories. And there is also a red solution, entire solution here, which is somehow unstable. And this is an invariant set. So if we start exactly on this set, we won't converge towards none of those black trajectories. So we want to get rid of this set, which has a zero Lebesgue measure. And excluding this particular set, which is actually the boundary between the basin of attractions of these two trajectories, then we get that for all initial conditions, we get a reliable behavior, since we can converge towards one or the upper uniformly attracting entire solutions or the bottom one. So in the particular case of the picture here, we can say that the system has echo index 2. Now I want to show you one application of the input-driven fixed point theorem that I mentioned before. Suppose to have a map, an autonomous map F with a fixed point x star, such that it satisfies this relation here, which is basically there is a neighborhood of radius delta of the fixed point, which is contracted with a ratio of m, where m is a constant less than 1, of course. Right, so we have our input-driven system here defined by the map G. G is a continuously differentiable map. And suppose there is an input value u bar such that the corresponding autonomous map obtained forcing using the constant input value u bar. So we get this autonomous map. If this autonomous map possesses a stable point with this property, then it is possible to prove that for any input sequence having small enough amplitude, let's say, then there exists a unique uniformly attracting entire solution confined in a neighborhood of this fixed point x star. So that gives us a way to see how a uniformly attracting entire solution can emerge. It can emerge, for example, perturbing with some noise or small amplitude input perturbations, a stable point with this property that we call a uniformly attracting stable point. So this result implies that slightly perturbing an autonomous system possessing a number n of those stable points will lead to a non-autonomous system with echo index n. And also it implies that the echo strip property cannot hold in general for small amplitude input signals unless we put some restrictions on the recurring connection on the reservoir. Okay, as last result, we have here this input-driven system, as always, defined by the map G. And this time, this map G has this form, which is a fairly general form of a recurrent neural network map, right? We have a matrix of the recurrent connections. Here, we've got the input matrix. This function C is basically the readout of the reservoir. And we also consider the possibility to feed back the output into the network by means of this matrix WFP. This is the leak rate, and of course, this is the activation function. So under the hypothesis that the readout and the activation functions are both continuously differentiable, and as always, the activation function is a bounded, monotonically increasing function with first derivative with a unique maximum point in 0. Think about the hyperbolic tangent, which is a great representative of this class of activation functions. Under this hypothesis, we were able to prove this theorem, which can be paraphrased as large amplitude input sequences induce recurrent neural networks with echo index 1. So with just one reliable attracting trajectory. So now I think I'm finishing my time. So there are some consequences of this theorem about the topology to select on the space of input sequences. And it turns out that the uniform topology seems to be a more suitable choice for the stability analysis of many reliable responses. For the details, check the paper. And here I pinned out some of the research directions, but I think I will stop here. Thank you all for your attention.
All right, yeah, thank you very much. So now it's Josef Teichmann, and then we'll take questions after Josef's talks. Thank you.
Hello, everybody from my office at ETH Zurich. Thanks a lot for inviting me for this fascinating session on reservoir computing and dynamical systems in machine learning. My friend Juan-Pablo asked me to give a talk here, which makes a connection between, on the one hand, reservoir computing, as most likely everybody in the audience knows it very well, and an area of analysis and of stochastic analysis, which is often coined as rough analysis, and in which center an object lies, which is called signature. I want to, on the one hand, make this connection, and on the other hand, show recent results which have been obtained by Lyudmila, Lucas, Krista Cucchiero, and Juan-Pablo and myself, which are able to show that the paradigm of reservoir computing actually, from this perspective, force in the realm of provable machine learning, that one can get a very clear perspective why this representation of generic dynamical systems by random dynamical systems has actually a good chance to work. Questions as usual at the end of the session, and I'm happy to answer them. So let me start. Yeah, the mouse works. So first I do something which is just to set the stage. Everybody knows here in the audience what reservoir computing is about. And I will take relatively quickly a continuous time point of view. So in contrast to many works in reservoir computing, I take continuous time models. I call them models for this discrete time series analysis area in order to prove certain results and to apply a certain geometric and also algebraic technology to prove those results. And then when I have these results, which is actually the construction of the signature process, I will apply random projection techniques, which are well known from the theory of compressed sensing, to construct what you would probably agree is a true reservoir and to prove some generalization results for them. And this highlights in particular on the role of randomness in learning procedures and provides also some explanations via signature techniques, random projection techniques, why and which type of randomness one has to apply in order to obtain expressive or sufficiently expressive dynamical systems which have a random character. As I mentioned already before, this is work with Krista, Lucas, Lyudmila, Juan-Pablo, and also important to mention Martin Larsson, because another aspect of random dynamical systems has been analyzed with him and Krista together in a work which I will soon mention. So let me right away jump to the continuous time perspective. I do not consider here time series or discrete dynamical systems. I consider non-autonomous continuous time dynamical systems driven by, you see here a couple of objects. E is a state space, so you can think of Rn or a compact manifold as we had it in the great talk of Allan. Y is and Yt is the solution of this non-autonomous dynamical system. And I always write it in this stochastic way. So I only write the differentials, but for people who feel uncomfortable with differentials, just take the division by dt, and then you have the derivative of y equals to a weighted sum of directions. These are the VI's, these are vector fields on my state space. And the weights are the derivatives of the UI's at the point t. And you can think of this as a controlled ordinary differential equation, which gives this abbreviation code, which of course is also reminiscent of coding, which will appear at the end of the talk. So controlled ordinary differential equations come with a state space, a finite number of vector fields, and a finite dimensional control U taking values, let's say in a space Rd. And for simplicity, we take here the control to be smooth. Smooth means at least C1, such that we can easily talk with classical with tools of classical analysis of the solutions of this non-autonomous dynamical system. The vector fields are considered C infinity, so at least locally Lipschitz, such that you have solutions. But think of globally Lipschitz vector fields such that we have also global solutions of the system. And these are controlled ordinary differential equations, and you can consider two input slots. One slot is the initial value, little y, and the other slot is the control U. If you fix the control for a moment and consider the the output, so this is the solution at time t, depending on the input little y, then you get something which could be a model of a feed-forward neural network by just imagining that the VIs are of a neural network type, let's say shallow neural networks, and you discretize the U, or you take a finite variation path with finitely many jumps. This gives you actually a continuous depth model for a feed-forward network. This point of view has been analyzed by Krista and Martin and myself, and this is actually very fruitful because we could also show that on a space of arbitrary dimension, E, arbitrary finite dimension, with random vector fields VI, let's say of a neural network type, so random matrices inside with a generic type of randomness, one can always find controls U such that one can interpolate n points. So from a point of view of training, you can always, with randomly initialized and only trained in a very vague sense neural networks, feed-forward networks, you can achieve interpolation tasks. This is of course well known from the classical universal interpolation theorem, but it is interesting to see where the randomness appears here in order to prove in this controlled ordinary differential equation setting the result. And it gives also an explanation why randomness creates expressivity beyond the classical explanations. But this is not the point of view of what I want to talk about today. Today's point of view is you actually fix y, the initial point, and you consider the solution depending on the control. Yeah. So we have a map from a control to a solution map, y, from little u to capital Y, and we are actually interested in this map. Yeah. And in order to take a little bit language, a general language of dynamical system, it's a non-autonomous dynamical system, so we don't call it a flow, we call it an evolution. You start at time little s, you go up to time t, you feed in the control u, you fix the y, maybe you have a readout w, and this gives you a map from u to this space where the readout ends. And you might ask, how can you be able to learn such maps in an efficient way? Of course, such maps are continuous time models or metaphors of random recurrent neural networks, or of LSTMs if you want, depending just on the way how you write your vector fields. So the question is, how can you represent in an efficient way a given recurrent neural network, a given non-autonomous dynamics by other dynamics? What can you do in order to do that, and what is an efficient way to do this representation? And of course, as everybody knows, the paradigm of reservoir computing, as it has been already presented in the three previous talks, tells such an input-output map. So mapping little u on capital Y, this curve little u on the curve capital Y, such an input-output map can be learned by a non-trainable reservoir, which often has random features. So it's a random dynamical system, and the readout, W, let's also call it W, which is actually to be trained in order to represent this, this map. So the statement here is, and I remember still when Juan-Pablo told me this statement a couple of years ago, that you have a given well-defined dynamical system, maybe a linear map of this dynamical system. You can represent at least approximately this dynamical system by another dynamical system, and the linear map on the output of this other dynamical system. And this other dynamical system, the reservoir, has random features. So you represent something deterministic given the planetary motion or whatever dynamical system you're thinking about by an object which has random features, and by the very construction has nothing to do with the deterministic given dynamical system. How is that possible, and why is that actually a very, very reasonable point of view? So this is a question we have been investigating since a couple of years, and our starting point was at related to a theory which I have to say, in love with since many years. This is the theory of rough path. Nowadays, very often summed up with rough analysis. And this gives actually a very beautiful way, known since many years, of analyzing dynamical system on generic state spaces. And let me introduce you very quickly, not to the theory of rough paths, but let's say to the foundational statement, which is of course also well known in any textbook of a dynamical system. This is this following non-commutative, I call it, Taylor expansion. So consider a control differential equation, some vector fields, and the control, as I said before, is something smooth. So C1 curve, of course, it could also be a Stratonovich-Brownian motion or a finite variation continuous map, or even a rough path. This does not matter. The only thing which matters for the following analysis is that we have actually a first order calculus, so that the standard rules of calculus apply. You know, if it were an Ito-Brownian motion, the standard rules would not apply. You have a second order term, but this is these are details. So we want to understand the map from the input control to the solution Y. Yeah, this is obviously a nonlinear map and a complicated one. And in stochastic analysis, one of the proofs I show relatively early to my students in stochastic analysis is that this map on Wiener space is nothing better than measurable. It does not have continuity properties. Can you still hear me, or am I frozen?
Yeah, you froze a bit, yes.
Is it okay? Okay,
yes.
good. So I continue. So this is a non-linear map. Yeah. Okay. Complicated nonlinear map, which in case of stochastic analysis is at best measurable. Why is it? Yeah. So let me introduce some language here. Let me introduce some language here, which I will use for the following statement. The language is smooth vector fields. Can also be considered as first order transport operators or differential operators by just saying, if I apply a smooth vector field on a test function, take the directional derivative of the test function in the direction of the vector field at the point, and this gives a transport operator, the typical identification which you make when you're talking about the method of characteristics. Okay. And then the following theorem can be actually proved. Let me just the following theorem can be proved. So if you take the solution and you consider a test function applied on the solution of this evolution system, you can write this test function applied on the solution system in the following. I'm sorry, I have the impression that everything is lagging. On the one hand, you have these iterated integrals here, which are just depending on the control and not on the particular dynamics of the evolution system. And this here depends solely on the characteristics of the dynamic, not dependent on the control at all. So you see here this splits the option on the evolution into two parts. One pole and the other part is depending only on the particular characteristics. There's even a remainder term. This is an analysis which of course goes back to change by Belarus and then finally libertarian alliance in the theory of rough paths. And or together, this gives us actually an abstract version of the writer to you. And let me use here technology which I have. Yeah. So let me stop my video here, which might make it a little bit easier. So can you see that?
We do, and we don't have lags anymore, so it might be that that it's your computational power. So maybe it's your power. And I'm hearing me double, so maybe I mute myself again.
Okay. So I try to continue, and just give me a sign if you don't hear me. And I think I will switch off my video afterwards. Might be easier. So we have this map from U, let's say, to the evolution STU. So this was the Y, this process. And what this Taylor expansion tells, you can take here the collection of all iterated integrals. This is called the signature of the control. And you can write a linear map on the signature such that you can represent this dynamical system perfectly, at least asymptotically to be precise. And for certain real analytic vector fields, you can actually prove that this representation is really a representation. So this is very reminiscent of reservoir computing with two caveats. One is this guy here is potentially infinite dimensional. Reservoir computing usually comes also with a numerical efficiency, and therefore also a low dimensionality of the reservoir is very desirable. But what is clearly reminiscent of reservoir computing is that we have a linear map here, a linear readout map. Yeah. So one is able to write the solution of any given dynamical system as a linear map of an object which does not depend at all on the dynamical system, but only on the input. Yeah. Let me switch that off. Then let me return to the, okay. me return to the what is now the Zoom session. Can you hear me?
Yes, we do, yes. Yes, we do, yes.
Okay, I somehow have difficulties to return to the session. Where's the somehow 1 second, let me look how to do that. Where's the Zoom session? I somehow here it is. Somehow my session disappeared completely. Can you just stop my session and then I start it again? Is that possible?
Yes, okay.
Yeah, now it is.
Yes, okay.
Yeah, I think now I have it back. Thank you so much. What does it do? I'm sorry, is it now back?
Yeah, it's working. You can go ahead and we can just...
Yeah, I don't know. I think something was broken with my camera, so I just continue the talk. So you have this dynamical system, which is represented in this way through, on the one hand, this signature process, and on the other hand, this linear map. The linear map depends only on the characteristics of the dynamical system, and the signature process depends only on the control. So in that sense, the signature process is an abstract reservoir, which has nothing to do with the dynamical system. And the W, this linear map, is something which is written on the signature process, and this object depends on the characteristic dynamical system. Now, the signature process is the collection of all iterated integrals. There's actually a very beautiful way to understand the signature process as an object which lives in a famous algebraic object. So this is the algebra of non-commutative power series in D indeterminates. And this algebra has a couple of beautiful algebraic properties, making it into a Hopf algebra, which is particularly beautiful because I'm also working in the building here where Heinz Hopf, who was a former member of the math department here, where he was thinking about Hopf algebras. So the signature process lives in the process of in the algebra of non-commutative power series. You can write a non-commutative power series where you take just the product of generated the E1 up to generate the EK, and you multiply it with the iterated integral with the system. And this processes, or this object is not only collecting all iterated integrals, it's also a dynamical system by itself. We are representing a generic dynamical system by an abstract dynamical system and a regression on it. To reservoir computing is that actually this abstract dynamical system, as I said before, is infinite dimensional one and is therefore, from a point of view of numerical tractability, actually relatively badly behaved, or at least one needs very sophisticated techniques in order to evaluate it. And this was a starting point for an analysis, let me come to these references later, which we started to think about a couple of months ago. We were thinking, is it possible to compress the information which can be found in signature into a lower dimensional object, and having the additional property that the lower dimensional object can be calculated without accessing the high dimensional object. In other words, can we calculate the information which is available in signature by just taking information of a projected dynamical system? And one idea which we applied, it's not the only idea how you can think about the theorem, is this Johnson-Lindenstrauss lemma, famous lemma from the 80s, from the geometry of Banach spaces, a statement about how scalar product spaces behave. Scalar product spaces have a funny property. The property is the following: if you take an n-point cloud in a scalar product space, you can find a linear map from the scalar product space H, which, restricted on the n-point cloud, almost preserves its geometry. This means the projection of the Q into this lower dimensional space has the property that the distances of the image points of points in Q actually are almost the same as the distances of the pre-images, and this is measured by epsilon. And the statement is very precisely, for every epsilon you can find a lower dimensional space such that there is an almost isometry from the set Q to its image in the lower dimensional space. Of course, this is not a surprising statement if you say nothing about the dimension. The funny thing is the dimension can be chosen logarithmically in the number of points. And let me rephrase that in another way. You can find in a k-dimensional space e to the power k, exponential of k, many almost orthogonal points. If you rephrase it like that, you see that this is not how we imagine usually k-dimensional spaces, that you find in a k-dimensional space e to the power k almost orthogonal vectors. So this is the Johnson-Lindenstrauss theorem, and of course this result had a lot of consequences, in particular since this map F can be constructed with high probability by choosing an appropriately scaled random matrix. And this is precisely what we did. We take our signature system, which lives in an infinite dimensional space. We map it via such a Johnson-Lindenstrauss map to a low dimensional space. And then we are asking whether this low dimensionally projected dynamical system has similar property than the original system. And this is where actually the Johnson-Lindenstrauss map helps us. The projection gives us a vector field on the low dimensional space. You can think of signature defining a certain very high dimension such that the logarithm of this dimension is moderate, and we actually are able to prove that this low dimensional dynamical system, even though it is in some respect relatively far away from the signature system, from the point of view of linear maps on this low dimensional system, behaves relatively similar as a signature. And this is a statement which we can prove, and I think it's maybe not today, but it might be tomorrow, that a first version of this statement actually can be found in Archive, a proof of that. And the second fascinating thing is, since F is a Johnson-Lindenstrauss map, F star is then just a composition of such Johnson-Lindenstrauss maps, and they are chosen as random maps, one can, for high-dimensional pre-image spaces, actually write down laws for these random matrices, or at least asymptotic laws, and actually they appear to be random matrices which are asymptotically normally distributed with independent entries. Of course, this is an asymptotic result, but still it's a result which we are able to prove by application of a martingale central limit theorem. And this gives then the following statement. If you have an evolution, a differential equation of such a type with a certain control, which you know, vector fields which you do not know, you can take a system of such a type. This should remind you now of a randomly chosen recurrent system, a reservoir. And this system, if the matrices A and the shifts beta are chosen appropriately, are tuned appropriately, and sigma is just the activation function here, such a system is a reservoir, and there is a degree of accuracy by which you can learn the solution of the previous system as a linear readout of this system if the dimension is high enough and the tuning of the matrices and the shifts has been done in an appropriate way. And time does not permit me at this point to show either an alternative proof of this statement. This is only one proof by the Johnson-Lindenstrauss approach. Another proof just goes via representation theory and goes in a different direction. I just want to show you at the end, maybe not to show, but just to invoke a promised application from mathematical finance. imagine, for instance, the following situation. S&P 500, so a very high dimensional time series, which we observe one trajectory from. And if you take standard theory of financial markets, you can at least, under some relatively mild assumptions, continuity, and that actually you observe the discounted prices, you get, under relatively mild assumptions, the statement that the evolution of this of S&P 500 should follow Ito diffusion. So there is a Markovianity assumption, there's a continuity assumption, there is a no arbitrage assumption, but under all those assumptions, you end up with an Ito diffusion here. And in particular, the Ito diffusion is of such a type that there exists an equivalent local martingale measure. This means essentially that the V, the drift, lies in the span of the VIs, the volatility vector fields here. And now you can think of the BIs as the control U. This is the unknown dynamics. And you would like to learn the VIs. This is the dynamics of S&P 500. And the procedure is then very clear. So what you do is extract from one trajectory which you observe the market Brownian motion. You can, of course, not observe the Brownian motion without drift, but you can at least observe, after inhaled V into this part here, a Brownian motion with drift, which is this MI here. And this exists, of course, under the absence of arbitrage. And then you can learn that from a trajectory. So you learn the U path by path. You learn the MI path by path from the Y. And then you just have the map from the MIs to the Y, where you take via a randomized signature approach, construct a reservoir. In this reservoir, you make a linear regression on the observed path Y. And this actually gives you then a model for S&P 500, so for a very high dimensional time series, which, and this is what we are just doing in my working group, has a very high predictive power if you try to analyze it or compare it with other econometric models. Let me just mention, since my talk ends now, my time is over, upcoming work. So this is work with Krista, Lucas, Lyudmila, Juan-Pablo, and myself on the representation of dynamics by randomized signatures. And just consult the archive where you find this. And very important, I mentioned also the School of Terry Lyons in Oxford, where with non-randomized signature method, which by the point of view which I tried to show you is related to reservoir computing, many interesting applications of this approach of reservoir computing to control problems, to representation problems, to classification problems. And this is just one work where this is outlined. So I stop here my talk. I'm very sorry for the inconvenience due to the technical problems, but otherwise I'm grateful to the organizers and I thank you for the attention.
My name is Nozomi Akashi. I'm a PhD student at the University of Tokyo. Today I would like to talk about my research on the physical reservoir computing. In this study, we collaborated with Kyoto University, National Institute of Advanced Industrial Science and Technology, and Bridgestone Corporation. I'm going to begin by describing spintronics device, which is based on nonlinear magnetic dynamics. It is expected as a neuromorphic computing device because of high-speed dynamics and small size and high energy efficiency. In recent years, spintronics device has been used in reservoir computing. For example, in 2017, a study published in Nature used a spintronics reservoir to solve voice recognition tasks. Here, I am going to explain physical reservoir computing. Physical reservoir computing is an architecture that exploits the dynamics of physical systems in computation. It is based on a recurrent neural network approach. The right figure shows comparison between conventional reservoir computing and physical reservoir computing. In the reservoir computing, weights in reservoir layer are usually fixed. If we consider internal layer as a high-dimensional dynamical system, it is possible to replace internal neural net artificial network to a physical dynamics. Various dynamics of physical devices, such as a soft and compliant robot, fluid wave, spintronics, photonics, and quantums can be exploited. The outstanding advantage of physical reservoir computing is that physical reservoir computing can use the device's material properties. For example, spintronics reservoir can implement extremely fast computation, and it can be used in radioactive environment. There are two issues in spintronics reservoir. First, input signals for the reservoir computing affects the dynamics of the device. To use the device as a reservoir, we must inject the input signals into the device. Device used as a reservoir should have rich dynamics, and these input-driven dynamics usually show complex nonlinear phenomena, such as input synchronization and input-induced bifurcation. Of course, the device's information processing capability is also affected by these phenomena. Recent studies have shown that spintronics devices also show input synchronization and input-induced chaos by a periodic input. Second, physical device cannot easily adjust internal physical parameters after fixing the device configuration, which contrast neural networks. In short, in PLC, it is better to have diverse dynamics repertories generated by input configurations. In this study, we tackled these problems. The method of this study is totally numerical simulation, but the device parameters are obtained from experimental studies. We analyze input-driven dynamics and the information processing capability of spintronics reservoir, where random input were injected. Upon computation, we solved the virtual and real benchmark tasks using the spintronics reservoir. As a result, we discovered two types of input-driven bifurcation, and the information processing capability is modulated accordingly. This result suggests that only by tuning input parameters, the performance can improve. The spintronics devices are various types such as oscillator, switching, and vortex. In this study, we choose the spintronic oscillator. Free layer magnetism M is depending on an ordinary differential equation called LLG equation. Here we inject input signals into STO to use reservoir computing. Input signal is current J in that is included from -1 to 1. Furthermore, we take variables as reservoir states from STO. Here we choose magnetism M, which is dynamical variables of LLG equation. And the dimension of M is 3. We explain our reservoir setup in more detail. First, input signals are shown in the top figure. Input signal consists of piecewise constants with magnitude A and interval tau. Next, states are taken at the time of next injection. In middle figure, States are taken after tau time in order to wait to sufficient propagate input into the system. Oh, sorry. Finally, output is same as conventional reservoir computing. So output signal S is linear transformed from states. Here we calculate random input dynamics at 3 magnitude, 0, 5, 500 milliampere, shown in blue, red, green, respectively. The center figures show free layer magnetization oscillating in semisphere. 0 milliampere shown in blue represent no input, and the dynamics show periodic. For 5 milliampere shown in red, the dynamics is almost periodic, but they fluctuated. They may exhibit chaos. For 500 milliampere shown in green, the dynamics went toward 2 fixed points. It seems to be exhibit order dynamics. We found that the system's dynamics completely changed based on input conditions. We created a bifurcation diagram to analyze the behavior of dynamics in more detail. In the center figure, we plotted local minima of Z coordinates. We separated the input magnitude into 3 regions. Blue, green are periodic, while red is chaotic. Therefore, there are 2 bifurcations for input magnitude, from order to chaos, from chaos to order bifurcation. We calculate Lyapunov exponent to confirm bifurcation quantitatively. A positive Lyapunov exponent indicates initial state sensitivity as a chaos. The diagram on the left shows the results. The x-axis represents the input interval, which is the length of piecewise constant. And the y-axis represents the input magnitude. Red region represents positive Lyapunov exponent and chaos. 2 blue regions represent negative Lyapunov exponent and order. Chaotic regions and 2 bifurcation exist for all input intervals. Next, we want to relate information processing capability with bifurcations. Here we investigate an echo state property. The echo state property is whether dynamical system is derived by input sequence or not. In information processing, it guarantees the reproducibility in computing. Echo state property was proposed in a study of reservoir computing. The almost equivalent concept in dynamical system is generalized synchronization, and the echo state property can be checked by common signal synchronization. If following synchronization index value is 0, the system has an echo state property. Right figures show color map of synchronization index. Yellow region have echo state property. They coincide with the region of negative Lyapunov exponents. Next, I'm going to explain memory capacity. It is defined as an ability to reconstruct past input signals using the current reservoir states. The reconstruction ability of each past signals, called memory function, can be calculated by normalized squared correlation between reservoir states and the past input signals. Memory capacity can be calculated sum of memory functions through delay D. The memory function is included 0 to 1. If a memory function is 0, the past signal can be never reconstructed. If a memory function is 1, the past signal can be completely reconstructed. The center figures show color map of memory capacity. And the right figures show memory function at input interval 80 and 160 picoseconds. For example, red bar indicated 0 delay components, while light blue bars indicate from 4 to 20 delay components. We found that MC is dependent on bifurcations. In the right top figure, MC peaks on each of bifurcation points. Moreover, memory function changed completely before and after bifurcation. Before chaos region, with an input magnitude about 1 milliampere, gray bar as extremely long delay components are dominant. However, in after chaos region, with input magnitude of 100 milliampere, red bars as short delay component are dominant. Next, MC is related in the original oscillation period T. Original oscillation means that inputless STO's limit cycle period. The input interval was equal to NT as the right bottom figure, shown by the lack of peaks on each of bifurcations. Therefore, memory capacity is affected drastically by input-driven bifurcations. Finally, we solve virtual and real benchmark tasks using our spintronics reservoir. Norma2 is a virtual task defined by a following difference equation and typically tests for recurrent neural networks, nonlinearity, and memory. The PAM length estimation can be found in bottom movie. PAM is pneumatic artificial muscle used in soft robotics. Length estimation of PAM is a real task in edge computing. Length dynamics has nonlinearity and hysteresis, so it is hard to predict. But in our previous research, we found that the conventional echo-state network can predict it in high accuracy. We solve tasks by spintronics reservoir. To improve performance, we conduct 5 special multiplexing spintronics reservoirs. It uses output from difference device driven by common signals. The results are shown in the left figures. The top section shows the input signals. The middle section shows Norma2's target signals and predicted signals. The black line represented target signals. The blue line represented predicted signals for Norma2 best performance. And the red lines represented predicted signals for PAM length estimations best performance. Also, bottom section are PAM's target and predicted signals. Different input configurations were used to solve each task effectively. In conclusion, we confirmed the presence of 2 types of input-driven bifurcation in STO. We analyzed the relationship between dynamics and memory capacity. Accordingly, we also demonstrated that task performance can be improved when only adjusting input conditions. Thank you for listening.
Yeah, thank you very much. Yeah, so we'll take questions later on. So now it's Lyudmila. Yeah.
Okay.
Let me share the screen.
Thank you.
Do you see my screen?
Yes, we do. Yes.
Yeah.
Yes. Yes.
Everything is fine. Okay.
Yes.
So hello everybody. Good afternoon, and as everybody, I would like to thank Boumediene, obviously, for keeping up on this idea of this event. It's not easy these days, obviously, so it's great that you just didn't decide to postpone or just to stop the event, and nevertheless made such an effort to put it all together. And obviously, it would be great to be at the Fields Institute. It's been a while, and let's hope that for the next edition of this conference, we will have a chance to meet again everybody already physically, right? So thanks a lot for coming to this session, and I will be talking about memory and forecasting capacities of nonlinear recurrent networks. And as you will see, since I'm talking in the session which is devoted to reservoir computing systems, we will see that these results that I will be presenting to you will be valid also for particular reservoir computing systems. But what is important for us that they also hold for much more general class, just simply nonlinear recurrent networks. So this work is, so this talk is based on the paper that has been accepted like 2 weeks ago, and this with the same title by Lucas Gounod, Juan-Pablo, and myself. So you can go just on any of our pages and just download it and to look in detail. We also have it in archive, so you're free to look into the details of the proofs. So what I will be trying to do here in this talk is to convey some major results that we managed to show, and also to try to put that in context with other things that you already have heard during the previous talks, and also which are linked to other results in machine learning literature, which is booming these days. So what I will be talking mainly about will be the history of the capacity equation, mainly for those people who have heard never anything about that. I will tell you something that already you have seen in previous talks, what kind of systems we're working with. Here will be a little bit of repetition. Nevertheless, I will try to be brief on that and to point out some main things over there. Then I will stop a little bit more in detail on assumptions which we use for the input processes which we fed in those state space systems, or if you want reservoir computing systems, to put that in context, and also the output to target processes that we have out of those systems or which we try to reach as a target. And then I will give you a definition what we mean by memory and forecasting capacity, and what we managed to obtain would be the upper bounds. Well, the lower are quite trivial in this case, but the upper ones are something that we were hunting for, and it will take place in the setting of the stationary inputs. And also I will put that in relation to already known results, classical results, well, starting from Herbert Jaeger from 2002, on memory capacities for linear systems. And there we will see how actually the bounds that we have formulated for particular assumptions, they just result in well-known actually bounds that you have available for reservoir computing systems in particular. And then what is nice, since we're here on the symposium, which is devoted to these relations, beautiful relations between dynamical systems and reservoir and machine learning systems, and we're trying everybody here to explore these links and implications that dynamical systems offer for machine learning literature, and the other way around, what machine learning literature can offer in order to get some insight about dynamical systems. There would be a nice link between these memory capacities I will be talking about and the well-known Kalman controllability conditions for linear systems. So we will see how these two concepts are related to each other, and to our knowledge, this is the first result on that matter. So, and it has far-reaching practical implications. You will see that in a couple of minutes. And then in the end, I will show you an illustration on the quality of those bounds. We will see that, well, they behave as expected. And something that I need already to tell you, there would be situations in which these bounds will be sharp, and there will be others in which these bounds, well, do not enjoy that property, right? But nevertheless, the result that I will show in this part 6 on this illustration looks very reasonable. Okay, so let me first of all tell you a couple of things which actually have to do with not only reservoir computing systems, but any machine learning paradigms that are out there, right? So now these days, obviously, statisticians are also saying that actually linear regression is also machine learning tool. But here we're talking about more sophisticated classes of models, and something that we're always hunting for as people who are trying to put some models to learn something either that is an observation of a dynamical system or something that well, is in the nature of the stochastic process, which we try to capture. There would be a few properties that we actually want from the machine learning paradigm. So the first one would be something that would guarantee nice approximation properties of those models within some class of, let's say, functions or whatever setting we're in. So here you can think about the success that neural network actually land to universal approximation results by Hornik, Strichko, Tsigenko in 90s, and actually which put neural networks on map once the training schemes for those became available and computationally efficient, right? So here we will want to work with concepts or classes of models which have these universal approximation properties, which we managed to establish in particular for reservoir computing paradigms as well in different contexts. So you can look up our papers on that. So yeah, there is a series of works on that. So on that side, we can be in peace. And in principle for neural networks, classic neural networks, it is well known, and also for deep structures and recurrent neural networks, a little bit more novel results. And actually for recurrent ones is not that yet clear, right? Not in all the contexts that these results are available. What another thing that we may want to hunt for will be generalization properties. What that means that even if those systems, they have nice approximation properties, what we would like to have is also some consistency in their behavior in terms of statistical risks. So there should be some statistical guarantees that go with those models. So presented with different samples, the data generating process for those we do not have an access to. We are in the agnostic setting. So what we would like to guarantee is that once we obtain the parameters of that model and put it to work on for some computational task, at least with high probability, nothing will go wrong. Right?
Sorry for interrupting, but your slides are not moving.
Yeah. So I'm gonna, let me see. Oops.
We're seeing the first page.
Yeah, okay. So what people tend to do in that case is they have this so-called PAC bounds, so probably approximately correct bounds. However, these unfortunately are just probabilistic statements. So, and as always, there are these no free lunch results, which actually tell you that even if you can guarantee in principle that you will have a convergence in probability to, let's say, the best risk, nevertheless, this convergence can be as small as actually one can see in nightmares. So ultimately, these no free lunch results imply that we should look for particular architectures in neural networks, in particular, reservoir computing systems, and any kind of machine learning paradigm, right? So what happens is that is why people spend careers, years on coming up mostly with empirical results, in some occasions, theoretical results on how actually to tune the architecture of a particular, say, neural network, how to choose the number of neurons, how to come up with a number of the layers if we're thinking about deep learning, how to come up with efficient training schemes which guarantee these desired properties of solutions. So here you may want to look at papers by Josef and his group on, for example, implicit regularization. So there are these beautiful results out there on how actually to enjoy nice properties of stochastic gradient descent in different occasions. So for reservoir computing systems, the same thing remains put, despite the fact that we will see that some of the ingredients of the state map that you have already seen in the previous talks will be randomly generated or randomly initialized. Nevertheless, there would be hyperparameter tuning involved. And actually, there are many papers where what people are doing, they're coming up with different schemes, how to tune hyperparameters, how to select the spectral radius of the connectivity matrix, how to come up with, in general, the number of neurons or the dimensionality of the state representation. So all these issues will be extremely important, not only for classical nonlinear recurrent networks, but also for reservoir computing systems, right? So what people have spent their careers on was
Sorry,
also...
but your slides are not changing.
I'm sorry.
We are still in the first page.
In the title?
Yeah, in the title, yes.
I'm sorry. But...
so maybe like reduce the size, not full screen.
I see. Okay.
Are you changing? You can, okay, now we see contributions. Yeah, okay.
Yeah, and now I will move it like this. So like this is better, right?
Yeah, so now you are in page 5, right? Yeah.
Yes.
Yeah,
I
yeah.
apologize for that. I don't know how this happened. Anyway, so the available results on that matter are the people have proposed different measures on the performance of recurrent neural networks and eco-state networks that you have seen in the previous talks already. And one of those measures as a function of some hyperparameters of the system are different capacities. So memory capacity is one of those. The concept is very simple. It has been proposed by Herbert Jäger in 2002, and then he had quite some papers trying to quantify memory capacities to compute them explicitly, and also to bound them whenever the explicit expression would not be available. And the concept is very simple. So what we're looking at is how much of information is contained in the states of the state space system, think of reservoir computing systems, from the previous past inputs that have been fed in that system. So how much it actually captures the dynamical features observed in the past. So in the reservoir computing literature, obviously people have spent much more time with linear and eco-state systems, and especially with linear because their analysis is much simpler. And there you have here multiple references. I have put here many papers all the way to 2019. So for example, by Pietro Verzelli, Levy, Peter Tino, there are multiple papers on that. And also the analytical expression of capacity for time delay reservoirs, it has been formulated in our papers with Juan-Pablo some years ago. And what people were doing, they were using this memory capacity in order to come up with optimized hyperparameters for reservoir computer, right? So what people had in mind is that once you can set up the memory capacity, come up with the expression for it as a function of hyperparameters, then simply by solving an optimization problem, as basically maximizing that memory capacity, you can attain nice performance of a reservoir computer for a class of tasks, in particular for memory reconstruction tasks. So there are other obviously measures like Fisher information-based criteria. Also, you have here recent papers on that. So all these concepts are somehow connected with each other, not always known how exactly, but there are nice papers which try to put relay them in relation with each other. So literature is pretty rich on that. So what are the problems and what are the big things that happen in that literature? Well, usually that memory capacity, and this is exactly how it was proposed by Herbert, they are set up for the case of the independent, or, well, a better version of it if you want less restrictive white noise inputs. So for those cases there is literature, it is very, very vast. Also those references that I gave you, they are mainly the setup, basically the results take place in that setup. So for dependent inputs, the literature is very scarce. So here you have a couple of references, and especially I would like to mention this paper by Sarah Martin, where she proposed not only that she was working in the setting of dependent inputs, which, as you may imagine, is much more realistic assumption than just assuming that we're handling inputs which are independent of white noise, but she also proposed the notion of a forecasting capacity, which has been already known for recurrent neural networks, but she also used it in such a setting that can be used also for the reservoir computing setting. So what she said is that the problem with using memory capacities is that the usual idea that people have in our community is that once you maximize the memory capacity, then for all the tasks that have to do with memory reconstruction and also forecasting, then the performance of our computer will be, well, at least we have hopes to be maximized. And the problem is that she managed to show that if you just work with linear networks, as simple as that, and you optimize memory capacity, what may happen is that, well, forecasting capacity is decreasing, and actually it can get very, very bad. So this is a problem that exists these days, that actually you should not maximize the memory capacity once you want to solve not the memory reconstructing tasks, but also to be good in forecasting. So for that, forecasting capacity should be used. But nevertheless, this was done for linear networks, and in this paper what we were trying to do is, and which we hope will have some practical implications also for people who are using reservoir computing systems for whatever practical purposes, we try to do that for nonlinear networks. So to give you a short overview of things that we managed to do before I go into details. So we managed to generalize these known, if you want, expressions and bounds that are available for memory capacities for linear systems to the case of nonlinear systems, and also for the case of stationary inputs, not assuming any, let's say, uncorrelatedness or even what people are doing much stronger, independence, right? So this is valid in the case of dependent inputs, which is something that is very, very reasonable once we're talking about computational tasks. And also what we managed to show is that, well, those bounds, they collapse to well-known ones under, well, particular restrictions. And then in the linear case, we managed to reveal these nice links between this Kalman controllability condition and memory capacity. And what is already the punchline of this talk will be that for the case, the classical linear case, which has been handled before in those references that I showed to you, and also has been proposed in that setting by Herbert Jäger, in that case, we are not only able to show what has been already known, that the memory capacity is maximal if and only if Kalman controllability condition is satisfied, but moreover, we will be able to show that memory capacity actually is equal to the rank of the Kalman controllability matrix. So for practical use, this has importance. Why? Because now it is not only that we tend to maximize the memory capacity, but keeping in mind that is not always the maximal memory capacity that renders for us good performance in forecasting, we can actually design reservoir in a specific way so that it has a prescribed memory capacity, not necessarily maximal. So we will see how actually we can do it, because since we know that this memory capacity is equal to the rank of controllability matrix, then it's up to us actually to design now the reservoir computing system in the linear case with exact memory capacity that we hunt for. So let me now go to something that you have already seen. So here I will try to be brief. I just mentioned the state space systems that we're working with. So here you can see this 1 and 2. So here we don't assume for now anything about the state map, this capital F, which we have in this state equation. We keep it for now cryptic. I will give you more properties of that state map a little bit later. And what I here mentioned is that the readout map, this H that you see here, which links the states with our output of the system, will be given by affine map. So we will have this W and A, which in case of the recurrent neural networks can be, well, tunable using, let's say, some more sophisticated training schemes, and also with some ingredients of this app. For reservoir computing system, what we will see is that this W and A will be just given simply as a solution of the linear regression model regression problem, and we will see that we will have to handle the specific cases when we will need some regularization in place, right? When the covariance matrix of these XTs will be non-invertible. So very good, we fixed this notation. So actually what this state space system does is just for given inputs produces for us the output via these two equations that actually is the state equation and the observation one. So the recurrent neural network, usually what people mean by that is that this F is exactly the neural network-like state map, okay? So just to put that in context with the classical literature on neural networks. So what we will be doing here, you already have heard in previous talks about eco-state property, we will work not with any state space systems, but we will work with such that determine an input-output system, which happens at the presence of this eco-state property, which, as I said, has been the subject of discussion already the whole morning, right? So we have two versions of this ESP at the level of the system. This is mainly that we will use, and at the level of the state equation. And what that ultimately means is that for any, say, input, here I work with the inputs, which are just infinite sequences, d-dimensional, so this dd will be just a subset of Euclidean space d-dimensional. We will work mainly with compact subsets, so this will be some part of the assumptions in what is coming. And what actually we have as an output will be again the same infinite sequence, but this time around we keep this m as a dimensionality to denote the dimensionality of the output. So let's keep that notation in mind, that the d will stand for the dimensionality of the input and the m will be the dimensionality of every entry in my sequence, right, for the outputs. So what we will be doing, we will be using our good old tools that we're using, well, in all our papers, will be this filter and functional language, where we associate to those state space systems the filter. We denote, well, we keep these subscripts and superscript in order just to keep in mind that this will be the one which is associated to the whole state space system. So this will be nothing else but just the map that takes us from, well, input sequences to output ones. And whenever we are not mentioning the readout, we're just keeping the superscript and not subscript, like what we have here in this piece of notation. I'm not stopping about these relations with functionals. This is not what we use here. We will be working only with filters. And what we have to keep in mind that keeping that eco-state property will guarantee, well, that this state space system that I showed you will actually determine an input-output system. So this for us will be important, right? That we can recover the behavior from the observing the states or the outputs. Okay, so what are the simple conditions that we mainly use here, and actually which suffice here? There is this vast literature also, we contributed to that a lot, which provides sufficient conditions for this ESP to hold. And there are many occasions in which these sufficient conditions can be characterized, provided. Here what we will be using will be a very simple condition, and the sufficient condition for the ESP to hold will be simply working with continuous state maps with compact targets. And what we will require from that state map is that it will be a contraction on the first entry. In our notation, first entry is on states, right? So it should be a contracting map on states. So in that case, we can immediately have in our hands the eco-state property for any input. And then we will have the associated filter, which has the ESP, the eco-state property, and it will be, well, continuous. So there is also a way to characterize the behavior of those filters in terms of their fading memory properties. But this I leave aside, and this is what Juan-Pablo mentioned in the very first talk, that these fading memory properties, they play a huge role whenever we're using this filter functional language to talk about reservoir computing systems, and in this case, recurrent neural networks in a more general sense. So here, this is all we need actually for things to work. And here you can immediately imagine that for, let's say, for the eco-state network, whenever you're working with some kind of an activation function of a type Allan brought up, so tanh, sigmoid, well, this will be obviously fitting exactly this kind of a setting. Okay, very good. So What is the problem with this is that these state space representations, they are non-unique, right? So it would be fine for us if those different representations of a given filter would not come with different memory and forecasting capacities. So we can find a whole set of different representations which would have different memory and forecasting capacities. And since we want actually to ultimately evaluate, but we at least hope to be able to bound them, we would like to work with those that, for example, keep some kind of invariance properties in terms of capacities, both memory and forecasting ones. And that would be a way to do it. You will see that, well, literally in a minute. So what we will be using here will be a language of morphisms, and there would be properties of those morphisms that actually guarantee for us, in particular, the invariance of those capacities. Well, whenever we're just taking the maps which take us from one state space of one system, say characterized by a pair of the state map and readout, and another system which is characterized by, which is determined by another state map and another readout. So we encode that in this language, encode that in these properties of morphisms. And actually what that means is that if I give you two different systems, there would be a way to define a morphism, which will be simply a map from one state space to another, provided that the two properties hold, so system equivariance and readout invariance will be core properties that will give us the system. Isomorphism, there would be a very neat characterization as well, once we have these usual technical assumptions that LDF has an inverse, it's also a morphism. So in that case, we will be able to talk about system isomorphism and also be able to write it down in a very trivial way, explicitly, as you can see over here. Okay, so these morphisms will play some role for us. And what will be nice is that once I give you two different systems, as I said, we will first try to come up with a representation which is much technically easier to work with. And at the same time, later on, we will see under which conditions actually this new representation of this new system, say F2, H2, right, with the associated state map F2 and readout map H2 will have the same memory and forecasting capacity. So for now, let's just stick to the fact that we would like at least the ESP properties to be propagated through this map between the two state spaces, and that indeed holds. So what that is enough for us to do, I give you just a map again between the two state spaces, and what I can say is that if the target system where my map takes me, it has the equostate property, and for the first one, the original one, there existed at least one solution for each input, then what I will automatically have is that in case if this F will be a morphism between the two systems, then what I will happen to have is that the original system also will have the equostate property, and moreover, the filters which are associated to those two systems, they actually are the same, they coincide. So for us, it will have very neat implications. So obviously for isomorphism, even things are even better because then you can switch between the two systems without any problem, right? So we will see how these morphisms will intervene. As for the input and target processes, what kind of a setting we're in, we are working with the stationary inputs and stationary outputs. And here what we mean is we don't work with a strict stationarity case, despite the fact that it will have very neat, will give us very neat tools for analysis. Nevertheless, it is very difficult to test for the strict stationarity. Everybody knows that. So just invariance of distribution, basically with respect to the time shift, is very difficult to establish, to verify, and to check that the assumption to be plausible or not valid or not in some particular practical situation. So what we hunt for is to work with a second order stationary situation, so where we just say that in the case when we are working with a process which is square integrable, the mean stationarity and autocovariance stationarity gives us second order stationarity, so which means that the mean and autocovariance, well, they're not functions of time, right? And in the autocovariance case, it's just a function of a lag. And in particular, we will work with the covariant stationary case. So where what we require is the autocovariant stationarity only for h equal to 0. So only the covariance itself has to be independent of time, constant in time. And then we will work with white noise, where we'll just the uncorrelatedness of the input for the z's, right? And which means that, well, all our autocovariances for any leg different from 0 will be equal to 0. Okay. So now what we have here is this beauty that I told you, that, well, this stationarity gives us stationary states. So if we would be working with a strict stationarity case, everything would be nice, because this, whenever I'm giving you the strict stationary input, automatically the state process will be also stationary. The joint process of time shifted any way we want the state and the input processes will be also stationary. So this will simplify for us the analysis. Unfortunately, well, if we are in the case of the second order stationarity, these two concepts, they are equivalent only for Gaussian processes, and we don't want to restrict ourselves to that. So we work just with the covariant stationary or second order stationary situations. So these morphisms that I just showed you gives us a very nice, neat tool to standardize our system, right? So what we know very well, that working with standardized states is much simpler, mean zero and covariance matrix identity. So these morphisms tell us that actually, technically speaking, this is valid, because what we can do, we can simply come up with a morphism that actually will be, it's going to be not only morphism, it's going to be an isomorphism, and it will be just a standardizing map that actually gives us the two isomorphic systems, the initial one and the standardized. So for us, it makes no difference to work with one or another, and analysis becomes much simpler when we are working with the standardized ones, for which, for this state x tilde, well, the mean is 0 and the covariance is identity. This will give us the tool to bound our capacities in a very neat fashion and elegantly. So if you want, this is a very simple idea which actually helped us a lot. So memory and forecasting capacities. The idea is very simple. With using this definition, actually, the only assumption that we have is that we're working with inputs. Here, for simplicity, we're working with univariate inputs, which are variant stationary. And we assume that our state map has the ESP. As I said, these are the systems that we're working with respect to inputs, the paths of Z. And moreover, what we require is that the state process is covariant stationary, which is implied automatically only in the case of strict stationarity, but for variant stationary inputs, unfortunately, we have to assume it additionally. And then what the same thing happens for the joint processes. And please mind that we have this pair, this joint process over here and this process over here. They will be used respectively for the memory and forecasting capacities, because what we will be looking at is how much the output of our system remembers the past inputs for the memory capacity, and we will see how actually the state at a given time reflects the inputs that are coming, right? And in that case, we will be talking about the forecasting capacity. How we define it? Well, in principle, the definition is what you see. Here we are regressing what will happen, what actually happened before. We are regressing what happened on what the states, what the filter associated to the state equation gives us at the time t. And for the forecasting capacity, we're doing the other way around. What we're trying to see is how much actually the target, the states that are provided by our state space system can tell us about the input which is coming in some given delay tau, okay? And what we're doing, we're just dividing by the variance of the ZT. So this optimization problem can be solved explicitly, right, for some occasions. So one of the occasions is, for example, whenever our covariance matrix is invertible. In that case, this memory capacity for any leg tau and forecasting capacity are nothing else but what you see in front of you. So this is a covariance of the previous, keep in mind that this t and tau are in Z minus, so the previous inputs with the current state, and well, other terms alike. And the forecasting capacity is the covariance of a current input, right, with the previous state. defined through this covariance. So this is the main ingredient that we need, and also the covariance matrix of the states. If you have them, you have the memory capacity and forecasting capacity, and that is why people used that a lot in empirics, right? Whenever they were trying to evaluate this memory and forecasting capacity. Momitian, I'm sorry, I forgot when I started.
You started at, yeah, 1 minute. Yeah, you finish at, you have 10 minutes.
Okay, very good. So thanks a lot. So this explicit expressions for memory capacity tells us that whenever we know how these covariances look, how the covariance of the states looks, right, under the assumption that it is invertible, we can actually compute them. The problem is immediately if you see it, you see that this state is coming in principle from the state equation, which has this state map, which is nonlinear, right? So evaluating these covariances under assumptions which are, let's say, weaker than independence or white noise will be very difficult. And that is the main, if you want, problem in that literature. And we tried to cope that for time delay reservoirs where we were able to actually compute this memory capacity, or at least to propose some expressions under the assumptions of high order stationarity. But nevertheless, the expressions, they are truly awful, and it's completely intractable, right? So this is the main problem in this kind of literature, right, for the nonlinear case. For linear case, one can do much more here, especially if you use some assumptions of independence of the input signals, or you use, for example, the white noise assumption. You can still do something, and you can compute, for example, the memory capacity. But this happens also only in the case whenever, as we said, these explicit expressions are valid only under the assumption of invertibility of our state covariance matrix. And this is not always the case. And for people who are coming from reservoir computing literature, immediately this looks a little bit alarming. Why? Because we do know that for the reservoir computing systems with high dimensionality of the state space, usually what you end up with is the covariance matrix, which is singular, right? So this singular case is always haunting us, and that is why we come up with these Tikhonov regularized linear regressions, so that we can somehow overcome the non-invertibility of the covariance matrix. So we will have here a few problems, right? First, this may be in general not available due to non-invertibility of gamma x, even for the linear systems. Second obstruction is that for linear systems, for something which is milder assumption than independence or white noise, this also will present a problem to be able to compute it. Not to mention the nonlinear systems, right, for which in general computing this memory capacity or forecasting capacity is something which is completely intractable, right? So these expressions will be intractable. So what we're doing here, we will be pursuing in the following step. So the first idea would be immediately, as already an advertisement, is that we will be able to bound actually those memory capacity and forecasting capacity for general nonlinear situation. And we will be able to provide explicit expressions for them for the linear systems. And moreover, even in the case for non-invertible covariance matrices of the states. The way we handle it will be through this morphism language. And I told you that what we can do, we can propose actually such maps between the two state spaces with these morphism properties that actually guarantee for us that the capacities will stay unchanged when we go from one system to another. However, technically, that will simplify things for us, because what we will be able to show is that there would exist such morphisms that actually give us new state space system with a state space of lower dimensionality, but for which this covariance matrix will happen to be invertible. So this will be the main tool that we will be using. Okay, very good. So we know how these people look like. So we know that these morphisms that actually guarantee for us those properties, they will be simply nice basically linear injective system morphisms, and they will be put to work for us for the cases when this gamma X happens to be non-invertible. So if you want, this is the only tools that we will be using here. Let me present to you the main result that we have. I'm not getting into details for the proofs. You can open them, they're neat, and you will see there is nothing really sophisticated there. But what we managed to show is that in this conditions of this definition of the memory and forecasting capacity, which I remind you only needed the state map to have the eco-state property. So the eco-state property has to be satisfied only on the state equation level. We worked with the variance stationary inputs, and we were additionally assuming that also the state process is covariance stationary. So these are the only things that we required. And here, let us start from the case when we assume that this covariance is non-singular. And in that case, what we can do, we can come up with this bound. For those who like to work with spectral densities, we have this resulting 5, where basically it's the same, whatever you want. Actually, you can use those. You have additionally to assume actually simply the absolute summability of your autocovariances, right? But nothing else actually is used in this part 3. The main bound, let us look at it more in detail, will be this one. What this bound tells us is that obviously our memory capacity and forecasting capacity, they are non-negative, and they're bounded from above by some quantities that encode some important information, not only about the system, but also about the inputs and targets, right? So here we have the number of the neurons, and we have the covariance, right? Gamma 0, which is the covariance of our states. And what is more, sorry, this gamma, this time around, this is the covariance, the autocovariance of my input process. So basically the variance of it, right? And then we have the quantity here, this rho of H, which, well, it's, you need to come up with this specific Toeplitz matrix for different legs. And then you need to look at the limiting behavior of the spectral radius of those matrices. But ultimately, if you want to see that in action in a more explicit fashion, look at this one. This is the upper bound that we have both for memory and forecasting capacity. And this encodes the variance and autocovariance behavior of our inputs, and it encodes the information about the state dimensionality, state space dimensionality of the network, right? So this is nice. And what is nice also, that if we think of the classical results of Herbert Jäger, and we're assuming now that we're in the case of independent inputs, well, these results will collapse to the well-known results, which actually tell us that the memory capacity is bounded from above. This is known from his paper of 2002, since then, by the number of the neurons, right, or dimensionality of the state space. And forecasting capacity, something that you would immediately expect, will be equal to 0, since we have independent inputs. Well, forecasting capacity is sharp 0. Let me go a little bit further in this little time that we have, and I show you, just flash on you the results that we have for linear case, okay? Which we find very nice, because for linear case, we are not able only to bound the memory and forecasting capacities, we're also able actually to provide the explicit expressions, right? And this is nice for people who are designing, let's say, reservoirs with linear state equation, right? So the linear reservoirs, this is something that would be nice to use when you're thinking about coming up with a specific forecasting of memory capacity. So here what we assume is that, well, our state equation is given to us simply by the, determined by the two objects. This is A, this is our connectivity matrix, and our C, which we call input mask. So this just matches the dimensionality, and usually for reservoir computing systems, those are randomly drawn, right? So let me show you the results that we obtain, which we find very nice. So the only thing we need is we need to guarantee the eco-state property, which comes down to just choosing, well, the matrix, or generating the matrix A, or estimating the matrix A if you are in the classical recurrent neural network, such that its largest singular value is smaller than 1, and basically this is all that you need to have the ESP. And then in the same conditions as I showed you, so for, well, let's say with the second order moments, finite, absolutely summable autocovariance functions, and so on, we're able, and non-singular covariance matrix of the states, we're able to provide these explicit expressions for the memory capacity and the forecasting capacity. So here you can immediately see that also these are explicitly computable. You can come up with those. And actually, well, this is something that one can do easily for linear systems. And I'm running out of time, so give me just one more minute. This result also collapses to the well-known for linear systems, again by Jaeger and other people in the literature, where we know that in the case of a classical linear situation, when we have we are in the conditions of the white noise and linear state equation, then the memory capacity is equal exactly to the number of the neurons, or if you want, the dimensionality of the state system. And what we can say is that obviously linear systems with white noise inputs automatically have maximal memory capacity. And finally, let me show you just one nice result that we have in the end, where we are able to do the same kind of analogy for the singular case. You can look at that in detail, but what I want to show you is that in the case when these covariance matrices of the states are non-invertible, using these morphisms that I showed you, which are capacity preserving, we're able also to prove a series of results. And for example, the one that tells us that once I'm ending up with a new system for which my covariance matrix of the states will happen to be invertible, in that case, what I will end up with is a sharp characterization of a memory capacity. Memory capacity will be equal to the rank of the controllability matrix. Or if you want, this controllability matrix is the one which is rendered by the Kalman controllability condition, right? That we know that, well, these vectors that you see over here, so C, AC up to A to the power n minus 1C, has to form a basis in Rn, right? This is a controllability condition a la Kalman. So this condition actually is equivalent to what we see over here, to the invertibility of the state space, and moreover, coming up with this controllability matrix and computing its rank, we can immediately say what will be the memory capacity. So you can use this condition in order to generate a specific reservoir computing system. Let me finally conclude with this nice illustration, and I finish here, is we try to see if those bounds are sharp or not, right? So what is nice to see here is that what we did simply is that we used as an input very standard time series processes. So autoregressive of order 1, moving average of order 1, and ARMA 1, 1. And then what we took was a reasonable reservoir, or if you want, linear state space system with a dimensionality of the state space 15, number of neurons 15, right? And in that case, we know that once we're feeding well, our system, if we would be feeding it with a white noise, right, or independent inputs, the rank would coincide with 15, right? We are nevertheless feeding it with the inputs of the AR, MA, and ARMA structure, and we want to see how sharp are those bounds, right, for the linear case. Let us see that in action. What we can see immediately is, so here what we have, let me show you in this example, we have the value of the phi, which is a parameter in our AR, right, polynomial. And it varies from 0 to 1 in order, well, to guarantee the stationarity, right? We have that the phi should be smaller than 1, I remind you. And what we're doing, we're looking at the log capacities, and we're plotting theoretical bounds, forecasting capacities, and memory capacities. We know the results for the memory capacities in the literature, that whenever we're working with independent inputs, right, our capacity should be sharp equal to actually the dimensionality of our state space, which is the case. You don't see that for the log scale, but believe me. And also it coincides with the theoretical bounds that we have. Unfortunately, you can see that as we separate from that case, in many occasions, the behavior of the bounds is as is expected, but they are non-sharp. And suggestions for the future work would be to see what are the links between this memory and forecasting capacity to come up with sharper bounds. And also there is this link between controllability and memory capacity, which we saw for the linear systems, right? Which are very suggestive, so, and which need to be explored, obviously for non-linear cases. And this would open, I'm sure, a whole path of, a whole field of research that can be actually very fruitful. So I just invite everybody to look into that. We found that pretty and cute result. And obviously it links and talks to all these empirical papers that you have in vast majority, trying to characterize and to come up with a higher memory capacity and forecasting capacity for different reservoir computing systems. Thank you very much. Sorry I took a little bit longer.
Yeah, all right, thanks a lot. So we'll just move to the next speaker. Yeah, thank you.
Hello, everyone. Can you hear me?
Yes, we do, yes.
Okay. Can you see the screen?
Yes. Can you change the slides just to make sure that they are changing? Yeah. Okay. Yeah, that's working.
Okay. Okay, fine. Hello, everyone. My name is Pietro Verzelli, and today I'm presenting the work conducted with Cesare Lippi and Lorenzo Livi, which are my two supervisors during my PhD. And I choose the title, Learn to Synchronize, Synchronize to Learn, Measuring the Echo-State Property, because that is what we're trying to do. So basically we realized that in recent years, many work have been devoted to study the relationship between the synchronization and the echo-state property, because they seem related concepts. And we want to actually show this relation in a formal way and show that it could be exploited to find nice results. This is going to be a short pitch, basically, because I only have 20 minutes, more or less. But I invite you to see the longer video, which is posted on YouTube, and also a paper should come out in, like, hopefully this week or maybe the next one, but it should be out soon. So in there you will find all the information about this this issue and this work, basically. So I'm going to start by describing the synchronization and what it is. Then I'm going to describe the reservoir computing paradigm, and then discuss some experiments relating the two concepts which have been introducing. So I start with synchronization, which is based on the concept of sensitive dependence of initial condition, because this is the problem with chaotic systems, that if you have two systems which are identical, as in equation 1, but their initial conditions slightly differ, they will move apart. So if at time 0 the initial condition differs slightly, we will see exponential divergence. While if they are the same, they will stay the same and be like that for every time, because of course the time is the systems are identical. But this exponential divergence actually leads to the phenomenon of uncorrelation between the two systems, because even if they are living in the same attractor, again, because their equations are identical, they won't be correlated. Their motion would be correlated. And this is actually a side phenomenon of chaos. And one may want to synchronize these two systems. So you want to decide a coupling between the two, which relates them, and so that the evolution will converge in some sense. And the sense is the one described here in this definition of complete synchronization, where two identical systems are said to be in complete synchronization if the distance between their state goes to 0 as time goes to infinity. So of course, this is an asymptotic property, but because we are in a non-autonomous framework, but of course that's what you would expect from that. And so what we are actually requiring is that after a transition period, the state of one system is identical to the state of the other. Okay, this seems pretty obvious, and this is the notion of synchronization that one would give in general, the most maybe obvious one. But one might want to generalize this idea and have a generalized synchronization for systems which are not identical and not even similar. Maybe they have different dimensionality, different equation, like in equation number 2, but still you may want to need the concept of synchronization. And there are many ways of describing it, but the one we choose is this one, where basically you say that the trajectories of two systems are said to be synchronized in a generalized sense if there exists a synchronization function.
Yeah, sorry. So your slides are cut off from the bottom. Maybe you should zoom out.
Okay, but it's strange because I have the presentation mode. Maybe I use this one. Is it better now?
No. Zoom out. Yeah.
Okay.
Yeah.
Yeah. Okay.
Yeah.
I stay like that. Okay. That's gonna be okay. A bit of pain, but it's fine. So I was here. Okay. And so this is the new definition of generalized synchronization, or better, this is our definition of generalized synchronization, which generalized the notion of synchronization that we've been given before. Because of course, if the phi function is the identity, this reduces to the idea of synchronization, the complete synchronization. But here, we have a far more wider possibility to use. You know, we have many options because phi can be a general function. Basically, you will actually require some smoothness, but it's not required, at least theoretically. And so, what you want a function that maps the attractor of one system X to the attractor of the other system Y. And you want this relationship to be time independent. And if you say if it is so, then you can say the system is synchronized. Because to every state X of the first system, it corresponds a different system of Y, a different state of Y, sorry. Okay, and this is pretty nice because it really raises some possibility. Of course, the problem is to find actually the phi because it's really hard to find it in general. Luckily, we have a different definition, which was proven to be equivalent to the generalized synchronization, which is the asymptotic stability. And basically, it says that if you take two copies of the system, identical copies this time, so it relates actually to complete synchronization, and you let them be driven by the same system X, which is an input in this case, the system X and Y are said to be asymptotically stable if it converts to zero. If the distance converts to zero, as in the equation. I'm sorry, I think I've bit confused you in a way, but I think that the equations are clear. So you have two identical copies of the system. You let them be driven by X, the same one. If they go to zero, it means that the system has asymptotic stability with respect to X. And of course, this might resemble reservoir computing framework because this is basically the echo state property formulated for dynamical system, right? This is exactly the same idea. And okay, so after I've been introducing all this framework, I'd like to move to reservoir computing, which hopefully everyone is familiar with. And so I'm just describing the framework in a higher way. You know, this is, I'm not specifically referring to reservoir computing network or echo state networks, but I'm just describing the framework in general in the dynamical system idea in mind. So S is our system model, which is the system we would like to model, okay? And this is the system generating our input, U, and our output, Y. The assumption here is that both U and Y only depend on S each time, okay? So we have like this highly dimensional system, which is unknown and unknowable, actually. And we have some observation U and some observation Y's. U are the observation that we use as an input, and Y are the observation that we use as output. And that we want to, is a target, the target we want to learn. So the goal would be reproduce the target Y without the knowledge of S, but only knowing the measurement U. That's the basic idea. Of course, if you divide in training and testing phase, in the training phase, you would have both U and Y. In the testing phase, you only have U and you want to predict the Y. This is pretty standard in machine learning and in reservoir computing as well. So we have some assumption underlying this framework. So we have no knowledge of the system model, as we've been said, and we have a large collection of U and Y. And it is possible to predict Y from the knowledge of U. This is important because it might be not possible to do so. So the assumption is that it is actually possible. And as I said, lately you will only have U and not Y, and you want to learn to predict new Ys out of new U's. And how do you do so in reservoir computing? You create a new reservoir system, R, and you use it to represent your input. This will create a highly dimensional representation of your input. And then you train a readout to read out, of course, it's a readout, to read out the state R and generate your desired input, output Y. Okay, so we split the training phase into different phases, as is common in the literature. The first one would be listening, where you generate this R with a new F, which is this evolution equation. But this time, differently from S, this system is not autonomous. It takes R as an input, but also you, your input. And of course, you can do this. This is in machine learning, you would call this procedure untrained, because F is random in some way or partially random. And so you don't get to choose anything. You just select your hyperparameters and then you let them go. And you end up with a set of states, R1, R2, R3, each one for its time. And this is an input-driven system where U is the driver. And then you fit. You have this whole sequence of R's, and then you train a readout to generate your Y hat, which is the symbol for our target output that we generated. And you want it to be similar to Y, the true output that you aim at generating. And what I've been describing is an offline learning procedure, but of course you can also use online learning procedures. They are in some cases analogous, in some cases not, but this is what I'm talking about. This listening and fitting are two separated phases, and this is our framework, which is, I would say, the most common for what I've seen, because that's actually the advantage of reservoir computing. So this is a diagram that which recap what I've been saying. So you have your system S, you get an observation out of it, and you couple it to the reservoir R, and you train a readout psi to produce your Y hat, and then you compare it with your true target Y. Okay, so all this framework is based on the echo state property, basically, because in the seminal paper, Jaeger proposed it as a needed to. So it says you need to have this property, and basically it is compulsory to have it to require a feasible computation, acceptable computation, a working one. But many important results, of course, can be proven assuming the echo state property. But proving it actually is hard in typical cases. And often you end up assuming hyperparameters which are far away from the optimal ones, especially the spectral radius. It usually gets to be 0.5 or less than 0.5 for many frameworks. As many people know, that if you actually try to use these networks, that spectral radius 1 or higher usually works better, not always, but usually. So there is a sort of a gap between our theoretical knowledge and our ability of proving results compared with the actual framework and what actually people are doing. But as I said, accepted property in our context is exactly asymptotic stability. And so we can use this relation between the state S, the source state, which is unknown, and the reservoir state R, and formulate it in this new framework using generalized synchronization. So say, okay, what I actually want is that every state R of the reservoir is a function of the known system S. I don't know S, I will never be able to measure it, but I can assume that this is true in some cases. And this is possible because the training does not affect the dynamics in the reservoir. As I said, you have the listening phase, which is independent, and only then you train your readout. So the readout actually estimates a static mapping between R and Y. And we know that Y, by assumption, is K of S. So it's a function of our source system. And due to generalized synchronization, R can be written as a function of S. And so we have this nice relation that we expand our S into an unknown function phi, that we hope it is good enough for the readout psi to read it and generate our desired output, Y, which is K of S. So all of this relies on the fact that K of S, Y, is a function of S only, and is not time dependent. So given an S, we have a Y. And also that it is possible to do the same on the left-hand side. I'm running out of time. Yes?
Yeah, 2-3 minutes left, yeah, because I accumulated a lot of delay. Yeah, thank you. Okay.
Yes, I just go to the results. So, okay, this is basically the strength of the reservoir computing. And just showing this experiment, I use a measure of this, which is mutual fascinating networks. I don't give the details. It's a measure of synchronization. If it's I, it means that the systems are not synchronized. If it's not I, it means that it is. So I'm not describing the reservoir computing model, it's just a reservoir network. And this is the task, right? You read the X coordinate of the Lorentz system, and you need to reproduce Y and Z. This is what you're going to do. The red one is what you don't know. And so after a while, you don't get the Y and the Z anymore, and you need to be able to reproduce it using the readout and the form we described so far. And so I plot the correlation between the spectral radius, which actually accounts for the instability of the readout of the system, sorry. And I plot on the left, on the blue axis, the error, and on the right axis, the synchronization measure, actually the desynchronization measure, and you see that they are somehow related. In a finer scale, it would be more obvious, but I plot with error to be more consistent. And I replicated with some different measures and also with some different systems, like here we're trying to predict, and here we're trying, you use the Russell system instead of the Lorentz, and it's more or less always the same. And so to get to the conclusions, I'll just skip it to it. So you want the exclusive property to hold because it guarantees a reliable computation, but you can prove that it is the same as the asymptotic stabilities. And the asymptotic stability implies and is implied by generalized synchronization, so that you can start with the generalized synchronization and use it as a both practical and theoretical tool to describe what you're actually aiming at. And another advantage is that it can be measured using the measure provided above. And so it's really, really useful compared to echo state property in past formulations. And that's all. Thank you, everyone. Sorry for the slight delay. Okay,
yeah,
bye.
Yeah, thank you very much. So do you have a pre-recorded version of your talk? Or?
Yes, 1 hour long one. So
yeah,
there will be a lot of details there.
Yeah, okay, good. Thank you very much. Yeah, okay. Yes, and now we can switch to Graham Rollins.
Hello, everyone. I'd like to tell you today about full nonlinear control of a chaotic system using a reservoir computer. My name is Dan Gauthier. I'm at The Ohio State University, and this project was done with a few grad students and postdocs and many collaborators over the years. And the work on control was mainly done by Daniel Canaday with a lot of input from Andrew Pomerantz. And this work was originally funded by the Army, then DARPA here in the United States, and then most recently by the cortical program of Raytheon BBN Technologies. So in the long talk that I gave that is pre-recorded and already posted, I covered a lot of ground on how to use a field programmable gate array as a physical substrate for reservoir computing. I'm not going to touch on these topics today. Daniel Lathrop will be giving the next talk. We'll be discussing some of these topics. Today, I'm just going to focus on controlling dynamical systems with reservoir computers. So the idea for control is that I have some kind of dynamical system, which in the control language is usually referred to as a plant, and that we have to design a controller so that the controller takes a desired behavior, figures out how to apply perturbations to the system so that the output state is equal to the desired behavior. And in general, the plant is going to be described by some kind of nonlinear system that is a function of both the dynamics of the plant itself, as well as some accessible system parameter U of t. So I've got some kind of knob that I can adjust that will change the plant dynamics. And so the goal of designing a controller is that I want to take the desired behavior and the current behavior of the plant and use that to predict the control perturbations that I have to apply to the plant. And the goal is that in the asymptotic limit, the plant is equal to the desired behavior. And so for nonlinear control, it's a challenge to figure out this function G. So the idea is that we'd like to be able to invert the dynamics of the plant to figure out this nonlinear function. that tells us what perturbations that we need to apply. That is, given the plant dynamics and this input, I would like to be able to know what U is. And the idea is to use a reservoir computer as the controller to figure out how to invert the plant dynamics. And everything that I'm going to talk to you about today was motivated by this very nice paper published back in 2012. This is kind of the base upon which we're working from. And just to review what was in this 2012 paper, so the idea is that we have two different phases. I have a training phase where I train the reservoir computer to learn how to invert the plant dynamics. And then I have a control phase where after the reservoir has been trained, I am going to input the desired behavior of the plant, and the reservoir will tell me how to perturb the system. So let me walk you through these two phases. They're a little bit complicated, but I'm assuming that I can read out the plant dynamics. I'm going to feed the current state of the plant into the reservoir, and then I'm going to have a small finite time delay, and I'm going to feed the time delay version of the plant dynamics into the reservoir. And the output layer then is trying to make sure that the reservoir reproduces some input signal U of t that I'm using to perturb the plant. Now, since there are some time delays that are in here, I also have to delay this. So the goal of the reservoir is to have it trained such that it reproduces this perturbation that I'm applying to the system, but at a delay time tau. And what is suggested in this paper is that we just make U of t random so that I'm constantly jostling the plant to learn how it responds to perturbations. And so the training goal, again, is just to have the reservoir produce whatever the perturbations are that are being applied to the plant. And then I flick a switch to turn this now into the control phase, where I now just feed in the current state of the plant and then the desired behavior some time in the future. And sorry, this is a typographical error. This should be tau instead of delta here. And if I've done things right, the reservoir has figured out how to invert the plant dynamics. And what's coming out through the output layer is the perturbations that are required that need to be applied to the plant so that one step tau in the future, it's properly controlling the dynamics. Now, in this past work, they have applied this to several different linear control problems or weakly nonlinear control problems. And our goal is to apply it to do full nonlinear control of a chaotic system. So the idea is I'm just reproducing some of the equations that I had here before. This is just the dynamics of the plant, and in a moment I'm going to be thinking of the plant as being the dynamics of the Lorentz chaotic system. The perturbations I need to inject into the plant to control it is some nonlinear function. And the idea is that for some short time tau, then the state of the plant one step in the future is some function, capital F, that I don't know, it's not exactly this function here, but it's related of the current state of the plant and the perturbations. And what we know from the last talk in the previous section, that I should have generalized synchronization of the reservoir to the input signal. So the idea is that the dynamics of the reservoir, which I'm denoting by x of t, should synchronize to both the desired behavior one step in the future and the plant behavior. So the idea is that once it's trained, U of t is just going to be some output matrix of some functional of the perturbations in the current state of the plant. And that just ends up being the inverse of the plant itself. So that's what I mean by the reservoir trying to learn in inverse of the system. So as I mentioned on the previous slide, we're going to try to control the Lorentz 63 system. This is the standard equations for the Lorentz, but in a slightly different notation. With these parameters, it's running in this chaotic regime. And these U's are perturbations that the controller, as the reservoir, is going to try to control. And so the idea is I'm going to input all three of these variables into the reservoir. And if it's properly learned the inverse, I then tell it what I want to do, and the reservoir will figure out how to apply these perturbations. We've very successfully have been able to control the Lorentz system by stabilizing it to its steady state. So there's an unstable saddle here and two unstable fixed points here. We can stabilize all three of those. We can stabilize unstable periodic orbits, similar to what was done 20 or 30 years ago in controlling chaotic systems. And we can even control orbits that are not on the attractor. But for what I'm going to show you now, we're going to focus on stabilizing the unstable saddle that's at the origin. So we go through this training process of trying to learn the inverse dynamics. And then what we do is we just replay the same data back to see how well did it really learn the inverse of the reservoir. And the blue line is how it's learned the inverse. It should be exactly equal to the orangish line. And you can see it sort of gets it right, but it doesn't really do a very good job. And when we try to do control of the unstable fixed point, we see that the control error is quite substantial. And what will be important for the next couple of slides, we're using 100 nodes in the reservoir for this particular case here. So what I'm showing here is that if we look at what happens as we increase the size of the reservoir, that is, increase the number of nodes, this is a well-known way to improve the performance of the reservoir. And this red line here shows how well we're inverting the plant. And sure enough, as we increase the number of nodes in the reservoir, the plant inversion error gets smaller and smaller. However, if we look at the control error, that is how well does the reservoir really control it to that unstable saddle at the origin, what we find is that the control error is quite large. And then as we get to a critical size, there's a bifurcation, where suddenly the control error drops, takes on a minimum value. Then it actually gets a little bit worse as we increase the size of the reservoir. So this is something that is quite unusual in the reservoir computing literature. Usually you just make the reservoir larger and it's going to perform better. But this data clearly shows that there's an optimal reservoir size. It's roughly around 30 nodes. And we find that this is the case for controlling a wide range of different dynamical systems besides Lorentz. We always find that there's an optimal reservoir size, and we always have a finite control error. So that led us to the idea of a new concept of trying to make what we call a layered or a deep reservoir computer controller. The idea is that we can think of the plant and that first reservoir that we applied as a new dynamical system, and that I can use a second reservoir on top of that to control the plant plus the first reservoir. So again, coming back to controller now is really one reservoir that's applying perturbations to the plant. And then I can now think of this reservoir and the plant as a new dynamical system, and I add another layer which just runs in parallel. It takes the desired behavior, the plant dynamics, feeds that into the second reservoir, and we just sum the perturbations from the first and the second reservoir to generate a composite control system that's applied to the plant. And what's nice here is that adding layers only scales in complexity with the number of nodes that are in each one of these reservoirs. Whereas if we just made one reservoir larger, well, we already know it doesn't work very well. The we get to a finite control error. But the training time scales with some polynomial power of the number of nodes. So this is a very efficient way of trying to control the reservoir. So I think of this as maybe a onion or a type of doll where everything is layered one on top of the other. So what we see is that what I'm plotting here on the vertical axis on a logarithmic scale is the control error, the actual plant behavior relative to the desired behavior as we add more layers. So this is the control with 1, and it goes down to some finite error. Then we add a second controller, and we do orders of magnitude better, a third, a fourth, and a fifth. So we can just asymptotically drive the error to 0 just by adding more layers. And in all of these cases here, we just fix the number of nodes per reservoir to 30, and we see quite dramatic improvement in the control. So we've...
I have a question, please.
Yes.
Why at 0 error equals 10?
Sorry, questions are only at during the break, so we don't have a lot of time. Yeah, so you can ask the questions later. Yeah.
Or send me a message. Yeah, what I have to say is we've pre-trained everything along the way, so we're just showing what happens as we turn the switch after we've pre-trained each one of the layers. So this transient behavior is just the dynamics of the controller as it's trying to control the system. So we've built an experiment just based on a chaotic electronic circuit that I developed back in the 90s. It's a double scroll type attractor. There's 2 capacitors, an inductor. The dynamical variables are the 2 voltages across the capacitor and the current going through the inductor. There's a nonlinear coupling between what's called a negative resistor. Instead of sinking current, it sources current, so it's an active element that charges the capacitor, and that couples through this nonlinear system to what's called a tank circuit. It has the characteristic frequency associated with it. In this case, we just measure the 2 voltages, and we apply only a feedback signal, which is a current that is injected into this capacitor. And if we look at the attractor, when I plot just these 2 voltages, you see this characteristic type behavior. There's an unstable saddle, there's unstable fixed points at either side. And this is a fairly fast circuit, the way that we've configured it. The characteristic frequency is 50 kilohertz. And we end up using a field programmable gate array just to accelerate the code for a reservoir computer. So it's just a very inexpensive FPGA that just parallelizes the evaluation of the reservoir. And we can achieve with a control loop latency of only 2 microseconds. That is, when we do a measurement, we can apply the perturbation within 2 microseconds after the measurement. And this time scale is very, very short in comparison to the characteristic time scale of the attractor, which is around 50 microseconds. And so we've been able to control many different behaviors. I'm just going to show 2 different examples. We've gone and pre-trained the reservoir. This is now voltage of V1 and V2 measured from that circuit as a function of time. This is the chaotic dynamics. Then again, we've pre-trained it, so we turned it on, and the goal is to stabilize one of the unstable fixed points that's on the leaf of the attractor. And then we drag the trajectory to the other fixed point, and then we drag it back. And so this here is the current that the reservoir computer is injecting into the circuit. So here, this is just the characteristic noise level of our electronics. There's no control turned on. Here we turn it on. There's a large control perturbation as we force it to one of the unstable steady states. And then as we drag it from one unstable steady state to the other, there's another large control perturbation, then it settles down. And then when we drag it back, a similarly large control perturbation. And then after this dashed line, we add another reservoir, and we see that the control perturbations needed to drag it from one unstable steady state to the other get smaller as we add the second controller. And so this is just an attractor of the actual data. The blue dots are the uncontrolled attractor. And then when we turn on control, it goes to one of the fixed points here. And then the red dots show our desired behavior. This is what we're asking it to do, to drag it over to the other fixed point. And the orange lines are what happens when we have the first controller. You see it has a little bit more overshoot in the dynamics, but then eventually it settles down to some noisy point here near the unstable fixed point. And then the green is when we add the second controller. So it doesn't do perfect. It doesn't exactly follow the trajectory where we're only using two reservoirs, but it does a pretty good job. So this shows something that would be very hard to achieve using any other standard chaos control technique of being able just to drag it back and forth between unstable fixed points. We also asked it to control an elliptical behavior that's close to the attractor, but it's definitely not an unstable periodic orbit of the system. And these two lines show the orange is how well it does with just a single layer, and the green is with two reservoir controllers. So again, this requires a full nonlinear controller. It requires non-vanishing control perturbations to be applied to the system, because this is not a dynamics that's inherently part of the attractor, but just something that happens to be close. So what I've really focused on here is just the application of reservoir computers as a universal controller, and these other concepts of using a field programmable gate array as a physical substrate for reservoir computing is in my longer pre-recorded talk. Thank you very much for your attention.
Yeah, thank you very much. Yes, and we can move to the next speaker now. Thank you.
Okay, let me share the slides. So first, I'd like to thank the organizers, and yeah, I'm sorry we couldn't have all joined together in Toronto. It's a lovely city. I've missed travel. Dan Gauthier and I were chatting about that. It's unfortunately the remote does work, but it's not the same as in person. There's a pre-recorded talk, which is a longer version of this. I've cut out probably about a third of the slides to sort of give you a preview of the longer talk. And I want to also highlight that JD Pethek is also giving a talk on Thursday, and I have a few slides from the results from the theory group at Maryland that I'll show in this. So I'm going to be talking to you about reservoir computing. Probably the first third of the talk is going to talk about the ability to do forecasting and prediction on weakly turbulent or strongly turbulent data. And then the latter two-thirds of the talk, I'm going to talk about our work to set up high-speed hardware accelerators to do reservoir computing using electronic versions of the nonlinear system. So roughly speaking, everybody on the right of the slide is the experimental group: Heidi Komkoff, Itamar Shani, Liam Shaughnessy, Artur Prevolov, and Alessandro Rastelli, and the theory group then on the right-hand side, and JD's there. Michelle Gervin, Brian Hunt's kind of the math guru for our electronics project, my senior colleague Ed Ott, and John Ross. So I'd like to acknowledge the very helpful advice and inspiration from Dan Gauthier, and funding from the Laboratory for Telecommunications Science, the State of Maryland, and the National Science Foundation. So this covers things that have been said by a number of other speakers, but the basic inspiration for our work is the outstanding performance that we've seen using a reservoir computer to do prediction work. And this is then based on the work of JD and Ed and Michelle, using the reservoir to have a training phase where they determine the output layer, and then closing the loop to do prediction, let's say at time t equals 0. And I was really greatly impressed when I saw JD's talk about the ability to predict weakly turbulent data from the Kuramoto-Sivashinsky PDE. So here's just an integration of that can be used to train the reservoir. And then here it shows the true state starting from t equals 0 is a prediction then, which is the middle color graph. And then the difference between those two shows the ability to predict this weakly turbulent signal for up to 5 Lyapunov times. Moreover, the trained reservoir actually acts as a mimic for the original system, and that mimic can be queried for various dynamical aspects of the original system without having access to the equations of the Kiramoto-Sevashinsky. The reservoir itself is able to reproduce things like the Lyapunov spectra for the system, including negative Lyapunov exponents. And this, really after seeing this, I started thinking about all the various ways in which we could use this, both on experimental data and what experiments we might also do to further the field. So I'm going to show you a reservoir prediction test that we did on experimental data from a liquid sodium spherical Quet flow experiment. So this is a 3-meter diameter rotating outer sphere, 1-meter diameter rotating inner sphere. The liquid is metallic sodium, so it's a magnetohydrodynamic experiment. And we're going to be doing prediction tests based on a vector of 33 Hall probes that just measure magnetic field just outside the outer sphere as a function of time. So this is neither a numerical experiment nor a Gedanken experiment, but here you can see the outer sphere inside the cube, and Dan Zimmerman, one of the original experimentalists who designed and built it up on top of the experiment. And this is really intended as a laboratory model of the Earth's core, but it gives us some nice turbulence data, vector data to test with reservoir computing. So the basic idea is take Hall probe data from the outer sphere in operation. We're at a Reynolds number of around 100 million, and then train over, let's say, 1,000 rotations of the outer sphere. And once the reservoir is trained to predict the next time step, we close the loop and start predicting the experimental data. And here shows a comparison of the prediction in red and the original time series in blue, not for all 33 probes, which is hard to look at, for just from one of the probes. And what you can see is that for the first 10 revolutions, I've scaled time here in terms of revolutions of the outer sphere, we have a reasonably accurate prediction of the ongoing magnetic field data coming out of the experiment, including both large-scale wave modes and their angularity, non-sinusoidal behavior, as well as predictions of some of the smaller scale turbulence coming out of this. If we zoom forward in time to 100 to 109 rotations, we see that we're still predicting some of the large-scale waves, but the system has stopped predicting any of the smaller scale turbulence. And then as we go out many hundreds of rotations in the future, it's still mimicking the waves, but not really able to predict either the waves or the turbulence. Now, we're showing one probe gives you an idea of the performance for the first few rotations. What I've shown here then is from all 33 probes, we just took a time here, I guess it was 27 rotations out in the future, and just mapped all of the 31 probes into a color graph of the magnetic field coming out of the outer sphere in an equal area representation. So red being magnetic field radially inward, blue being magnetic field radially outward. And then below you can see the prediction from the reservoir computer. And so it's predicting something like the weather of this magnetic field as it comes out of the experiment. So we were quite buoyed by that, and just sort of finishing up, wrapping up a series of further tests on this, comparing it to autoregression predictions, and then also hybrid models between the reservoir and autoregression. And hopefully we'll have a paper out on that in the next few months. Now, based on this, Itamar Shani, one of the team members, asked me whether or not we could do experiments that would be the nonlinear system, the reservoir itself. And we set out on an exploration for what sort of nonlinear experiments we could do that could be used as a reservoir. And again, acknowledgements to Dan Gauthier, who was already working in a field programmable gate arrays. At the time, we then went forward to look at, can we use CMOS logic elements as the nonlinear elements for the reservoir? Now, a number of groups have done work using nonlinear elements, let's say from an optical system or from other electronic systems as the reservoirs. And the key realization for me was realizing that a logic gate, in this case, let's say a NOT gate, has an output voltage versus input voltage, the transfer function, that looks quite a bit like a tanh function. So tanh functions, of course, are often used as the nonlinear activation in various machine learning tools. And so we just went forward to look at, can we use logic gates themselves as the nonlinear elements to build large reservoirs of gates? Now, of course, a NOT gate's a one input device. We're going to be using 2 or 3 or 4 input devices. So the functions are higher dimensional, but they're still nonlinear. And I just want to point out that the logic gate use here, we're not using them just in the binary sense of them being on binary 1, off binary 0, but we use the voltage in the entire range to convey information inside the reservoir. So there are a few ways to go about doing this. You can just build circuits with logic gates yourself, and we've gone forward to do that. I'll mention toward the end of the talk. Or instead, you can use this technology called a field programmable gate array, where they just give you hundreds of thousands, if not now millions of logic gates that you can configure into your own designs by having these programmable interconnects. And so this is a mature technology, and these are actually surprisingly common devices. You probably inadvertently use FPGAs many days. I suspect that many of your cars have FPGAs that actually run things like the infotainment systems and control systems and otherwise. So these are off-the-shelf commercial devices produced in large numbers. Now, in going forward to do that, then we're just thinking about, well, can you make a high-speed hardware accelerator that will follow the path, something like we've seen in other hardware accelerators, math coprocessors or graphical processors, accelerate those functions? Can we do something like that for machine learning? So this is the way it looks in practice in the experiments. One obtains these FPGAs, which is here shown as the central chip. This is actually an educational unit, the pink Z1, in a development board that then we go in and we reconfigure the FPGA to be a design, a connectivity, a graph of logic gates of our choosing. So that's when then the art and the recipes come into play, because you have to think about how do you want to build the graph, what is the analogy to the largest eigenvector. The connectivity matrix matters, but now you also are forced to choose as well the gate type. So the first test Itamar did was just to set up a 501 node graph, and he made all the nodes XOR gates. And initially, we just turned on the reservoir with no input and just to observe what it would do. And what we decided quickly was that this is a reservoir that's not necessarily useful as a machine learning tool, because even without input, it just starts free running modestly high dimensional turbulence. So this is an overexcited network of the sort that you would see in the software models. If you make the largest eigenvalue much larger than 1, you end up with self-excited networks. So we needed to turn down the self-excited abilities here, and the way to do that for our designs is to realize that the XOR gates are the maximal positive sensitive gate, in the sense that if you change either input bit, the output bit always changes. So instead of all XORs, you can use OR gates that have half that sensitivity, or pass through buffers, either NOT gates or just buffer gates, which extend memory without adding any sensitivity. So you end up having graphs of large numbers of logic gates that are put together, controlling the sensitivity as well as the connectivity to make them sensitive but not overexcited. So, and actually the longer talk has a variety of other results on that, but as we vary the mean sensitivity of the graph, here shown in the bottom graph, at a mean sensitivity of below half, the network is quiescent without input. Silent here. As we go much above 0.55, we end up instantiating spiky networks. And for large average sensitivity, we just have free running turbulent networks. And again, that XOR initial model would just be a mean sensitivity of 1. So we have to just reduce the sensitivity to make a useful machine learning tool. Now, the last design feature that I want to say before going to various use cases of these field programmable gate arrays in machine learning is we've undertaken this year the use of what goes beyond reservoir computers. We're actually modifying the reservoir by looking at its performance using genetic algorithms. So in this case, it's something more like a recurrent neural network. We don't have weights that we vary, but we actually vary the gate type distribution by observing a population, let's say, of 200 randomly generated reservoirs, having some goal that we're seeking. In this case, we seek a transient length of 50 time steps. We could control the memory of the reservoir. And then just picking the best performing 5%, generating another population of 200 using a slight amount of mutation and crossbreeding, then just continuing to do that. And so we've gone forward to be able to produce tunable amounts of memory, and then we're going to look to how we can do this to also do the same for accuracy and performance. Now I'm going to show, I think, what is maybe 3 different use cases for the reservoir. One of the use cases comes directly out of the literature, the ability to clean distorted and noisy serial data. So we train the reservoir to observe distorted data, and it's labeled data in the sense we know what the clean data should look like. And then we can test on other data, and we're able to show quite good performance up to 800 million bits per second in cleaning these time series data. Of course, a reservoir is quite useful for time series data. The time domain action in the memory assists in that. We've also, though, gone and looked at inference tasks that may or may not involve any time domain data. So one of the inference tasks we did is just the standard, these baby handwritten images, MNIST. So these are small images that are labeled data where we can train a reservoir to do classification on these and then test on some fraction of the data. And we do that again on another development board here. It's a Xilinx Vertex 7 dev board. We use a 4096 node reservoir of gates, and we can achieve 94% accuracy in classifying these images, again, just by training the output vector. Here we're not doing anything with the reservoir other than randomly generating it, and are able to then classify 7.1 million frames per second per watt, and overall 20 million frames per second. So yeah, in this case, and actually in every case, one has to think carefully about how to pre-process the data to present to the reservoir. In this case, we just unwrap the images into a single vector, present them to the reservoir, and then observe the reservoir state and present that observed state to the output vector for training. Yeah, I think actually I probably should skip a couple slides here and go to another use case. So another use case that uses time domain data is a classification task, an inference task, but classifying time domain data, in this case, radio frequency signals from different transmitters. So we had a labeled data set from the Laboratory for Telecommunication Science that had 5 different transmitters. They actually were all transmitting based on just Wi-Fi transmission protocols. And 4 of them were the same make and model, but different physical transmitters. And the 5th one was just a different make and model. So, so this is how then the workflow goes for that. We have 31,000 examples of these. It's a complex input signal that we first pre-process by converting the complex signal into a phase time series. And then we do a forward difference of the phase and present then that forward difference phases into the FPGA. We then observe the state of the network during the entire presented time series, and we calculate an output vector that then does inference to get a classification using one-hot encoding for all that. And the results look like this. So here's a confusion matrix of the 5 different transmitters. The actual transmitters were labeled 0 through 3 and A, and then they classified either 0 through 3 or A. I want to note that 0, 1, 2, and 3 are, again, the same make and model, but just physically different transmitters. Overall classification rate is 83%, which is not excellent, but we're actually have one transmitter, number 2, that apparently likes to mimic itself as number 0. So we have a tough to classify outlier here. Many of the others classify at a much higher rate than that. So I see I'm probably getting short on time. Oh yeah, and actually this just shows as the number of training samples increases, then after maybe 3,000 or 4,000, our performance tends to plateau. Again, training on some number of samples and then testing on the remaining. So here's where we're at with regard to the different experimental work that we're doing on this. Everything I've shown you with regard to the reservoir computing hardware was all done in field programmable gate arrays. commercially available development boards, and just a Python library that we put together for communicating, getting the data into the FPGA, observing the FPGA state, computing an output vector that's also put into the FPGA in order to get the results in testing back out of the FPGA. We're going forward with another path. The FPGAs have some limitations that we'd like to overcome. In particular, while the reservoir itself in the FPGA is an analog unclocked reservoir of nonlinear system of sort, the input data is strictly binary on the way in, and the output state is strictly binary on the way out. So we're going to look to overcome that, and experiments we're going to do on chips that we have designed, I should say Heidi Komkoff has designed and have been built. So we have 7 different integrated circuits that we have designed and built. They're currently at NIST waiting to be cut up. Here's an image of one of the designs of one of those. It's not a large reservoir in this case, it's only 64 nodes, but we do have the ability to actually select the node type in this case. So there's a 64-bit control word that we can present to these designs. So there's overall 2 to the 64 different designs that are capable to be instantiated in that. And we'll be looking then to do testing on time domain data in those. So yeah, so I showed you then FPGA work that continues to speed up as the generations get smaller scale and faster. The ASICs have been fabricated and are pending testing. So in conclusion, reservoir computers show surprising capabilities for time domain signals, but also can show both inference and prediction in FPGAs. And we're able to put 500 to 4,000 nodes of gates as reservoirs into FPGAs. The first reference here is to the theory group's work that JD will possibly touch on in his talk on Thursday. And then the experimental work that I've shown you are these last 2 references, one in the journal Chaos and the last archive preprint from late last year. So thank you.
Yeah, all right, thank you very much. Thank you.
Okay, I'm Tom Carroll. I guess one thing about this meeting is I can't complain about the coffee at the conference, except there aren't any donuts, so use better donuts. So I'm going to talk about some network statistics for reservoir computers. And the idea is that normally to optimize the performance of reservoir computer, you have to run the whole reservoir computer. That's computationally very intense. So using these statistics, we should be able to at least improve the reservoir computer based just on the network without having to run the whole computer. So, well, we all know how to build a reservoir computer, so I'll skip through this. The only thing I should mention is that we have our network, our adjacency matrix for a network, and some nonlinearity for the node. Okay, I guess you can see me now. That the relation between this adjacency matrix and the nonlinearity is important. We don't want the network to oscillate. It should be at a fixed point. However, with that consideration, there can be pretty much anything for this nonlinearity, which is why people like Dan Lathrop or Dan Gauthier are able to build these things with analog circuits. We also have an input signal we couple in, and this is just a random input vector. We don't want to make this signal coupling too big because it could drive our network instability. So the network will work differently depending on how we do our input signal. So I think we're familiar with how we set up our reservoir computer. We have a fixed network. We do a least squares fit to a training signal and save those coefficients. So then we do our testing stage. We just take those coefficients, drive the network with a new input signal, and use that to fit a new output signal. And we then can take the error between our new output and the target testing signal. So The error I'm going to define here then is just the reservoir output, so the linear combination of reservoir signals minus the actual target testing signal, and then I take the standard deviation of that difference normalized by the standard deviation of that target signal. So that's my testing error that I'm going to define here. So, well, why do reservoir computers work? Well, there have been a lot of talks trying to figure that out. It's not easy. Obviously, people have figured out generalized synchronization is necessary. Otherwise, we know the signals in the reservoir should be fairly diverse. There is some theory, but there's still a lot of optimization, trial and error to get parameters. And optimizing these parameters requires simulating the full reservoir computer, which is pretty computationally intensive. So what can we learn without simulating the full reservoir computer? So I'm going to start with a leaky hyperbolic tangent node, which is common in the literature. I'm also going to use nodes based on a polynomial differential equation. I like this node because we can really define a lot of different nonlinearities by changing these three constants. So it's a fairly general sort of node. I'm going to stick with these particular constants for these simulations. And my driving signal is going to be the Lorentz chaotic system. The input signal is the X signal, and my training signal is going to be the Z signal. So the first consideration is, what is the symmetry of the network? So I'm going to start with a random adjacency matrix where all the entries are 1 or 0. I use this form because it's very easy to characterize. I'm then going to randomly flip a certain number of edges to -1. So I'm going to say the fraction of edges flipped is epsilon sub f. If I don't flip too many edges, I can then count how many ways can I permute those nodes without changing the network. That's called symmetry. An example here with 4 nodes is I have 3 different ways I can arrange those nodes and get the same physical situation. So the number of symmetries I have is going to be zeta xi sub s. I'm not great with the Greek alphabet. So I'm going to start with 100 nodes and flip a certain number of edges and other parameters there. You can also read more about this in my longer talk or in some papers. So here is a log of the number of symmetries. I'm going from 1 symmetry, the identity, up to 10 to the 50th possible symmetries. Here is a log of the training error. As I increase the number of symmetries, the training error gets worse. Here are the leaky hyperbolic tangent nodes. I see the same thing. More symmetries means a larger training error. So more symmetry equals worse performance. In hindsight, you kind of say, okay, this makes sense. If I have a highly symmetric network, I have signals that might be even identical to each other in the network. So it's not going to be a good reservoir computer. But it's nice to actually see that shown. If I flip more than 100 edges, then I get to the point where there's only 1 symmetry in that network, the identity. So I have to characterize by the fraction of edges that I flip. So here is a fraction of edges that I flip, going from flipping no edges, so everything, all the edges are +1, to flipping half the edges. If I kept going, I would just see this pattern reflected about the 0.5 point in the axis. So I do see, as I flip more edges, the training error, the testing error goes down for both the linear, for polynomial and leaky hyperbolic tangent nodes. There is some saturation here, which I'll mention in a bit. The other interesting case, I can simulate linear nodes. They're the same as our polynomial nodes, but I set the nonlinear terms to 0, and I don't see any improvement in testing error as I increase the number of edges flipped. So larger fraction of edges flipped also gives me better performance. I do it this way because this is simple, but it's a very easy way to characterize the adjacency matrix. It's kind of hard to come up with good characterizations otherwise. So why do I get better performance? Well, let me put the reservoir time series signals into a matrix, call it omega. So I have m nodes, I have n time series points. I want to know how many orthogonal directions are there in this matrix omega. So using principal component analysis, I'm going to find a covariance matrix for omega. Omega transpose times omega. The eigenvectors of this matrix theta are the orthogonal directions. So I want to know what is the rank of this covariance matrix. And that statistic I'm going to use is actually very similar to a statistic that Dombre and all came up with, computational capacity. Not exactly the same, but it has some similarities. So looking at the Lorentz system again, here's fraction of edges flipped. This is the rank of that covariance matrix on the y-axis. And I see as I flip more edges for the nonlinear types of nodes, the covariance rank goes up. I do see the covariance rank saturates for the leaky hyperbolic tangent nodes. The rank saturates at 100. I have 100 nodes. The rank can't get any higher. For the polynomial nodes, the rank also saturates at about 50. For the linear nodes, I really don't see much increase in rank. So more edges flipped gives me a higher rank, which gives me a lower training error, so better performance. So going beyond symmetry, I can look at the strength of interactions between nodes. So I can find a general distance measure between the nodes. I want to know first, how many intermediate steps are there between nodes? Classically, this would be known as the path distance between nodes, and there are well-known algorithms for calculating that in the network. But I want to know more. I want to know how strong are those intermediate connections. So I define a weighted distance statistic. If two nodes are connected to each other, I say the distance between them is going to be 1 over the sum of the absolute values of the adjacency matrix elements connecting those nodes. Now I find this distance statistic can vary by quite a bit, and I want to be able to come up with histograms of that statistic. So I'm going to take a natural log to compress that scale. This means this isn't a true distance, it's a measured distance, but it's not a real metric anymore. So then I want to find a weighted path length between nodes I and j that may not be connected to each other, which I'm going to call L sub p. I find those by using a breadth first search, which is a common way to find path lengths in networks, using this for the distance between each pair of connected nodes. So the statistic can be computed without simulating the reservoir computer. So this is much less computation. So I look at 4 different network types, and I'm not going to go through these carefully. Use a fixed spectral radius, use my polynomial ODE nodes, and use a Lorentz signal. So here's my mean weighted path length, my new statistic. This is a covariance rank of the reservoir computers. And I see as my mean weighted path length is smaller, the covariance rank for 4 different types of networks is bigger, which means they should give a better performance. If I look at the testing error for the 4 different types of networks, as this weighted path length gets smaller, the testing error decreases. Some networks, the testing error decreases by a lot, some not so much, but there is a trend towards decreasing. So having a smaller mean weighted path length means a stronger interaction between nodes. It's a little counterintuitive. We might think, well, if nodes interact more strongly, then they should be more similar to each other. But this says, no, when you get a strong interaction, it gives me a higher covariance rank and a lower testing error. So I can look at some totally different types of nodes. These are some low connectivity networks from work from Dan Gauthier's group. They use a different kind of node equation. It's essentially a continuous version of the leaky hyperbolic tangent system. So in that case, for their 4 types of networks, here's the mean weighted path length and the rank. As a mean weighted path length gets smaller, the rank does get bigger, definitely gets bigger. But as the mean weighted path length gets smaller, as it goes down to 0, and remember there's a log here, so this isn't a true path length, I see the testing error gets smaller as that path length gets below 0, the testing error actually goes up. So the statistic works until the interactions between nodes get too strong. And if the nodes are too strong, then we get more error, although the covariance rank is still going up, which should be good. It suggests that there is some type of dynamical change around this point in the path length. And the longer talk, I do mention a dimension measure that also changes around here, which suggests there's a dynamical change going on. So optimizing the parameters of the Reservoir computer is computationally intensive. I can use some properties of the adjacency matrix to narrow down the parameter range that I need to search to get a good Reservoir computer. Obviously, high symmetry isn't good. This weighted path length tells me that smaller is better to a point. It can get too small. So the smaller path length leads to stronger interactions between nodes. I have seen in a longer talk that this smaller path length, the stronger interaction, can change the embedding dimension in the reservoir, which gives me larger training error. And this is just a bibliography. These papers are also repeated in a longer talk. Thank you.
Yeah, thank you very much. So now it's Erik. You can talk now. Yeah, thank you. So just for questions, we'll have questions after Erik Bolt's talk. Yeah, thank you.
Hello. Hello all. So, welcome to Potsdam, New York. I'm going to talk about, well, here's my title, on explaining surprising success of reservoir computing forecasting of chaos, and about the universal machine learning dynamical system. And I'm going to relate it to something more classical called a VAR, a vector autoregressive model. And also there's a relationship to something that's very much trending, which is DMD, which is a Koopman analysis as a linear system. So I have a paper that's up on the archive with the exact same title as this talk. And here's our little town. Hold on. Okay. So this is just a graphic time series from a nonlinear process. We typically think of it as an embedding. This particular process is from the Lesotho-Mackey equations, although this talk isn't as much about examples as it's about a connection. I think there's lots of wonderful examples today of what one does with reservoir computing. I want to think of samples from the time series as samples from a stochastic process in a dx dimensional space. So you think of an input layer, and you have a read-in matrix, which reads in U values, and then you have a inner variable R. This is written in the form of a leaky reservoir, and then eventually you have a read-out matrix W out, and you read out the values Y. And that would be in training mode, and Y's are supposed to be like X's, so then eventually you can connect it back into itself and iterate, if you like, after the training phase. The weird thing is, I've always found it very weird, is that you pick this W in and the A randomly. Although we've seen some talks, particularly Tom just gave a talk in doing a good job at choosing your A randomly. There's some structure in there. But I'm mostly going to ignore that and say, how could this work at all if we're picking these things randomly for only training the out matrix? So again, a time series, a zoom of the time series, and those inner variables R, there's lots of them. So typically there may be hundreds or thousands of these. And if I show you that, it looks like a complete screen. So it's just a subsample of some of those R's in time relative to a particular subsample of a long time series. So my perspective in this talk is, instead of trying to make a better method or make a practical method that I've seen a lot of literature in some of the talks just now to improve the method, I'm going to let myself make the method worse. So I'm going to monkey around with the Q. So Q is typically chosen as some sort of sigmoidal shaped function like a hyperbolic tangent. I'm going to make Q just be the identity function and see in what sense the method still works perhaps poorly, but it still works to some degree, but now I can analyze it, and that's the point. So we've seen about picking A well, controlling sparsity, controlling spectral radius, and a better distribution of those guys. The fitting method, picking a Q well, and all this, but I'm going to just simply study with Q is equal to identity function because now I can do a bit of analysis. I'm going to relate it to a classical theory of vector autoregressive models, and then also related to VMA, a vector moving average model. And there's a theorem in this theory called the Wold theorem about representation. So continuing with what one does, once you have those inner variables, R's, after the read in, then you compare it to the data you want it to be fitting, and you do a regression step on the read out. So a least squares in, well, this ends up being a matrix, so it's a least squares in Frobenius norm is typically what you do to fit the read out matrix, although a lot of people realize you get a bit nicer fit if you don't overfit with too many parameters. And one way of not overfitting is a regularized version of the least squares step. So this is ridge regression. So this would be the pseudo inverse in ridge regression. I'm trying to get this out of the way. Oh, I can't get the screen out of the way. I have to do it from memory. In any case, the singular values of this matrix should be over here. They are a scaled version of the original singular values. Okay, on to the main point. Hold on, I'm having a problem. Okay, so I'm going to say I'm going to pick this. So there's one weak justification of why this is relevant is we know that Q has a series that begins in leading order with the identity and then corrections that are high order, and you have the power in that read-in matrix to pick a scale of it. So if we scale this rather small, it'll make the inner variables rather small, at least for a while. So I can, that's a bit of arbitrariness that I have to keep those variables small, at least for a while. Anyways, I'm just going to pick an identity function. So picking R, the inner variable initially as 0, and with Q is identity, you can just follow through as an iteration of what the R variables would be. So on first read in, you read in the X variable, and that becomes the R2. At next read in, I read in the X2, compare also to iterating A on the R we just read in, like this. And then I just keep going in this manner, R3, R4, and so forth. And you see I get a series in a matrix series or a vector matrix series in the read in variables. So it's all deterministic when written in this manner. So when I inspect this series I get out for the kth iteration, I can write it in this way. And then this starts looking like something familiar. So if I read out the W out to each of them, it passes through the sum, and I have this expression. And then I have lots of matrices of this form, which is W out A to the K minus 1 W in hitting the X1, and then minus 2 hitting the X2, and so forth. And if I track the size of these things, so this object, these AJs, these are matrices. And then if I write those just as matrices, like this, then I recognize that. So a comment that Dan just made is he compared to an autoregressive process. This is a version, which is a vector autoregressive process. This is exactly the vector autoregressive form, which typically would also have an offset and a noise term as we go. but we're essentially fitting these A's. So this kind of starts getting into this mystery I had, which is how can a random A and a random Wn allow us enough freedom fitting just the W out to try to fit to data? And a bit of the answer is we have a bunch of these fits, and I can just stack the whole problem like this now. So I'm trying to fit these A's, but I'm only going to let you touch is the W outs, right? So this is a stacking of all these variables. And there we are. So now the fitting step with the A's written in this way, this A scripty guy, which has built into it these A's from the autoregressive process, but this is what it looks more like when you're doing reservoir, the linear reservoir. The fit can be written either by looking at this equation. So here's a regularized fit on the least squares for A, so regularized least squares. So it looks like this expression. I'm going to take this guy and define it to be a pseudo-inverse on this big X matrix, but a regularized pseudo-inverse. Or I can think about fitting this version of the equation, which the fitted out matrix is, again, the regularized pseudo-inverse on that is this expression. And this relates the A's in the vector autoregressive process to the X and the A from this expression. And so this equation here, when you stare at it, is actually a punchline. It describes the readout matrix in two ways relative to the A's from a vector autoregressive process and relative to what you would think of in terms of an RC computer. So once you realize there's a connection to the var K as I wrote it, then you start thinking, well, what does the theory have to say from time series analysis about representability? When would you be able to do it? What kind of stochastic processes will let you do it? And the Wald theorem is the answer to that. If you have a white noise unbiased process, then you can write expressions like this, which hides in a CL. CL is a delay operator. So these would be matrices times delays in the L's. And I kind of give examples in my paper of how to write that, but this is classical theory. And it says that a process, that white noise and unbiased, can be written in this way. And so this would be an infinite VMA, meaning vector moving average, which says it is a series in the noise part. Now, if this expression CL is invertible, then I can transform a VMA into a VAR, a vector autoregressive process, which is based on futures on the measured variable instead of pasts on the noise term. So this is a statement of that, and actually in this form I go further and I write the VAR as a VARK as a VAR1, where you stack the variables, you stack the noise, you stack that displacement, and then you get an A matrix. And the future in X's is based on the past in X's, and this is kind of a delay vector on those guys. So the X's here, and then the X's future can be written in this form. And there's two useful things about seeing it this way. Is one is, now just thinking in terms of iteration, I can push that all the way to the past. And so you get these series in A's. And then you think about pushing it all the way into the past. I want to invert this guy. And in doing that, I would think about, okay, what is this inverse? I get this series. It is known only to converge if the spectral radius of the A is less than 1. So this is sort of another view on the spectral radius less than 1 problem. That lets you bring the VMA over to a VAR. I just want to see one more thing about that. So actually, I'm not going to say one more thing about that. So I just showed you an expression like this for the transformation. on the 2 slides back, this expression, but now let me think about stacking these guys. So I stack the x's. I'm now going to stack a bunch of these expressions in y's. Remember, y's are the training outputs, but eventually I'm going to connect the training inputs to the training outputs and run it in autonomous mode. So if I take this equation and I stack it in y's, just like I stacked it in x's, these also being essentially x's. So this expression, I get this thing. And I look at this thing, and it also looks very familiar. So it's basically saying the outputs in X look like a matrix or a linear system on inputs in X, which is kind of a crazy thing to do because I'm just basically saying this expression, but this is the delay version of what's now running around as DMD. Dynamic mode decomposition is a linear representation of a dynamical system. So that whole story in Koopman analysis relates observables, a dynamics on observations of functions, which can be shown to be a linear process, like formally. So that little bit of it is dates back to Lasotomachi's book. I had a book in 2013, mostly about Frobenius Perron operator, which is actually the adjoint operator of the Koopman operator. And then fitting this is a numerical implementation of the Koopman operator. So, and I've been a player in that area. So I think this is kind of neat. So this talk has mostly been about connections. If I fit this K, I can least squares the K. I get what's called exact DMD. There's a lot of variants of DMD. So this was the hyper speed version of this talk. I had the slower version as posted, and there's that paper which has lots more details that I just skimmed over. But the nature of this talk is I wasn't trying to make a better reservoir computer. What I was trying to understand is what's going on under the hood to try to solve a mystery that always that confused me, that just regressing to the output matrix can be enough. Now, just fitting to the output matrix is, I can see why it's a good idea because it's cheap, because you can do that as a least squares step. And if you have a nonlinear element in for the Q, then trying to do a best fit to the inner weights ends up being a nonlinear fit, which if we wanted to train a full RNN, it would require some kind of stochastic gradient descent, perhaps, and it's very expensive. So it clearly advantageous if you can get away with just fitting the output layer, but why is it enough? So then I realized by just choosing Q is equal to identity function, 2 things. One is, I didn't show you evidence here, but it's a bit of evidence in the talk. It still works to some degree, and work to some degree, I'm going to weaken a statement I made in my long talk. To work to some degree is it still gives you good forecasts for some period of time. But separately, there's a theory behind it because it ends up letting you relate it directly to a classical theory from time series analysis where there's a representation theorem. So in that theory, we have the Wold theorem that tells you the kinds of time series stochastic white noise unbiased processes have a Wold representation, which is a VMA representation. And then under conditions of spectral radius bounding, then that may be invertible, and in which case you can bring it all the way to a var. Although in the autoregressive literature, you typically don't bring it all the way to var, you go after parsimony, and then you do kind of a balanced version, which would be an ARMA, but the vector ARMA is the VARMA, so it's a mixed case. And also in this formulation, I'm able to relate it to another trending theory, which is the DMD Koopman analysis. So this paper and this talk has been about connections, what's going on under the hood. So I'm going to end it here, and thank you for having me.
Yeah, thanks a lot. Thank you very much. Yeah, all right then. So our next speaker is Molei Tao, who will be talking about stochasticity of deterministic gradient descent. And yes, you can start. Yeah, thank you very much.
Thank you so much for the organization and the kind invitation. My name is Molei Tao. It's really my great pleasure to be presenting my work here at this symposium. What I'm going to talk about today is It's basically what can happen to gradient descent if you use a large learning rate. And in particular, I'll show that if the objective function is actually multi-scale, and then the deterministic iterations can actually exhibit behaviors that look like stochasticity. And let me first set up my notation. So, so this is the well-known updating rule of gradient descent, and it's designed to find the local minimum of a differentiable function f. And in numerical analysis, this is actually the forward Euler discretization of the gradient flow ODE, and therefore, if we want to use a large time solution to approximate the local minimum, then we have to use capital T over h steps, where h is the learning rate, also known as the time step. So therefore, to accelerate the computation, it's commonly desired to use a large learning rate h. However, there is a caveat that is if h is too large, then the gradient descent dynamics actually no longer approximate the gradient flow dynamics. Here are a couple of examples. So, so here, if h is very small, then you have nice convergence to the local minimum, and the dynamics of x exactly resembles that of the gradient flow. But if h becomes large, even though you still have convergence, the dynamics is actually very far away from the gradient flow. And if you further crank up the time step, then you can actually get instability. But all these three are not the only situations that one can have. And in fact, if the potential well that we just saw is actually a part of a multi-scale landscape, and then you use a large time step, then this is something that you can get. So the particle's location is actually xk, where k is the number of iterations. And you can see that the particle's motion is rather irregular, and it's almost impossible to predict what would be its next move. And in fact, here I plotted the trajectory of x as a function of the number of iterations. And you can see that the orbit is actually rather stochastic. And moreover, here is a histogram of the values that this trajectory takes. And you can see that you actually have certain kind of distribution that is peaked around the global minimum of the loss function. And that's why we wondered if it's possible that this deterministic dynamics actually produce stochastic behavior, and more precisely, stochastic behavior similar to that produced by stochastic gradient descent, even though actually here we don't use any stochastic gradient. And before I explain how, let me first explain what I mean by being similar to SGD. So, so number one, if you take any ensemble of initial conditions and evolve each one of the initial conditions according to the gradient descent dynamics, and then you have an evolution of the ensemble, and you look at the distribution of this ensemble as time goes to infinity, then you actually converge to a specific statistical distribution. So here is one example. So the initial condition is really uniformly distributed, and after 1,000 iterations, you actually converge to this red distribution. And what is interesting about this is that if you change your initial distribution, you choose a different distribution, you actually converge to the same thing. The second point is that if you take just any single trajectory and you plot the histogram of its values, and then as the time window broadens to infinity, you actually converge to the same statistical distribution as before. And this also does not depend on what the initial condition is. So in fact, what I'm plotting here is are the histograms of two orbits, starting with different initial conditions, but you can see that they actually overlap very well with each other. This is just the plot of one orbit. For anyone curious, it's rather stochastic. And moreover, this limiting distribution is something that we have explicit knowledge in. It's actually Gibbs distribution, well, approximately Gibbs distribution. And all these three features are actually observed in the deterministic iteration of gradient descent. And for those familiar with SGD, of course, they are shared by SGD as well. However, they are not exactly the same. So the gradient descent dynamics is actually deterministic So if you start with the same initial condition, you always get the same orbit. So that's obviously very different from SGD. And it's my, so we do have a theory for this. And our theory basically shows that if the objective function is multi-scale and the gradient descent uses a large learning rate, and then you will have chaotic dynamics. And that's why you will actually get stochastic behaviors. So let me first specify my setup. So our theory requires that the objective function to be multi-scale in the sense that it can be decomposable into a macroscopic potential plus a microscopic potential, which depends on a small parameter epsilon. An example of a microscopic potential is really just a rescaled version of a periodic function. So if you add small periodic oscillations on top of the macroscopic potential, that you get the total landscape, which is something non-convex that looks like this. If you think that the microstructure is too regular, here is another example. So here the micro potential is actually quasi-periodic. So you have basically richer microscopic details. And our theory actually requires weaker conditions than periodicity or quasi-periodicity. The conditions are a little bit technical, but roughly speaking, if you look at the micro gradient, the micro potential gradient, it has to converge weakly to something as epsilon goes to 0. And moreover, if you look at the second order derivative, it has to be at the order of 1 over epsilon. I mean, that's natural to see if you take the second order derivative of the aforementioned two examples. And also we require some limiting expectation to exist. So, so under those weaker conditions, we can prove our theory. But before doing so, in fact, I will not prove the theory in this short talk, but you can find more details in the long talk. Rather, I want to just specify what is really going on. And in fact, let me now talk about what is a large learning rate. So, so first of all, what is a small learning rate? So eta learning rate is something that that can be actually analyzed. So for example, if it's less than much less than 1 over L, where L is the Lipschitz constant of the gradient, then you basically resolve the small scale of the potential and get convergence to the local minimum. And it's easy to see that the Lipschitz constant is actually at the order of 1 over epsilon. So that entails your requirement on eta to be much less than epsilon. On the contrary, a bad learning rate would be an eta that is too large. And if it's too large, the iteration can't even resolve the large scale. So you will have instability. But in between these two extremes, there is actually a lot of space. And this space is what I'm interested in. I call it the large learning rate regime. And in fact, this regime is split into two sub-regimes. The first one is something that I call local chaos. And then as eta further increases, you will transition into global chaos. So let me first explain what is local chaos. So this is actually a regime where your dynamics will transition into chaos while the usual root of period doubling bifurcations. So when eta is very small, the local minimum is actually the only stable structure in a neighborhood of the dynamical system. But as eta keeps on increasing, at some point, this fixed point actually loses its stability. And it's still a fixed point, but it's no longer stable. Instead, a periodic orbit of period 2 actually is born and becomes the stable structure of the system. And then as eta further increases, the period actually increases, and eventually you get an irregular attractor very quickly. So the system actually transitions into chaos. One thing to notice is that throughout this procedure, the X actually remains in a microscopic potential while created by this microscopic potential. So this is actually happening within a very small sized interval. And in fact, you can choose an appropriate interval, and then on that interval, this map will become something called unimodal map. This is basically something that generates chaos that is very well understood. So you can analyze a lot of the stuff that is going on. But I want to skip those details because I think the more interesting situation is the global chaos situation. So as eta further increases, which if you like corresponds to a fixed eta and epsilon going to 0 regime, then there are a lot of interesting results. And here is just one of them. So if your F naught, the macroscopic potential is actually strongly convex and regular enough, then the limiting distribution of the phi iterations, the gradient descent iterations, will actually be approximately nearly Gibbs distribution. Of course, if epsilon is small enough. And what I mean by nearly Gibbs distribution is that it has a density that is Gibbs distribution's density plus a small correction. And the justification of this is actually pretty non-trivial. The long talk will have more details, or you can also see our paper. But what I want to emphasize on here is the implication of this result. So if you think about it, the actual loss function is actually non-convex. It has a lot of local minima created by the micropotential. But what this Gibbs distribution depends on is actually F naught, the macroscopic part of the loss. And it gives a distribution that sort of spans the entire space as the one given in red. So, so the gradient descent being convergent to the Gibbs distribution implies that you can't be trapped in any of those local minima. There must be a way to actually escape it. And in fact, you can escape all of them so that you can actually sample Gibbs distribution. Okay, so this is a mechanism of escape from local minima, and it's actually an effect due to large learning rate. Here we don't use any noise, so this is a purely deterministic mechanism. One may say, okay, what about non-convex situations? So one clarification is that the previously considered situation is already non-convex. It's just that you know, all the local minima are created by a micropotential, and the macroscopic part is actually strongly convex. But what about a non-convex macroscopic part? Well, this is actually the interesting case. This is where things can be different from SGD. More precisely, only the shallow local minima of F naught can be escaped, but not the deep ones. Here is an example. So here is really, this is a dynamic example. F naught is just some toy double well potential. F1 is any microscopic potential. It doesn't really matter. If I choose a small value of k, where k is the scaling of the macroscopic potential, and then you can see that if I start with an initial distribution that is concentrated in the right potential well, and then after 10,000 iterations, my distribution actually becomes spread out symmetrically across the two wells. And in fact, this is approximately Gibbs distribution. However, if I crank up the value of k, and I do the same thing, so same initial distribution, and then after the evolution, my distribution is actually going to be concentrated only in the right potential well. And this is not because I didn't run for long enough. This is actually intrinsic. And the reason is because here, a large K basically gives you a higher potential barrier that cannot be crossed. So really what I meant by shallow local minima and deep minima should really be in comparison with what you have as a micro potential. So what is the intuition behind this dichotomy? Well, so if you think about the overdamped Langevin approximation of SGD, there you basically can always find a realization of a sequence of noises that point in the same direction. So basically, the sequence of noise will push you across any barrier. But in our situation, where we actually have completely deterministic dynamics, our noise is not really noise. It's actually coming from the microscopic gradient. So it's actually correlated in time, which means that it's almost impossible to have a sequence of noises that always point in the same direction. So if you want to cross a barrier, then you have to have individual noise terms to be large enough in order to cross the barrier. But in fact, the noise comes from a gradient. So and under our assumption, this gradient is actually bounded. So if the barrier is too high, then you just can't cross it forever. There is a quantitative analysis of this that sort of embody this intuition. It's only in 1D, but it's rigorous. But I'll skip the details. And instead, I want to show you one example. So this is actually a real example, not the academic examples that we previously saw. So this is actually the training of a neural network using a large learning rate gradient descent. And here you see that here is the histogram of loss values. So you see the loss actually doesn't converge to a local minimum. Instead, it actually has a statistical distribution, which, by the way, is actually multi-model because I mean the loss. It's reasonable to think that the macroscopic part of the landscape is actually non-convex. Here is a weight parameter in terms of its histogram, and also the histogram of a bias parameter. Here you actually see the multimodality very well. And the last plot is actually the orbit of this bias parameter. Clearly, it doesn't converge to a single value, but a distribution. So we actually don't know if the conditions for our theory hold in this complicated situation. But even if they don't, it seems that we still gained stochasticity. So the theory is in some sense not sharp. So do I have any theory that explains this neural network example? We have a little bit of theory, namely that we have some preliminary results, namely if the data is actually multi-scale, which is not a bad assumption because data usually corresponds to fluctuations around a mean, then the loss is also possibly multi-scale if you are in a reasonable setup. And this is actually non-trivial because the loss is actually a function of the weights. They are not the function of the data. The data is already fixed. So this is non-trivial, but it's possible. So if you're interested, we can talk more. But I think I'd rather summarize here. So so I basically showed, I believe, for the first time, that deterministic gradient descent can actually exhibit stochastic behavior if the objective function is multi-scale and also the learning rate is large. And here, a large learning rate has to be very precise. It has to be too large to resolve the micro scale, but it still has to be small enough to resolve the macro scale of the loss. And then you can have chaotic dynamics, which is the origin of this stochastic behavior. Now, if you look at only the macroscopic part of your loss of your energy landscape, and that's going to be strongly convex, then the behavior of the deterministic algorithm actually resembles that of SGD, and all the local minima can actually be escaped because they are all created by the microscopic potential. However, if the macroscopic part of the potential is already non-convex, then only the shallow macroscopic potential wells can actually be escaped, but not the deep ones. And this is where you start to see a difference from SGD. So with this, I want to thank you for listening, and I'll welcome questions, but I'll teach during the first question and answer session, so I'll be back in a second. Thank you again.
Right, okay. So I'm Yuzuru Sato, Hokkaido University. This is a recent collaboration with these people at Daijitsu and Akio Fujiwara to Osaka University, which is working on information geometry. Is one of the theory of machine learning. So I'll be talking about noise-induced degeneration in online learnings. This is outline of my talk. I will explain this gradient descent dynamics in the multi-layer perceptron and introduce this vanishing gradient and the plateau phenomena. And I moved to online learning settings, and I introduced stochastic gradient descent dynamics as random dynamical systems. And then this 2 and 2b is our result. This is a review. 2b is about noise-induced phenomena in this kind of stochastic gradient descent. And I will talk about some summary of this work. So the review part is probably many people already introduced, but right, I also revisit this multi-layer perceptron and gradient descent. Right, so we give this multi-layer perceptron. This is 3-layer perceptrons, and the hidden layer is only 1. We can have multi layers in as hidden layers. And our purpose is we have input X random variable and output Y also random variable. And we like to know the relationship between X and Y. So Y is approximated as Tx in this picture. So this multi-layer perceptron is function approximator as with input X as random variable. We change this theta W1 to Wn, W1 to Vn to fit this function approximator. To choose theta, we use this loss functions, the average of this L, but typically we use this mean square error. And minimizing this, so we have this fitting Tx as by f x theta. Right. So this is called deterministic gradient dynamic. Sorry. So minimizing the mean square error can be achieved this way. This is most primitive algorithms. It's called the deterministic gradient descent dynamics. Eta is running rate. It's time scale of dynamics. Then we have potential defined by L x theta averaged over x, and we have deterministic potentials. This is just related to the former talk. It's exactly the same schemes. Right. So this kind of settings, this is classical, most classical, typical, I think, traditional settings for the machine learnings. There are well-known problems in the learning process. The first one is vanishing gradient and plateau phenomenon. Phenomenologically, this is explained as this error or loss function will not decrease, sometimes trapped in very long time, in some distance. So we can escape after a long run, but we trap other part, and we again observe plateau in time. So this is caused by roughly gradient is vanished. So the gradient value derivation around 0. So we cannot decrease this EX in this gradient, simple gradient descent dynamics. The other problem is called overfittings. And this is explained by these figures. We give data and try to fit functions, but it's fitted, but it's overfitted. This caused by by too many degree of freedom for the systems. Theta is too high dimension, so then we can fit like in this way, but this is not what we like to obtain. Right, so there are many other, of course, it's a problem of machine learning, but we discussed this too, especially this plateau phenomenon. So there's classical studies done by Japanese statistician and machine learning theorist. We call this Fukumiza-Amari model, but it's nothing but minimal multi-layer perceptron with average running. These 2 nodes, input, output, and 2 nodes, 1 layer. This is minimal perceptron. In which sense minimal? So this is minimal perceptron which shows plateau phenomena, right? So we can write down the very concrete models in these minimal settings. And this is, I think, in our context, this is a minimal model for machine learning. The theta is W1, W2, V1, V2. So four-dimensional state space. L is given in this way, and fx theta is just this summation of tangent hyperbolic. T is already also fixed. We choose this particular T. In some of the result is more general, but our example is given by this particular target function. And then X follows these Gaussians with fluctuation sigma square. The optimal theta star given in this way, because this fx theta is Tx, becomes Tx. So even in these models, we can observe plateau phenomena. This is training error, log of training error, and this is log of this number of iterations of this Gaussian synchronics. So we have long plateau and escape, but again drop to other plateau. Right? So function is, this is a target function, right? And then this is like trapping. So the perceptron generate these simple functions and then trapped for a long time. Right, their analysis says that one of the reasons why this plateau phenomena occur is degeneration of theta. So dynamics trapped to degenerated subspace in theta, W1, W2, V1, V2. For example, this fx theta, we have W1 equal W2, V1 equal V2, or in general, in this theta, particular theta called theta d, then the f is these functions, which can never approximate these target functions. Right. So this, because this is only the variable is effectively two variables. So the degree of freedom of system decreased, and degenerate subspace is sometimes sticky. So it's very difficult to escape from this degenerated subspace. So dynamics approaching this degenerated subspace and stay there for a long time and then escape. And in some kind of limit, this degenerated subspace is so-called Milnor attractor in terms of dynamical system theory. This attractor has measure their escape hole in the own attractor. So there are some of this kind of structured Milnor attractors in the state space of theta, and then we trap there for a long time. So this is one of the dynamical systems explanations for this plateau phenomenon. There are many other reasons of this plateau phenomena or slow conversion rate for learning, but this is one mechanism of this phenomenon. Right, so we go to stochastic gradient descent dynamics. This is typically for, this is a model typically used for online learning or small batch size learnings. So in this case, this is a very extreme case. So we try to minimize the square error, including X, so no average. So one step, one shot run, so data put to the system, and we already apply this gradient descent, and the next data, and we apply. This is one typical example, but this is a model, more general model for this online learning, so batch size run. So in this case, we don't have this average for this square error. So then this potential is random variables or random potential, like this way. So every step we have random different potential, and we go to the and the dynamics follows gradients. So it's called stochastic gradients and dynamics. So we exclude this average EX. Right. So in general, in this way, online learning or similar type of learning is modeled by random dynamical systems. Because in general, dynamic and learning of learning system has two slow fast dynamics, and slow dynamics is expressed by theta, and fast dynamics is like internal state or like external force. So it's non-autonomous dynamical systems. But we assume the input, the data X input is random variable, so it's random dynamical systems now. So Fukumi's Amari model is given similar way or exactly same way, but we only apply this stochastic gradient descent, no average, and just put data X, and X follows Gaussian distribution. Then we can have this very concrete dynamical systems, actually random dynamical systems, because we include X, right? So X is random variable following Gaussian, and we have this gradient descent map composed by target function or tangent hyperbolics. It's already complicated, but anyway, we have very concrete dynamics. So we can explore these random dynamical systems and actually observe the dynamics of learning. Right, so this is simulation data, sorry. Right, this way. So we put initial condition, W1, W2, V1, V2 in 4D space, and this is projection. This is W1, W2, V1, V2, right? With different sigma. Sigma is fluctuation of data, the variance of X. And then gray point is optimal point for this target functions, right? Okay, so learning rate is not large like format talk, it's small. So we don't observe oscillation or chaotic behavior. Then we generate all possible trajectory for this running dynamics. This is actually a converging process to Pullback attractor in random dynamical systems. So with sigma square 0.1, the most dynamics quickly goes to optimal, right? But in this case, we can wait the next one. Sorry. Yes, here, this one or this one is trapped very long time and converging on this line in some initial conditions, right? So this is actually W1 equal W2 and V1 equal V2. So synchronization manifold. So in some sense, we observe noise induced synchronization. So V1, V2, W1, W2 is synchronized in this space with this noise level, completely same dynamics. So then this is the just difference of the variance of the noise. In this case, we combine. In this case, we observe this trapping to the degenerated subspace. And we observe plateau phenomena, phenomenological, like error function don't decrease, doesn't decrease. Right. So, okay, so this is other discussions, like escape from local minima in the potential by perturbations, typically based on the additive Gaussian noise, and then we have escape rate and so on. But this view doesn't work for this online learning and other finite setting machine learning. Right? So this is a numerical result of this escape time as a function of noise amplitude. Noise amplitude is small and large. If noise amplitude is small, so average escape time is large and then decreasing. This is fine. But in some noise level around 0.1, actually escape time increase because of this noise induced degeneration. Right? So the larger noise induce trapping actually based on this noise-induced phenomena. And this is expected to be observed in many other, more larger systems in online learning or similar settings, when stochasticity or this random dynamical system model is adequate. So this is a very typical behavior in terms of random dynamical systems. It's everywhere in this dynamics, even in gradient dynamics. Right. Okay, so this is our interpretation of this typical problem in machine learning studies. This vanishing gradient is synchronization, degeneration of theta. And overfitting is, in some sense, desynchronization. Its degree of freedom theta is too large. So this trappings or degeneration is not always bad to avoid overfitting. So we need some synchronization to shrink the model to have better result. So the trade-off, this synchronization, desynchronization is important to have good or better machine learning. This is just interpretation and our view in this particular model and settings. Okay, so this is the summary. Noise-induced degeneration and noise-induced plateau phenomenon exist in a particular model, this small Fukunizamari model we call. And the freezing degree of freedom generates this plateau phenomenon. And this we didn't, we cannot observe in this Fukunizamari model. Overfitting, no overfitting because it's too small dynamical systems. And basins of attraction we didn't discuss, but it's actually important to discuss plateau phenomena. And the fluctuation of data is also important because fluctuation of data is noise in this setting. Right. So, and the real machine learning is always finite time, finite space, and finite data. So this analysis is actually sometimes works for this realistic settings. Right. So this is a preprint on the archive, and it's submitted to this special issue of this conference, Machine Learning and Dynamical Systems. Okay, thank you.
Yeah, thank you very much. So now it's time for Haijun Yu. So do you want to share your screen?
Yeah, I'm here.
Okay, thank you.
Professor, I'm here. Can you see my slide?
Yes, yes. Yeah, can you move to the next slide because sometimes it blocks? Ah, yeah, it's working. Yeah, thank you.
Oh, thank you. Can I start now?
Yes, please. Thank you.
Okay, thank you. So my name is Haijun Yu. It's my great pleasure to be here to give a talk on this symposium. This work is actually recently done with Professor Wenyi and my friend Zhenyu Liao, and also with my student Xinyuan Tian. The topic of my talk is unstandard learning stable and interpretable dynamics using generalized Ansky principle. So my talk has several parts. First, I go say something about the motivation, then the Ansky principle, and then the structure of the net and the application, and then finally a summary. So first, our motivation is to find a low-dimensional model for the incompressible Navier-Stokes equation. You know, this equation actually is a very famous equation in fluid dynamics. It can model complicated fluid motion such as turbulence,
and it's hard to do analysis because it's a nonlinear, high dimension, and have no scale separation, and it's not a gradient system. That's several features that make it very hard. If we can find some low-dimensional model that's which can keep some of the intrinsic property of the high-dimensional model, then we can do analysis on this low-dimensional model. There one very famous example is that the Lorentz system, which only use 3 variables to describe the really Bernard convection phenomena, and that's the first low-dimensional model that's predict chaotic solution, and it's famous for that. However, its quantitative accuracy is very limited because Lorentz system have only 3 modes. It's highly truncated. The high frequency mode are all truncated, so it's we cannot expect it has some quantitative accuracy when the system is far from the linear region. So our goal is to learn some dynamics with following features. So first, we want to have a low-dimensional model. Second, it should be have high fidelity. Third, it's physically meaningful. It has some internal structure. The fourth part is have some theoretical guaranteeing of the long-time stability. So that's the goal in our mind. And we look at, there are a lot of existing approach for learning dynamics and also model reduction. For example, the sparse identification, the direct numerical neural network fitting, and the Gallagan closure approximation approach. So the first 3 approaches can be regarded as non-structured approach, which means they have no predefined or physical structure in the neural network. Recently, there are some structured approach. For example, you apply some gradient structure or Hamiltonian structure in the neural network, such that the learned neural network, the dynamics is guaranteed to be stable. However, in those structured approach, the hypothesis based are too specific. Those methods does not apply to the Navier-Stokes coefficient. So our approach is based on generalized Unsicker principle. Now I give some introduction to the Unsicker principle. So we start with the Unsicker principle. So Unsicker principle is very famous in stochastic physics, and it gives some structure to the dissipation system, which written as a mathematical equation 1. So here, this H usually called reaction coordinate or generalized coordinate. It's to describe the microscope phenomena of the system, and M is a matrix. Unsicker original principle or Unsicker reciprocal relation tell us that under some assumption, if the system microscopically is time inversible, or it's near equilibrium or thermodynamic equilibrium, then this M should be symmetric. Dissipation means M should be positive semi-definite. So by these 2 properties, we will have that this V, we usually call the potential or free energy or entropy, negative entropy, gonna be a non-increasing function as a function of time t. Right? So this is a very simple equation, but it have a lot of application. This is a version of the ODE system. So people have extended this to a PD system, and it has been applied a lot in mathematical modeling of complex fluid and material science. However, the Unsicker principle is only applied to this basic gradient system. So in our Navier-Stokes coefficient, it's a non-gradient. So we need to add more structure into the physical law or principle. So here we consider a generalized Onsager principle. We add a W term here, which is the anti-symmetric part, which accounting for the conservative interaction. We also add external force term G. This term accounts for external force. For this V term, in Onsager approach, if the system is close to equilibrium, this V is very close to a quadratic form. But here we only assume require that V is lower bounded, such that it makes sense to be a potential of free energy. So let's look at the structure of the generalized Onsager principle. The former equation can be written into a mathematically equivalent form. Here we assume that M plus W is invertible, so we can invert it to the right side and rewrite the equation in this form. So it's not too hard to show that this equation have a dissipation structure as equation 2. So which means that the free energy V involve according equation 2. If this F is 0, if no internal force, we have V to be dissipative. If F is non-zero, we can, under some mild condition, we can prove that the state variable H and V it's stay finite for all time T. Those are the conditions we need to make the system to be stable. So when we design the learning, we need those parameters. Okay. We can also, that's this principle, it can be called a principle. It's actually it's an invariant to coordinate chains. And this principle also applies to a wide range of systems. For example, the deterministic Langevin equation, the generalized Poisson brackets, and also the incompressible Navier-Stokes equation. So if we want to use the Onsager principle to do the machine learning, we face two challenges. The first one, that's how to find a good set of generalized coordinates. The second one is how to determine the large amount of coefficient U in M, W, and V. So traditional people do it by using mathematical analysis. If you have some ground truth microscopic model, for example, the kinetic theory, then you can derive if this system have some scale separation or near equilibrium or quasi-equilibrium, you can do some mathematical analysis to obtain a continuous equation or low-dimensional model. However, in a lot of situations, there are no scale separation such as this Navier-Stokes equation. So we do it using a data-driven approach. So we use the PCA principal component analysis and autoencoder to find the generalized coordinate, and we use the neural networks to parameterize those physical quantities in the Onsager principle, the M, W, and V, and then put them together and to feed the data. And we call the overall networks to implement the Onsager principle. We call it the Onsager net. So now we can see the structure of the Onsager net. So its structure is so on the left side. So we're using a multi-layer perception neural network with resonant connection to form some adaptive bases, and then use the linear combination of those bases from these physical quantities, UI, L, W, F, then use this this form to generate output as the right side of the Onsager principal equation. Here we need to use the autograd algorithm to calculate the gradient of potential. To make this potential to be lower bounded, we assume it has such form. So this B is the B in the stability requirement. If we have a non-zero F, then we need to have some positive B to make this system to be stable. And then also we need this dissipation matrix M theta to be positive definite. So this is a clever way to define a positive definite matrix. Here L is the lower triangle matrix. So to train the neural network, train the AskNet, we use such a loss function. This loss function actually, we have some trajectory data. Each sample have two snapshots at time t1 and t2, and we forward the solution from t1 to t2 by using a Ronde-Coulomb method, and then compare the prediction using the prediction error as a loss function. So if we use want to do a model reduction, for example, you have a high-dimensional data, trajectory data, but you want to learn a low-dimensional model, then you have to do a model dimension reduction. We can use PCA to dimension reduction or use the autoencoder. So the autoencoder is a nonlinear extension of the PCA. It's here. We add a regularization to the autoencoder to make the system, the autoencoder to be isometric. Try to make it isometric. So this LAE is the loss of autoencoder is the standard, and LOD is the loss of the AskNet fitting error, and here this beta is the penalty constant. Small l ISO is the isometric loss of the autoencoder. So by adding this term, this alpha is related to the PCA loss of PCA isometric loss. So we require the autoencoder behave better than PCA here. Now our goal is to apply to find the minimum model for the really Bernard convection problem. But since we don't know ground truth, we use two OD systems, which we have the ground truth to test our approach. The first benchmark problem is to learn a deterministic Lagrange equation. So it's given in this form. Here, this gamma is the resistance. It can be constant or nonlinear depending on this V. So we consider two cases. One is a Hooking model, which this gamma is a constant. Here it's very simple. Another way is a pendulum model with nonlinear resistance. Here the gamma is 3V squared. This is the benchmark compared with dissipative symplectic neural network. It's recently posted on arXiv in this year. And another, this is a simple multi-layer perception OD net, has no structure, internal structure. And then the blue bar is AskNet results. So the height of the bars stand for the accuracy. You can see AskNet performed the best, and then followed by the MLFT ODNet, then the SimODN. The reason that SimOD perform not very good is that because in their structure they assume that the dissipation part is a function of X. Instead, here we have gamma is a function of V. So that's which means we need to have a good assumption, a proper assumption of the structure to let the system behave good. Okay. Here we also test 5 C1 solution function as the activation function. That include touch, sigmoid, soft plus, req and reqr. Req is the square of ReLU, and it's a C1 function. So we recently studied that by using this function, we can recover polynomial approximation exactly. So reqr is a regularized req, because req is have quadratic growth. It's if you have a very deep layer, then it's hard to train. So by using this regularization, it has ellipses. It's global ellipses, so it can be trained more easier than req. Here we show the trajectory accuracy. You can see from this phase portrait, we can see that the solid curve are the learned curve from the initial condition, and the dot are the ground truth. So we can see they have very accurate results. The error is within 1% for as long as time to 20 seconds. We have also learned the potential. You can see that on the first line, the result for the linear Hawking model. The second line is the result for the nonlinear pendulum model. For the linear model, we have the accuracy is about 10 to -5. For the nonlinear model, we have accuracy about 10 to -3 for the learned potential. And then we apply this to the Lorentz system. We can see we can capture all the quantitative structure and also quantitative accuracy. The error is below 1 to 10 to -5 for this case. For the qualitative case, we can see that we have a very good short time accuracy. We can start from the solution at 0 = 0. We can capture the solution we're activated as long as time equal to 20, and then when the chaotic happened, we can capture a few oscillations. Then eventually we lost the trajectory, but the qualitative property is captured. Then we apply to the Reed-Bernard conversion problem. I don't have time to give the detailed explanation. I will show you the result. That's the trajectory accuracy as we using more and more node variable. We get the solution accuracy improved. Okay. Here the fixed portrait, we capture all the limited size fixed point at trajectory accuracy, and here this quantitative accuracy and also the learned potential. It's when we using more and more hidden variable, we get the potential very like the quadratic form. That's a high really number case. When R equal to 84, we can capture 4 limit cycles. That limit cycle actually is not in the data. We learn from those trajectory, then we calculate the limit cycle by analyze the learned ODE net. And for such a system, the traditional Gautier method need to use more than 100 mode to get an accurate result. Here we use only 11 mode, so we can see that's the advantage of use this approach. So summary. We have proposed a systematic method to learn stable and interpretable dynamics. Physics meaningful structure ensures stability without sacrificing accuracy. It is using very general hypothesis space. It's applicable to a wide range of problems. And we introduce isometric regularized autoencoder to find the nonlinear generalized coordinates. The end-to-end chain lead to better low-dimensional reduced order model, and the results is a learned model. It's a non-intrinsic high-fidelity model that could serve as a surrogate models for faster computation or further analysis. And it's a very general approach that there are a lot of other methods can be combined with it and with improve for plus a lot of interesting applications. But okay, our paper have been put on archive recently with same title, and I want to thank my founding agency, and also I had a lot of discussion with those professors and friends, and thank you for your attention.
Yeah, all right, thank you very much.
Thanks.
So now it's Anna Korba and Adil Salim. I'm not sure who's.
Yes,
Yeah.
I'll share my screen. Okay. So can you see my screen now?
No, we just see your video, not the screen.
Ah, okay. Okay.
Try again.
Now?
Try again. Wait. Okay, now it's okay.
Yeah, okay,
It
it's
works.
working. Yeah, thank you. Can you just like move to the next slide just in case? Ah, yeah, okay, it's working. Yeah, thank you.
Okay. Just, okay, so I'm Anna Korba, currently at CREST and SAE. So firstly, thanks to the organizers of this symposium. So today with Adil Salim, we'll present our recent works that can be grouped under the name Wasserstein gradient flows for machine learning. We are basically interested in problems that can be formulated as follows. When one wants to transport some initial probability distribution, mu0, to some target distribution denoted mu star. And I will show that this has applications in machine learning, such as sampling for Bayesian inference or optimizing some wide neural networks. And these problems generally can be written as some optimization problem over the space P, the set of probability distributions. Typically, for instance, one example is the minimization of the Kullback-Leibler divergence between some probability distribution mu and the target distribution mu star. And in this view, Wasserstein gradient flows find some continuous path on the space of probability distributions when it's equipped with the Wasserstein geometry. And to solve such optimization problems over the space, we can come with different algorithms resulting from different time-space discretization, and that's where dynamical systems appear. So I will present two of our main motivations for these works. The first one is the case of regression with infinite width neural network. More precisely, assume that you have some data x, y. So x is, for instance, 4-dimensional and y is a scalar, distributed as some distribution called data. And imagine you want to solve this problem with one hidden layer neural network. So this is represented as this image where you have the input x, and the hidden layer has capital N neurons, where each neuron is parameterized by some parameter zi. And the output of the neural network is y hat. In this case, it's the linear combination of the outputs of the capital N neurons, so it's this quantity. And one looks for the best capital N parameters of the network. But if you consider some theoretical framework where the number of neurons in the hidden layer capital N grows to infinity, then this minimization problem becomes a minimization problem over the space of probability distributions. And this linear combination of the outputs of the neuron becomes an expectation of phi z, the output of the neuron when parameterized by z, where z is distributed as some distribution mu. So this becomes an optimization problem over the set of probability distributions over the parameters of the network. And in some work that I will present later, we've shown that actually this optimization problem comes to is equivalent to minimizing some known loss in machine learning called the maximum mean discrepancy when we are in the well-specified case. So this requires that we have to assume that there exists some optimal probability distribution mu star, such that the conditional expectation of y given x is the expectation of phi z when z is distributed as mu star. So you can actually write your conditional expectation with a network with this structure. Then the previous optimization problem over P, using a bias variance decomposition, you can make the conditional expectation appear, and developing the square and switching expectations, you obtain this loss on P, which is the expectation of some kernel K under mu star and mu star, plus the expectation of this kernel K under mu and mu, minus 2 times the expectation of this kernel under mu star and mu. Where the kernel between two parameters z prime is the expectation when x is distributed as the data distribution of the output of the neuron when parameterized by z, phi z of x, transpose phi z prime of x, so when the neuron is parameterized by z prime. And actually, this is a known loss called the maximum mean discrepancy. It's a distance between mu and mu star. So this is one first example in machine learning when such a learning problem can be written as an optimization problem over the set of probability distributions. The second motivating example is the one of Bayesian statistics, where in this case, one has typically access to some data set D of data xi, yi, and you assume some underlying model parameterized by theta, generating your data, such as, for instance, P of y given x theta is a Gaussian, and you can compute the likelihood of the model. And also you choose some prior distribution P on the parameter theta. Then Bayes' rule gives you the formula for the posterior distribution P of theta given D. But the problem is that this normalization constant Z is typically intractable. So it's a difficult problem to sample from this posterior distribution. And there is a huge literature about this problem, and in particular, Markov chain Monte Carlo methods that generate some Markov chain whose stationary distribution is this posterior distribution. But there is another point of view adopted in this paper in variational inference, where one can see this sampling problem as the minimization of the Kullback-Leibler divergence over the space of probability distributions. So we will come later on why this is the Kullback-Leibler in this case, but it is a second problem in machine learning where we want to optimize some divergence between some probability distribution and the target distribution, which is here the posterior distribution of the parameters. So we'll now introduce, I'll let Adil introduce some preliminaries on gradient flows for our work.
So yes, so I will introduce the kind of dynamics we will look at and the kind of techniques that we will use. Next. Okay, so first, at the core of what we do is Euclidean gradient flows. So we should understand these dynamics well. So let's consider a function v defined on Rd, which is smooth, so differentiable with the Lipschitz gradient, for instance. The Euclidean gradient flow of v is defined as the solution to the differential equation x prime equal to minus gradient of v at x. So this gradient flow can be seen as a continuous time version of the gradient descent algorithm, because if we apply Euler discretization to the gradient flow, then we obtain xn plus 1 minus xn over gamma, where gamma is a step size, equal to minus gradient of v at xn. So this is exactly gradient descent. Yes. So why do we study gradient flows? Because the gradient flow tends to minimize v. So first explanation is that if we take x star to be a minimizer of v, and if we denote L of t, the function v of xt minus v of x star, so think of L as a Lyapunov function, then the derivative of L is non-positive. So basically, to compute the derivative of L, we apply a chain rule to obtain that this is equal to x prime times the gradient of v at x, and then we use that x prime is equal to minus the gradient of v at x, and we obtain that the derivative of L is equal to minus some square gradient. So this tells us that V of xt is non-increasing, and moreover, it tells us that it gives us a rate for the convergence to 0 of the average of the square norm of the gradient. So this converges to 0 at the rate 1 over t. So this quantity is expected to converge to 0 because the gradient flow tends to minimize v, and we have a rate. Okay, next. Okay, let's consider another Lyapunov function. So LC of t, which is the square distance between xt and x star. So if we assume that v is convex, the derivative of LC the derivative LC prime of t is equal to some inner product that can be upper bounded by basically minus the distance minus v of xt minus v of x star. So this is non-negative. This is non-positive because x star is a minimizer of v. And this tells us that the distance between xt and x star is non-increasing. And moreover, out of this, we can obtain a rate for the quantity v of xt minus v of x star, so the objective gap. And this tells us that this converges to 0 at the rate 1 over t. Next. Okay, so these two arguments are the core of what we will do in the sequel. And basically, if you want to prove, for instance, convergence rate for gradient descent in the convex case, you can basically use discrete versions of this Lyapunov function to prove the standard 1 over n convergence rate. And if your function is strongly convex, then you expect the quantities, the objective gap, the distance to the solution to converge exponentially fast to 0. And these results can be obtained also by using these Lyapunov functions. Next. Okay, so now let's move to the dual point of view of this work, where we look at probability distributions. So if we take the gradient flow x prime equal to minus gradient of v at x, and if we assume that x0 is random with probability distribution mu0, then xt will be random as well. So let's denote mu t the distribution of xt. So it turns out that mu t satisfies some PDE, some partial differential equation. And to prove that, you can just take a test function phi and compute the expectation of phi at xt. So this expectation can be, we can compute the derivative of this expectation with respect to the time with first using an integration by part or using the direct method, and equalizing the two equalities. Then we obtain that mu t must satisfy that its time derivative is equal to the divergence of the function mu t times the gradient of v. So mu t has to be, think of mu t as the density of the density of xt. Okay.
So in this case, it obeys a partial differential equation on mu t obeys a partial differential equation, and actually, this is also the case, this is a particular case of our object of interest, which is Wasserstein gradient flows. So for this, I need to rigorously introduce our setting. We will restrict to the set of probability distributions P on X, a subset of RD, where, so these probability distributions have bounded second moment. And we consider some functional curve F defined on the space P. So think of F as, for instance, a Kullback-Leibler divergence between some mu and mu star, or the MMD between mu and mu star. And then we say that a family mu indexed by some time t in 0 plus infinity, where at each time t we have some probability distribution mu t, it satisfies the Wasserstein gradient flow of curve F if it satisfies this continuity equation. So the time derivative of mu t is the divergence of mu t times this vector field that I will describe. So in this case, consider the differential of the function of f at mu. This is a function denoted by partial f of mu on partial mu from x to r, and you can take its gradient. So, and we denote this gradient of the differential, we denote it the Wasserstein 2 gradient of f, and it's a function in L2 of mu. which is the space of functions from x to x, which are squared integrable with respect to mu. So these Wasserstein gradient flows take the form of this equation. And in particular, we can write it more precisely if the functional f is a free energy. So what is a free energy? It's the sum of three terms, an internal potential U, an external potential E indexed by V, and an interaction energy W. So this is parameterized by three functions U, V, W. In this case, we can write the Wasserstein gradient flow of the free energy as the gradient of the differential of f, which is u prime of mu t plus v plus w convolved with mu t. So we recover what Adil showed in a few slides ago was a specific case where there was no internal potential u and no interaction energy. And in this case, we had only a term v. And actually, some few losses of interest in machine learning can be written as free energies. So firstly, the case of the relative entropy, so the Kullback-Leiber divergence between mu and some target distribution mu star, can be written as a free energy because if you choose u of s to be s log s and v of x to be minus log the density of mu star, then the curve f is the sum of an internal potential and an external potential. And we've seen that this free energy appears, for instance, when we want to sample from a posterior distribution mu star. Also, the maximum mid discrepancy that we've mentioned in the introduction, more precisely the squared MMD, can also be written as a free energy because if you choose for a specific kernel K, if you write the potential this way in terms of the kernel and the optimal distribution mu star, and you choose this interaction term, then the MMD can be written as a free energy, which is in this case the sum of external potential and interaction energy. And we've seen that this loss appears when optimizing wide neural networks. So these two losses that appear in machine learning are two free energies, but in the first case there is no interaction energy, while in the second case there is no internal energy.
What is the underlying structure behind these gradient flows? So these dynamics can be seen as dynamics in the metric space in the metric space P of probability measures with finite second moment, endowed with the two Wasserstein distance. So what is the two Wasserstein distance? So the square two Wasserstein distance is defined as the infimum over all couplings of mu. So I take two measures mu and u, and it's defined as the infimum over all couplings of mu and u of the integral of the square distance x minus y with respect to the coupling. So I recall that a coupling between mu and u is a probability distribution over 8x times x, such that its first marginal is mu and its second marginal is mu. Next. Okay, so the two Lyapunov arguments that I showed in the Euclidean setting can be carried into the Wasserstein space, and this is the important fact that will allow us to prove convergence rates. So first of all, the Wasserstein gradient flow tends to minimize curve f. So if we take mu star, a minimizer of curve f, we can define the Lyapunov function L of t, which is f of mu t minus f of mu star. And we can apply some chain rule in the Wasserstein space. So the derivative of L of t is equal to some inner product involving the Wasserstein gradient of f. And using the Wasserstein gradient flow, this is equal to minus the square norm of some Wasserstein gradient. So L of t is non-increasing as before. So this proves us that, f of mu t is non-increasing, and moreover, as before, we can obtain a rate of convergence to 0 of the average of these squared gradients, squared Wasserstein gradients. So this converges to 0 at the rate 1 over t. Next. as in the Euclidean setting, if some convexity is involved, so in the Wasserstein space, we need something called geodesical convexity. So if F is geodesically convex, then we can consider the Lyapunov function LC of T, which is the squared Wasserstein distance between mu T and mu star. So this plays the role of the squared norm, of the squared Euclidean norm in the Euclidean setting. So once again, we can apply some chain rule, proving that the derivative of LT with respect to the time is equal to some inner product, and that inner product can be upper bounded if F is geodesically convex by basically minus F of mu T minus F of mu star. So this proves us that the distance between mu T and mu star is non-increasing, and we can also obtain out of this a convergence rate of F of mu T minus F of mu star to 0. So basically this converges to 0 at the rate 1 over T. Next. Okay, so in optimization of our Euclidean space, it is already known how to go from the Euclidean gradient flow, the continuous time dynamics, to the discrete time setting, which is basically gradient descent. And many works did that. What we will do is we will do basically the same. We will follow the same path in the Wasserstein space. So Wasserstein gradient flows are already well defined and so on, and several algorithms used in machine learning can be seen as discretizations of the Wasserstein gradient flows. So what we will do is to carry some proof technique from the continuous time Wasserstein gradient flows into the discretized setting. And so if convexity is involved, then we shall use the Lyapunov function LC, basically. And if not, we will use just the Lyapunov function L. Next.
Okay, so in the second part of our talk, we will present two works in this line of work on Wasserstein gradient flows. And the first one is called maximum mean discrepancy gradient flow that was presented last year at NeurIPS. It's a joint work with Michael Arbel and Arthur Breton from Gatsby unit at University College London.
National Academies.
So I've mentioned that so in this work, we are focusing on the Wasserstein gradient flow of the maximum mean discrepancy that I've mentioned in the beginning, but now I will describe it more rigorously. I assume that Z is a subset of RD, and I'll consider a kernel K, a positive semi-defining kernel on Z times Z, where the kernel K between 2 points Z, Z prime is the scalar product between the embedding of Z and the embedding of Z prime, where the embedding is a function from Z to a Hilbert space H, which is called the reproducing kernel Hilbert space. So it's a Hilbert space of functions, which is equipped with an inner product indexed by H and some norm indexed by H as well, that satisfies the reproducing property that says that if you pick some function f in this RKHS and some point z in z, f of z evaluated at z is the scalar product between f and the kernel evaluated at z, which is itself a function. And we'll assume that the map that maps some probability distribution mu on z to its mean embedding, which is the integral of the kernel under mu, is injective. In this case, we can define the maximum mean discrepancy, which is a distance on a probability distributions on Z, and is defined as follows. So the MMD between two distributions mu and nu is the RKHS norm, so the H norm of F indexed by mu and nu, where F mu nu is the mean embedding of mu minus the mean embedding of mu. And I will refer to this function as the witness function. So as soon as we've assumed that this map was injective, we have separation for the MMD. And if we fix some target distribution mu star for any distribution mu in P, we can consider the functional f of mu, which is 1 over 2 the squared MMD between mu and mu star. This is, as I said on the previous slide, the squared RKHS norm of the witness function. And by using the reproducing property, we can easily write the closed form formula for this functional. And we've seen in the introduction that this appears as a loss when optimizing some large neural network. So we were interested in the minimization of this functional to have insights on gradient descent dynamics when optimizing such networks. And so in continuous time, this takes the form of a partial differential equation. So you've seen that it's the gradient flow of the functional f. And in this case, when f is the square NMD, its Wasserstein gradient can be simply written as the gradient of the witness function between ut and the optimal distribution u star, which was in the example the optimal distribution of the parameters of the network. And under Lipschitz assumption in the kernel, this gradient of the witness function is simply the integral of the gradient of the kernel under ut minus the integral of the kernel under mu star. And this equation rules the density of particles, or the parameters of the network, that follow this vector field, so the gradient of the witness function. And this is actually a Maktoum-Vlasov process because the evolution of the particles depend on their distribution ut. So to better understand the link between the MMD Wasserstein gradient flow and gradient descent on wide neural networks, we've considered the case of the student-teacher network, which also enters our framework because it satisfies the well-specified assumption. So what is this problem? It's the problem when you have some teacher network. So think of a very big one hidden layer neural network, but with many parameters, for instance, so capital M, and some student network parameterized by capital N parameters that tries to replicate the output of the teacher network. So in this case, this problem can be written as follows, where one wants to find the best capital N parameters of the student network, such that the difference between the output of the teacher network and the one of the student network is small. And if you implement gradient descent for the parameters of the student network, you will have the following update at each time t for any parameter small n. That involves the difference between the output of the network and the gradient of the output of the neuron of the student network. And using the kernel I've mentioned earlier, which is a kernel that depends on the data, so it's a kernel between two parameters, this update, the gradient descent, is exactly, exactly pushes the particle by the gradient of the witness function between mu star and ut, where mu star is a distribution of the parameters of the teacher network and ut of the student network. So it's exactly a time discretized version of the gradient flow of the MMD. So to better understand this discrete time dynamics, we firstly consider the continuous time dynamics, so the Wasserstein gradient flow of the MMD, and we wanted to understand how fast the MMD decreases along its Wasserstein gradient flow. So we quickly derived that the dissipation of the MMD along its flow is minus the L2 norm of its Wasserstein 2 gradient. And we wanted to know if the MMD satisfied Loyasevich inequality, which can be written this way, which means that the dissipation of the MMD would be smaller than some constant times the MMD squared itself. And this inequality actually is satisfied if the weighted negative Sobolev distance between ut and the optimal distribution u star is bounded at all time. And this weighted negative Sobolev distance is the dual norm of the weighted Sobolev norm. So it's the supremum over all functions g which have a weighted Sobolev norm smaller than 1 of the expectation of g under mu t and minus the expectation of g under mu star. So if this criterion is satisfied, then we have this inequality for the MMD. And applying Renoir's lemma, this immediately results in a 1/t convergence rate for the MMD. And this result is actually also true in discrete time. However, there are a few problems with this criterion of convergence. So firstly, it depends on the whole trajectory. Then it's hard to verify in general because In this paper, for instance, they mentioned that one sufficient condition is that these densities are bounded from below. But also when implementing toy examples of the MMD gradient flow, we've seen failure cases for the convergence. And one reason for that is that so I will maybe be quicker on this, but the condition for the stationary condition does not necessarily imply that we have converged to the optimal distribution mu star. So that would be the case if if the particles, if the mu t converge to some mu infinity, unless mu infinity is positive everywhere, this does not necessarily imply that mu infinity is equal to the global minimum mu star. So our idea is to evaluate the gradient of the witness function between mu t, so the current distribution of the particles, and mu star, outside of the support of mu t, so the current particles, to get a better signal. And so that's why we propose the following algorithm, which injects noise in the gradient. So at each iteration, we sample some Gaussian noise, and instead of doing gradient descent, we evaluate the gradient at some blurred position of the particles, which is quite different from adding noise outside the gradient. And we've run experiments, in particular on the teacher-student network that I've mentioned earlier, and we managed to have a much better error than classic approaches such as stochastic gradient descent, or even better results than adding the noise outside the gradient. So I refer to the longer recorded talk for more details. So yeah, I will skip because of time. I think we're a bit in a hurry, but we provided some convergence criterion for the Wasserstein gradient flow of the MMD. But one interesting question would be how to guarantee that this criterion is satisfied. And we've provided some perturbation of the dynamics that can help for training large neural networks, but we may be able to refine these guarantees for the noise injection algorithm.
Okay, thank you, Anna. So now I will introduce a joint work with Peter Richtarik, in which we looked at Langevin algorithm, which can be seen as a minimization algorithm to minimize the Kullback-Leibler divergence with respect to some target distribution, mu star. Okay, next. Okay, so we consider the problem of sampling with respect to some target distribution mu star whose density is proportional to exponential minus v, where v is a convex function. So recall that so the function f is defined as the Kullback-Leibler divergence with respect to mu star, and the Kullback-Leibler divergence with respect to mu star of mu and mu star is defined as the integral with respect to the measure mu of the logarithm of the density of mu with respect to mu star. This is in the case where mu is absolutely continuous with respect to mu star, else the Kullback-Leibler divergence is equal to plus infinity. And we noticed in the introduction that the Kullback-Leibler divergence can be written as a sum of some internal energy plus some potential energy associated to V. Okay, so let's assume that V is smooth, so differentiable with a Lipschitz gradient. Then in this case, one can apply Langevin Monte Carlo. So Langevin Monte Carlo is a sampling algorithm that constructs a sequence xn using the following rules. From xn to obtain xn plus 1, one first does a gradient descent using the gradient of V, and then one adds some Gaussian noise scaled by square root of 2 gamma. Okay, next. Okay, so in this work, we consider the case where V is non-smooth. More precisely, it's written as a sum of a smooth convex term and a non-smooth convex term. And in this talk, I will concentrate in the case where the function f, which is smooth convex, is strongly convex. Okay, so in this case, one can apply the proximal gradient Langevin algorithm. That was, yes, the proximal gradient Langevin algorithm. So it constructs a sequence of xn using the following rule. From xn, one first does a Langevin step using the function f and some Gaussian noise. And then one applies the proximity operator of G at this point. So the proximity operator of G is defined at the point X, is defined as a solution of the solution of a minimization problem depending on X. And this minimization problem is defined as 1/2 of the square distance between x and y plus g of y. So you minimize this in y and you obtain the proximity operator of g at x. So the proximity operator is an object which is often used in optimization, and this is a generalization of the projection onto a convex set, because if you take G to be the indicator function of a convex set, C, so the function equal to 0 and C and plus infinity elsewhere, then the proximity operator of G is equal to the projection onto C. So in general, we always have that the proximity operator of G at point X is an element of the domain of G. So the set of X's such that G of X is finite. So in particular, when you look at proximal gradient Langevin algorithm, you have that Xn plus 1 is an element of the domain of G. And the domain of G turns out to be the support of mu star. We will, yes, next, yes, thanks. So, yeah, so the proximal gradient Langevin algorithm was considered in the literature in some particular cases. So in the case of constraint sampling, so if G is equal to indicator of C, where C is a convex set, then mu star is a distribution which is supported by C. So the support of mu star is not equal to the whole space. And this is the thing that make the analysis difficult. So in that case, because each step involves a projection onto the convex set C. And some complexity results were proven for this projected Langevin algorithm, notably in the general convex case. So the complexity is 1/epsilon to the power 12 in order to obtain epsilon accuracy in total variation distance. Okay, so next, in the case where G is Lipschitz continuous, so it means that G is finite, is always finite and Lipschitz continuous. Then mu star is a distribution over the whole space, supported by the whole space. So no constraints here. And the complexity of the proximal gradient Langevin algorithm is 1/epsilon square in 2 Wasserstein distance. And in this work, we considered the case where G is a general convex function, so lower semi-continuous and proper. So this is the general setting where G can take infinite values. And we assume that mu star satisfies belongs to some Sobolev space. So it's locally Sobolev 1,1. And in this case, the support of mu star is not the whole space. So the support of mu star is just the domain of G, which can be a strict subset of X. And we obtain that the complexity of the proximal gradient Langevin algorithm is basically the same as in the case where G is Lipschitz continuous. So 1/epsilon to the 1/epsilon square in 2 Wasserstein distance. Next. So yeah, so I won't explain how we obtain this result because I don't have time. Yes, I don't have time. But basically, can you go back to the previous slide, please? Yes. So basically, to obtain the result 2, the Jormus and co-authors, they interpret the proximal gradient Langevin algorithm as a discretization of the gradient flow of the Kullback-Leibler divergence. And what we did to obtain this result that holds under the more general setting where mu star can have a domain, the support of mu star is not the whole space. What we did is to interpret the proximal gradient Langevin algorithm as a dynamics, as a discretized dynamics over the space of probability distributions, involving some, yes, so I repeat. So we interpret the proximal gradient Langevin algorithm as a discretized dynamic over the space of probability distribution, equivalent to the gradient flow of the KL, but another representation of these dynamics. So it involves what is called monotone operators in optimization. And yes, so we use another view of the proximal gradient algorithm involving monotone operators and so on to obtain this result. Okay, next.
Should I jump to the conclusion or?
Yes.
As you wish.
Okay, so to conclude, so before concluding, two advertisements, because we have some other works in this line of using this line of in this line of works we have other papers. So we analyzed we provided a non-asymptotic analysis of Stein variational gradient descent, which is a sampling algorithm that iteratively transports a set of particles towards a target distribution. So this using also tools from the Wasserstein gradient flow, specifically the Lyapunov function that is used in the non-convex case, and we also analyzed a minimization algorithm over the Wasserstein space that we call the Wasserstein proximal gradient algorithm that allows to minimize a function written as the sum of an external potential, a smooth external potential, and a non-smooth convex, geodesically convex function. So these are joint work with Julia Louiset, Michael Arbel, and Arthur Gretton. Next.
So to conclude, we tried to show that many problems in machine learning can be formulated as the minimization of some functional over probability distribution. So we've mentioned sampling or optimizing wide neural networks, but there are many others in generative modeling or online learning or to compute the barycenters of distributions. And what we tried to do in some these works that we presented is that we borrow many ideas from optimization that are shown to be useful in this setting. So we've mentioned perturbation of dynamics or adapted discretization of the Wasserstein gradient flow. So thank you for listening, and sorry to be a bit late.
Thank you.
I would be happy to have questions.
Yeah, thanks a lot. Yes, I will have questions in about 20 minutes after Alexis. Are you there, Alexis? Or?
Yes, I'm here.
Yeah, okay. Yeah.
So should I start now?
Yes, yes, please. Thank you.
Okay, so do you see the screen?
Yeah, we see it, but sometimes I mean we cannot move, we cannot see the next slide. I mean, can you move to the next slide just to check? Ah, yeah, okay, so it's working. Yeah, thank you.
Good. Okay. Okay, sounds good. Today I'll talk about robust and stable deep learning algorithm for forward-backward stochastic differential equation. So it sounds really complicated, but that basically means we use neural network to solve partial differential equations. So first of all, okay, I'm a PhD student in the computing department of Imperial College London. I mainly work with Dr. Panos Parpas, Nicolas Kentas, and also Professor Greg Pavliotis from the math department. And more generally speaking, I work on smoothing techniques and implicit gradient methods. I'm also doing an internship within JP Morgan AI and machine learning. So this work is a joint work with Batwan Guler and Dr. Panos Parpas. And we have also presented with this work at NeurIPS 2019 for the Robust AI in Financial Service workshop. And the paper is available on arXiv. And there is also a quite interesting poster you can see on my personal website here. So after a short introduction, I'll explain the links between partial differential equation and stochastic differential equations. And then I will explain how we use this neural network and this concept of deep backward stochastic differential equations, then move to the stability and generalization issue we had and how we managed to improve a bit. And also the work we have done to improve the computational efficiency. So first of all, partial differential equations are really everywhere, can be in quantum mechanics, classical mechanics, but also financial math. And later on this talk, I will explain an example of the Black-Scholes equation. And usually when those PDEs get very messy, there is no closed form solution. And so we have to rely on numerical techniques. But most often those numerical techniques do not scale well with the dimension. And we name this phenomena the curse of dimensionality. That means the complexity or time to solve the problem grows exponentially with respect to the dimension of the problem. And we claim using a neural network like we did, prevent from this curse of dimensionality because we don't discretize in space, we only do discretization in time. So first of all, a bit of background about stochastic processes. So stochastic processes can be defined by a stochastic differential equation with x the variable of interest, and you have like two continuous function, mu the drift and sigma the volatility, and you have this Brown motion here, which is basically the limit of a random walk when delta t tends to 0. And if you want an intuition of that, I've plotted two different paths on the right side of the slide. So you have this black path where sigma is quite high, it's equal to 1, but the drift is almost equal to 0. So you can see in mean, it's close to 0, but the signal is very noisy, as opposed to the red one, where the drift is higher, but at the same time, the volatility is very small. So you can see there's like way less noise, and you can play with those parameters to basically create some path. Obviously here the parameters on this example are constant, but you can also have functions of t and x of t. And some famous stochastic processes are this geometric Brown motion, which is often used for to model stock profits and stock prices, and also both Ornstein, Uhlenbeck, and Cox Ingersoll-Ross processes that are used mostly in finance to model interest rate. So in this slide, if we take this stochastic differential equation, we know that the evolution of the transition probabilities P is basically ruled by the Fokker-Plant equation, which is this equation. Okay, so this is in the general case where d of x equals to the mu dt plus sigma dw, so this equation. But what I want to show in this simple example is if we take, for example, d of x equals dwt, so you only keep the Brown motion term, you can simplify the above equation, and you can basically delete the drift term here, and sigma is equals to 1 in that case, okay? And you're only left with the heat equation, which is this one. Okay, and we know again the solution of the heat equation is the Gaussian distribution. But I want to show you, so this is one way of doing things, but the other way is also, what if I sample like loads of paths from my Brownian motion here, and you can see on the plot down the slide that I've sampled 100 different paths, and if you check after a certain amount of time, let's say t equals to 1, you will see the distribution of the value obtained exactly follow Gaussian distribution. So if I plot the histogram here, you would see this shape here. So it's just to show you there's like consistency in between both, and there is like links between a PD and a SD. So this is to gain some intuition. Obviously, we'll go further than that. And for example, for nonlinear PDEs, it's a bit more complicated. In that case, we only restrict the analysis to parabolic nonlinear PDEs of this form. Okay, and instead of having only one equation associated to this PDE, you have a system of forward-backward SDs. Okay, so you have the first one, which is the forward one, which drives the evolution of X with an initial condition here. And you have the second one, which drives the evolution of Y with a terminal condition here. And you can see here the drift from the above equation, the volatility here, the function phi here is here as well. And the volatility is again here, okay? And this is a well-known result. And we can show that this system is equivalent to the above PDE if we take y equals to mu of t and x, and that equals to the gradient of u with respect to x. So u is really the u is the solution of the PDE, and that's basically the function we try to find. If I can give you an example of this variable x of y, I would say in finance it's very common to deal with call option, and x in this example would be the price of the underlying asset, and y would be the price of the call option. Okay. And what is interesting here is, for example, for a call option, we know very well the terminal condition. If we have the strike price here, the price here, and the payoff on the y-axis, you would have a payoff that looks like this. So that would be basically our function g in that case, the terminal condition. But obviously, we solve this PDE to have the evolution over time between now and the time t. Okay, so the idea is, what if we train a neural network to map the function y equals to u of t and x, basically mapping the, if we take the example of the call option, mapping the price of the underlying asset with the price of the call option, okay? So this is a reasonable way of seeing the problem. And in that case, the function u would be this neural network. And what is very convenient as well is we also need to compute this variable z, which is the gradient of u with respect to x. And it will be super convenient with like the latest deep learning libraries, such as PyTorch or TensorFlow, by using automatic differentiation. The discussion is only done in time. So you have this classic Euler scheme, and there's nothing much to say except the Brown motion is sampled from this normal distribution here. And you have delta t here for the time and the Brown motion here. But otherwise, those functions are exactly the same from above this system of forward-backward SDs, okay? So the concept here is not to apply the neural network on the PDEs themselves, but rather apply it on the set of SDs. So this is the neural network for only one step. So you can see here the variable x, the variable t. So x has a dimension d, okay? And the output is yt here, and what we basically try to do is to achieve this, to parameterize with theta of t and x of t, okay? And u of theta is this neural network over here. So we started with a very simple architecture, a fit-for neural network with a limited number of hidden layers, and also, I guess, like maybe 20 neurons per layer. So it wasn't that big architecture, but it was enough for the example we were working with. And that is a very important slide. You see here the neural network, but for the n different time steps. So if we remember the Euler scheme, we have discretized in n different time steps. And what you see here is that as an input, we have this tuple of T0, X0. And with the neural network, we basically have Y of 0 as an output, and we compute Z using the automatic differentiation. And then we basically feed those two values to X1, because in the nonlinear case, X1 will depend basically on Y0 and Z0, which is not super intuitive, but you have to be careful about this. And then again, you compute Y1, Z1 using the automatic differentiation, and you feed to the next time step up to the last step, which is the N. Okay, and what is interesting here also is we use only one neural network for all the steps. So we have this set of shared parameter through time, theta. But obviously other architectures could be considered. And you could, for example, try to fit one neural network per step, but we thought it wasn't worth it. So this is how we train the neural network. This is this, you have this big loss function, but at the end of the day, it's not that difficult, because what we try to do, so we sum over n, which is the number of time step. We sum over m, which is the number of trajectories. And then we just do the difference between the prediction of the neural network, which is this guy, minus what we consider as a true value, which is this one. So this kind of true value in green is simply the Euler scheme applied on the previous prediction from the neural network. Okay, so it's not like if we applied the Euler scheme over the n different time steps. We just take the previous prediction from the neural network, and we compute the n+1 using this discretization scheme, and we compare this value with the prediction of the neural network. Okay, and the last bit of the equation over here is just the terminal condition we know for sure. So that's always a good thing to include it in the loss function. So this is the last step. So obviously you only sum over the number of trajectories in that case. Okay. So here's the results we obtain. So in this particular case, as we wanted to try the performance of our method, we used a super easy terminal condition, which is this one, which enables us also to deal with very high dimension x, but have a terminal condition which is a scalar. So we are able to plot those values easily. And the second advantage of this terminal condition is because we can basically have a closed form solution for the Black-Scholes equation. So again, that's really to assess the performance of the technique. And here you can see on the left side of the graph, you can see the exact path in black and the learn one in red. And you can see it's very close, right? So it took some time, obviously, to achieve this result. But it was done with m equals to 100, which is the number of paths, n equals to 50, which is the number of time steps, and this is a dimension of x, okay? And in that case, we took 4 hidden layers with 256 neurons. But we wanted to go a bit further, and again, we wanted to explore other architecture. So I probably won't have time to go much into details, but basically we tried to use the existing literature on neural network that is seen as a dynamical system. And for example, ResNet is a very good example of that, because with this skip connection, you can basically see the neural network as an ODE. And there is a like famous paper which is how you see like each layer as a time step in the ODE. And a more sophisticated one is the NazeNet. And it's more sophisticated because by using b equals to 0 and h equals to 1, you can basically go back to the ResNet. But what is interesting here, again, I don't want to spend too much time because I have other things to present, but for example, we can constrain the value of a to have this form such that it's symmetric definite negative. And the reason for that is, for example, you can imagine a solution which is something like this, and you don't want that value to diverge, okay? So there's like very strong links between these architectures and the dynamical system and ODs as we know. And so we tested those three architectures. Though the fully connected one is really the first one we developed the model, and then we tested ResNet and NazeNet. And what you can see here on the left side of the slide, you can see that NazeNet achieved really good result. And if I can explain a bit, this graph, it shows basically the relative error with respect to the relative distance to the initial condition. And this is interesting because in our case, usually in machine learning, you have this concept of overfitting, underfitting, etc. In our case, we don't have this except for the initial condition. That's the only thing that the neural network can overfit on. So that was good to see how we can generalize the solution by moving the initial condition and see how behave the solution, right? And in that case, NazeNet is really doing well. Also, the graph on the right-hand side is quite interesting. It's just the loss function through the number of iterations. And as you can see, again, the NazeNet has a smoother loss function. I mean, both ResNet and NazeNet, but as opposed to the fully connected one, where basically you can see like those massive bumps here that suggest maybe we're stuck into a local minima, then we escape it, and then stuck again, escape it, etc. And this phenomena is not observable for either ResNet or NazeNet. So the last thing I wanted to talk about is the work we have conducted to improve the computing speed. So the whole point of this neural network is, again, to solve a PDE. So it has to be convenient and it has to be done in a reasonable amount of time. And what we suggested is basically, if you remember this discretization here, you have H here, which is basically delta T n, okay? And we played with this number delta Tn. So we start with H0, which is, I would say, a large time step, okay? Let's say you have like a period of time and you just divide this period of time into a couple of chunks. And so you would start with the largest time steps. And then at the next level, you divide this time step by a factor m. So H1 would be H0 divided by, let's say 2, because 2 is a classic value for m. And then you would have like H2 equals to H1 divided by 2 equals to H0 divided by 4, okay? And basically by doing this, you refine the time step up to the time step you want, the time step you want at the end, okay? So in the experiment, we have done before, we chose a time step, 50 different time steps. But in that example, maybe we could start with only 2-3 time step, then refine the time step. So the procedure is quite easy. We just start with a large time step. You train the neural network until the loss function does not decrease too much. and then you refine the time step, you train again, refine, train again, up to the final discretization level you wanted. And this turns out to be a very efficient method. So as I explained just before, level 1 would be like only a few points. So 3 in that example. Level 2 would be a bit more refined. So you would have like 5 different points, and then 7, and then etc. up to the desired level of discretization, which is the black line. And here on the right-hand side, you can see the time to train the neural network on our particular example of the Black-Scholes equation for the 3 different architecture. And NiceNet is obviously taking much more time than the other 2, but what you can see is that if we directly start with the desired level of discretization, it will take roughly 1 hour to train the neural network, but we could only need 6 minutes by applying these multi-level techniques I have just explained. So it's a very efficient technique, kind of a warm-up procedure when you directly go to the zone of interest for the parameters of the neural network. So to conclude this talk, I would say what we have done during this in this paper is basically review the recent proposal of using neural network to solve high-dimensional PDEs. We have better understanding of the stability, robustness, and generalization, and also using these links between architecture and dynamical system. And we also managed to improve the time computation by 1 order of magnitude using these multi-level techniques. And maybe future work could be focused on using more advanced discretization techniques, probably improve the sampling methods as well. And obviously, we only tried on a few terminal conditions and on a few equations only, but we could also try these techniques to solve more, probably more industrial problems as well. And these are a few references that have been very useful to conduct this work. There's a book from Emmanuel Gobet, a paper from Pierre-Henri Labordère, and also this paper from Massia Araisi, which is very useful for our work. So thanks a lot for having listened to this talk. And if you have any questions, I would be happy to try to answer them. Pierre-Henri Labordère, and also this paper from Massia Araisi, which is very useful for our work. So thanks a lot for having listened to this talk. And if you have any questions, I would be happy to try to answer them.
On the web page of the conference. And this is a joint work of 6 of us, Michał Misiurewicz, Georges Piliouras, who already was mentioned yesterday by Maximilian Engel, Tiparat Chotibut, Jakub Bielawski, Grzegorz Kasierowski, and myself. And what I want to tell about is, seems quite simple, because what we tried to do was to study behavior of learning algorithms in the case of very simple congestion game. The congestion game is just the game where the payoff of players, of agents, depends not only on their choice of the resource or the edge, but also on the number of players who are choosing the same resource. And now in game theory, the fundamental concept is the concept of Nash equilibrium, which is just a strategy profile where all players or agents choose a strategy that is optimal given the choices of others. But with this concept, there are some problems. For instance, in fact, we are assuming rationality of players so that each of the player will tend to maximize their payoffs. And in addition, which is more crucial, the knowledge of the equilibrium. So if they are in the equilibrium, they will not change their behavior. But here we, in fact, assume then that players know not only their payoffs, but also payoffs of every other player in the game. So, which in the case of a large number of players, usually doesn't work properly. But dynamical systems approach can solve this problem. First, we can, if we will repeat the game, we can say something about convergence to Nash equilibrium, or for instance, about asymptotic stability of this equilibrium. And then we will not have to assume even the rationality of players. In addition, even if we don't have the convergence to Nash equilibrium, we can predict what will happen in our game. So we will be able to see complex behavior, cyclical behavior, possibilities ignored by traditional game theoretic analysis. And in this talk, I will refer to very simple game, a congestion game, and special kind of this game, routing game, with which we deal every day, at least in the pre-COVID era. So let's say that in the pre-COVID era, we would go to the conference, we would say, and we can say that we are in the same hotel, and we are going to the conference, where the conference is, and let's say that we have two different roads. And each of us can choose road A or road B. And let's say that in the first day, most of us chose road A. It resulted in the congestion, in traffic jam, and in large costs measured by the time of the travel. And then road B is the better choice. The time is, the costs are smaller. We can get faster to our destination. Now, what we'll do in day 2, many of those who chose road A will decide, okay, we are changing to road B. But then we'll have the road B will be congested. Then we may continue day 3rd, day 4th, and so on and so on and so on. And we can ask whether we will get to some kind of equilibrium. So given a large number of self-interested rational users without central authority to control the traffic, can we reach an equilibrium traffic flow? And here I will try to answer this question. So I need a bit of formalization. So by X, we will denote the fraction of users choosing road A. And by N, we denote the total demand of the system. Costs are linear. Okay. And the question is how players will behave. Let's say that they are using some kind of reinforcement learning dynamics. So here follow the regularized leader. What we aim is to minimize the loss on all past rounds plus regularization term. So we have cumulative cost multiplied by the learning rate, and we are adding regularizer of x1 minus x. In the extended version of this talk, I discuss results in this general case, but here I want to concentrate on one case, a specific regularizer, R of x1 minus x, which will be the negative Shannon entropy. Then we will get a well-known algorithm called multiplicative weights update algorithm, which is connected with replicator dynamics. And for every n, the optimization problem which we have to solve is the following. Now, the question here might be, okay, does learning dynamics, like this multiplicative weights update algorithm, in congestion games converge to Nash equilibria? As I said before, the congestion game is just the game where cost of the edge of the resource depends on the number of players choosing this edge or resource. And the answer which we are giving is negative. In fact, this learning dynamics can cycle or become chaotic, never converging to natural equilibrium. In addition, because our game will be very simple, chaos is robust and emerges even for two parallel links and linear cost functions. So, because this is a kind of hardness result, if we have chaos in the simple game, in more complicated games, we should expect also such behavior. And in addition, presence of chaos can be proved not only for multiplicative weights updates, but in general for FTRLs, at least in the case where the dynamics is well defined. Now, the game, now let's formulate our game. So we consider a non-atomic congestion game with two edges, U1 and E2, and the total demand N. Non-atomic means that each agent controls infinitesimal amount of flow, so the change of her behavior will not affect payoffs of others. All agents update their probability distribution x1 minus x using multiplicative weight update with fixed learning rate. Now here we are using fixed learning rate, this is important, but total flow on E1 is n times x, and on E2 is n times 1 minus x, and cost functions are linear. What happens then? Well, in this case, for multiplicative weight update, our problem has a simple solution. So the probability of choosing the first route A, will be just the probability of choosing it a day before times 1 minus epsilon to the cost of this path at the day before. And we are dividing this by a normalization factor. Now, this equation gives us a discrete dynamical system because we have just a transformation of the unit interval. So, having this solution, we can say, okay, the only thing which we have to understand is the dynamics introduced by the transformation, which depend on two parameters, A and B, where B is tells us what is the connection between, okay, how this costs of different paths are to each other. So if B is equal 1.5, then cost of both roads are exactly the same. And A depends on the epsilon, so on this learning rate, and the total demand of the system. So if we will fix learning rate, and we will and A will be changing, that means that the total demand will change. Okay, so we have this transformation, and what we can say about this transformation. We fix B because we have fixed costs of our two paths, and we are asking what will happen if A will change, because epsilon is also fixed. The question is what will happen if the demand of the system will grow. So if this demand will be small, so if A will be small, then FAB is increasing and nothing interesting happens. For A bigger than 4, we have bimodal map. And this transformation looks like on this picture. This transformation has 3 fixed points, always 0, B, and 1, where B is the Nash equilibrium. And 0 and 1 are always repelling, while B is attracting for small a and repelling otherwise. Knowing this information, we can give main results. So first, if we will consider small a, so small demand of the system. So as long as the Nash equilibrium will be attracting, so as long as a is smaller or equal than 2 over b times 1 minus b, trajectories of all points of this unit interval will converge to b. So everything will converge to Nash equilibrium and nothing interesting will happen. But what if we will take a bigger than this 2 over b times 1 minus b? Well, then we have to consider 2 cases. With the first one, when cost of both roads are the same, and the second when they are different. So if costs of both paths are the same, then for a bigger than 2 over b times 1 minus b, so a bigger than 8, we'll have a periodic attracting orbit of period 2 symmetric to 1/2, which will attract trajectories of all points from the unit interval except countably many points. We'll get to this repelling fixed point 1/2. On the other hand, if we will have asymmetric case, so cost will be different, which means here that b is different than 1/2. Then for a large enough, this transformation will have periodic orbits of all periods, will have positive topological entropy. So the growth of the distinguishable orbits will be exponential and will be Lior-chaotic. Lior-chaos here means that if we will take, there is an uncountable set of points such that if we will take any 2 points from this set and we will look at iterations of these points, then these iterations will be very close to each other, then spring aside, then close to each other, spring aside, very close, spring aside, and so on ad infinitum. This is one of weaker definitions of chaos, but this is the case here. So predictions here in the case of different cost functions, well, they are not very good. But what will happen on average? On average, it turns out that everything will get to Nash equilibrium. In fact, this Nash equilibrium B will be Cesaro attracting. And in addition, if we will take, if we will use Birkhoff-Ergodic theorem, then we can say that for every FAB invariant probability measure, the center of mass of this measure will be B. What are implications of these facts? Okay, theoretic implications. Well, to simplify the calculations, let epsilon be equal to 1 minus 1 over E, because then A is equal to N and B is equal to beta. So A is normalized system demand and B is normalized equilibrium flow. Then we can say that first, if an interior equilibrium is not 50-50% split, and increasing the total demand of the system will lead to chaotic behavior, regardless of the form of the cost function. If only these cost functions will be different, then we will have chaos for large demand. On the other hand, time average flows on the edges converge exactly to equilibrium values. And this is a property which is usually not connected with congestion. games rather to with no regret learning in zero-sum games. Can we extend these results? It turns out that we can do that. We can do that for many strategies. So if we have more than 2 routes, the same will happen. If we consider nonlinear costs, calculations are a bit more tricky, but the similar thing will happen. For heterogeneous users, we are able to experimentally detect chaos and have some kind of Chezera tracking. We can also show it for the case of 2 agent, not a continual number of players. And what is more important, we can extend it to follow the regularized leader algorithm with steep regularizers. This assumption about steep regularizer guarantees us that the dynamics which we will get makes sense. These results can be found in 3 papers. 2 of them are available online. The Road to Chaos in Routing Games, When is Price of Anarchy Too Optimistic? It is right now submitted to NeoRIPS 2020. A Family of Chaotic Maps from Game Theory. And the last one, which will be available on archive soon, with Jakub Bielawski and Grzegorz Kosiorowski, the Robust Road to Chaos for Online Learning in Congestion Games, where we are showing where we are extending our results to FTRL dynamics. Okay, so thank you very much for listening. If you have any questions, then I will gladly answer.
Yeah, thank you very much. Yeah, so we'll have the Q&A session in about 1 hour. So next speaker is Chao Ma. Are you here?
Yes, I'm here.
Yeah, okay, yes, okay, if you can share your screen.
Okay.
Yeah, thank you.
Can you see the site?
Yes, we do. Yeah. Can you just make the next slide, because sometimes they don't change. Yeah. Okay. It works well. Yeah. Thank you.
Okay. So I start now.
Yes, please. Thank you very much.
Okay. Okay. Thank you. Thank you. Hi. Today I will talk about our recent study about the qualitative behavior of adaptive gradient algorithms. This is a joint work with Lei Wu, who is a postdoc in Princeton University, and my PhD advisor, Weinan E. I guess many people are quite familiar with adaptive gradient algorithms. They are a family of optimization algorithms that uses a coordinate-wise scaling of the updated direction compared to like gradient descent or SGD, who only use one learning rate to scale the direction. So compared to SGD, they usually converges faster, especially on neural network models. So they have become default optimizers to for many tasks. However, though adaptive gradient algorithms are fast, but the loss curve behaviors of these algorithms are complicated and lacks understanding. Here, for example, I show a loss curve of an IMS-prop algorithm on multi-layer fully connecting neural network on fashion MNIST data. Both the model and the data are rather simple, but we can see that the loss curve is quite complicated with many large spikes and small oscillations. So in this work, our goal is to study with a combination of theory and numerical experiments to study the qualitative behavior of adaptive gradient algorithms. So firstly, let's introduce some preliminary knowledges, which I think it's quite well known. In this work, we focus on IMS-prop and DAM. They are 2 very very commonly used adaptive gradient algorithms. And here we list the update schemes of these algorithms. So for MS-prop, we can understand it as adding a second order momentum on the gradient descent algorithm. And here notes that the VT, the second order momentum, is a vector, and the division here is conducted element wisely. So in this way, the gradient itself is rescaled in every coordinate differently. And Adam is can be understood as the momentum version of MS-prop. And by taking, this is the discrete scheme of the algorithms. By taking the linear rate to 0, we can obtain some continuous limits of the algorithms. However, different continuous dynamics can be obtained by taking limits in different ways. For example, if we only take eta to be 0, but keep alpha and beta fixed. For example, let's take Adam as an example. Here on the left, if we do this, then the memory factor of Adam will become weaker and weaker. Then the limit is something close to the sine GD. So if we take a look at these dynamics, if epsilon is 0, then this dynamics is just the sine gradient descent, where the right-hand side is the sine of the gradient. And if we take alpha and beta to 1 at the same time when eta goes to 0, specifically let's let alpha equals to 1 minus a times eta and beta equals to 1 minus b times eta, where a, b are constant, then we get ODE system as our continuous limit, which is listed here. This system depends on a and b. So after the preliminary knowledge, our study about the qualitative behavior of these algorithms, two parts. In the first part, we focus on MS-prop, and we try to summarize typical features of the loss curve during the training process. And later, in the second part, we focus on Adam and studied the influence of hyperparameters, that is to say alpha and beta, on the behavior of loss curves. So firstly, focus on MS-prop. Here we put two figures about a typical loss curve given by the MS-prop algorithm. And the right panel is shows the last 500 iterations of the left panel. And we can summarize three typical phenomena from this loss curve. And these three phenomena actually are quite common. It's not specifically to this this special loss curve. Actually, we have observed many different cases. So the first phenomenon is the fast initial convergence. That is to say, the loss curve tends to decrease very fast at the early stage of the training. We can see here on the left panel, the loss value decreases by several order of magnitude at the first very few number of iterations, and following the fast initial convergence, we get small oscillations. These are oscillations with high frequency and small ranges. And in our understanding, these are oscillations around the minimum. So if we can see these oscillations from like 100 iterations to 500 iterations, they are high frequency, but they are small. And finally, we have large spikes. These large spikes are sudden increase of the value of the loss followed by an oscillating recovery. As we can see here, these spikes bring the loss value to be very large. And if we see these spikes from 1,900 iterations to 2,000 iterations, we can see at first the loss value suddenly increased to very large, and then it's gradually come back with an oscillation. And for these three typical phenomena, we can provide some partial explanations and understandings. For example, for fast initial convergence, we can understand it from the perspective of this sine GD. As we mentioned before, when the momentum coefficient is relatively large compared to the linear rate, then the dynamics of the adaptive gradient algorithm is close to that of the sine GD. This is confirmed by the numerical experiment showed by these figures here. Here we compare the loss curve of sine GD and RMS prop with different learning rates. And our objective function is a simple randomly generated quadratic function. And we can see that when the learning rate is the same, the curve of the sine GD and RMS prop are very similar to each other. So that means we can use the property of the sine GD algorithm to shed light on the behavior of RMS prop. And for sine GD, we can easily have the following theorem about its convergence. If our objective function is strongly convex, and then that xt be the trajectory given by the continuous time sine GD dynamics, then we have that the loss of at xt is bounded by this quadratic function. And we can easily see that this bound means that the trajectory xt can converge to the global minimum within finite time. So since it can converge in finite time, then we can say that the fast convergence happens because the convergence can always be like superlinear in some stage of the training. And this together with the numerical experiments here can partly explain the fast initial convergence. As for the small oscillations, we think that it may be able to be understood via linearization, but here doing linearization is non-trivial, because if we come back to here, the ODE continuous limit of Adam, we will see that since usually epsilon is a very small value and the stationary point, at the stationary point, both V and M are zero vectors. Hence, at the stationary point, the dynamics is nearly singular. So that makes the linearization hard to conduct, and it may not be able to explain a lot of the phenomena. But fortunately, for very simple objective functions like the quadratic function in one-dimensional space, we can explicitly write down the oscillating solution. Here we have a two-periodic solution which the iterator oscillates between minus eta/2 and eta/2, and we show that whatever the momentum coefficient alpha is, the iterator will always finally converge to this two-periodic solution. And this numerical experiments also confirms this. In this figure, different lines shows the trajectory of RMS prop with different alpha. We can see that though they run in different speed, and the line with larger alpha is slower, it converges slower, but finally they all converge to the two-periodic solution. Okay, then let's come to the second part. In this part, we focus on Adam and consider the influence of hyperparameters to the loss curve behavior. To rule out the influence of the learning rate, we, instead of considering alpha and beta, we consider A and B. Recall that alpha equals to 1 minus A eta, and beta equals to 1 minus B eta. And for different combination of A and B, we identify 3 different behavior patterns of the loss curve. The first is, we call it the spike regime, which happens when B is sufficiently larger than A. In this regime, large spikes appear in the loss curve, as we have seen several times before in the near figures. There are large spikes during the training. And these large spikes make the optimization process quite unstable, and it's kind of hard for practitioners to decide where to stop the algorithm. And another regime is called the oscillation regime, which happens when A and B have similar magnitude. So A and B are close to each other. In this regime, the loss curve exhibits fast and small oscillations. And since these oscillations are quite small, especially compared to the large spikes. So in this regime, the loss curve is smooth and it can achieve small loss, as we will see later in the numerical results. And when A is sufficiently larger than B, we are in another regime which we call the divergence regime, because in this regime, the loss curve is unstable and usually diverges after a period of training, especially when the model is complicated. So this regime should be avoided in practice, since the algorithm cannot get a small loss. And we note that the three regimes above are focus on the cases where A and B are small. And when A and B are large, we have already mentioned that in this case, Adam behaves like the sine GD. We can see it as a fourth regime, but since it is like sine GD, and in this regime, the behavior of Adam is not specific to Adam, so we just don't pay much attention to this case. Okay, so here these figures show typical loss curves of the three regimes. On the left panel, on the left column, we set A equals to 1 and B equals to 100. It is in the spikes regime. And we have to note that since we set the linear weight to be 10 to order minus 3, this case is exactly the default hyperparameter setting provided by widely used packages like PyTorch or TensorFlow. So we can see that in this case, large spikes appear in the loss curve, and the spikes can always bring the loss to be very large. And in the middle column, we set A equals to B equals to 10, and we can see that the loss curve is smoother compared to the left column, and small oscillations appear later in the later stage, but oscillation is fast and the range is much smaller than the spikes. And on the right column, we show the divergence regime. We can see that the loss curve finally diverges and goes to some very large values like 10 to order 30. So we definitely have to avoid this regime. And another natural question is to ask, how does this sorry, it seems I was muted. So a natural question is, how do these three regimes distribute in the space of A and B? Here we plot two heat maps. And on the left panel, we show we conduct many different many numerical experiments with different A and B, and we compute the average loss value on the last 1,000 iterations. And we can see that in the divergence regime, which is on the bottom right corner of this plot, the loss is always very large. And in the spike regime, which is on the upper part of this this figure, the final loss shows large variance with respect to the change of A and B. So that shows the loss curve in this regime is unstable. And in the oscillation regime, which is here, the final loss changes smoothly with respect to A and B. And in some cases, it can achieve small loss values. And on the right panel, we show a subjective classification of the loss curves into three regimes. And this classification result is approximately consistent with our description in this page. So the divergence regime happens when A is larger than B, and spike when B is larger than A, and oscillation when A and B are in the similar order. So based on the numerical experiments above, we tend to conclude that the cases where A approximately equal to B is a good combination of hyperparameters to choose if when we do hyperparameter tuning. And in this page, we conduct more practical numerical experiments to confirm our conjecture. here we use a ResNet 18 on CFAR 10 data set, and we train the model with a stochastic ADAM with a large batch size 1,000. And in this figure, the lines show the loss curves of different combination of A and B. The green light shows that when A and B are close, the algorithm gives the most smooth loss curve, and it decreases fastest. And if we note the red line, which is given by the default hyperparameter, we can see that the red line is highly unstable and it suffers severely from large spikes. Okay, as a summary, in this work, we study qualitative behavior of ADAM and IMS prop. And for the loss curve during the training process, we identify 3 typical features. That is the fast initial convergence, the small oscillation, and the large spikes. And we try to provide explanations to these features. And then we study the influence of hyperparameters to ADAM, and we summarize 3 behavior patterns. That is the spikes regime, the oscillation regime, and the divergence regime. And observations show that small and stable loss curve can be achieved in the oscillation regime where A is close to B. And here we have to note that generalization is also a very important factor to consider when we study the optimization of machine learning models. But here in this work, we do not pay much attention to generalization because we want to be more focused on the optimization itself, and the study of generalization is left for future work. Thank you.
All right, yeah, thank you very much. So now next speaker is Zhenyu Liao. Are you here?
Yep.
Yeah, okay, if you can just start sharing your screen. Yeah, thank you.
Yep, thanks. So can you see my screen?
Yes, yes.
Yes,
yeah.
okay.
Thank
Good.
you.
Yep, so I can start. Hello everyone, and my name is Zhenyu Liao, and first I would like to thank the organizer for this nice event and thank all you to still staying here. So I'm a postdoc at the University of California, Berkeley, and I'm going to talk about some dynamical aspects of learning a linear neural network with gradient descent. And this is joint work with Yassine Chedour and Romain Gouillet from University of Paris-Saclay at Paris, France. So here is going to be a quick kind of summary of the long video that is already available on the YouTube channel of Fields Institute. So if you are interested in this work, do not hesitate to go to see, have a check of the long video, and also we have our preprint archive as well. So the introduction. I'll be working trying to understand how to get a neural network. So to first introduce the model, so basically we're trying to find a function f. To try to find a function f that is parametered by some w, and we have some data x and target y, and the objective here is to minimize. So find a good function that minimizes difference of y and fx. So naive solution is, for example, the linear model, which is a linear regression. And unfortunately, it's not in general not a good model because, well, it does not work for difficult problems that we are interested in, and it only describes the linear transformation between the input data and the target. We have other more complicated stuff. For example, we have linear neural network models. That is basically given in this figure. So we have our input, and we have some weight matrices or connection matrices, W1, and then this gives our first layer. And then we continue to have another connection or weight matrices, and et cetera, et cetera. So we can have many, many layers. And if all these layers are connected only using a matrix, so this kind of give a linear transform, this gives our linear neural network model. So finally, the output of this model. F is just the product of all this with matrices, and then X. So observe that we can always rewrite a linear neural network model to an equivalent linear regression solution. Okay, but of course we have also the nonlinear version of neural network, and the main difference is that we add an entry-wise nonlinearity, so the sigma function, at every layer of the network. So basically, there are commonly used activation function sigma, such as the ReLU function, Leakey ReLU function, or sigmoid function, etc. So with this nonlinear activation function, our F function of the model becomes slightly more complicated. And here's a model of nonlinear neural network. But why we need this deep neural network? Well, basically because people play with this kind of models and find deep structures works better in practice. And here's an example of a image classification task on the popular data set of the so-called eminence data sets, which are basically handwritten digits. And we'll try to classify with a neural network model. And people observe that, well, as the network gets deeper and deeper, we get better results. So the classification error rates decrease. So basically, we would like to use deep models in practice, but it's challenging. It's challenging in the sense that it needs more computational resources, and it's really a much larger model to tune. For example, so about 30 years ago, it's just 5-layer so-called LeNets. There's approximately 60,000 parameters in this very simple 5-layer neural network. But today, or let's say 5 years ago, it's already, so with the so-called Reservoir network, it's already more than 100 layers, and the number of parameters of this given model is 60,000. It has 60 million of parameters. So it's really a huge model, and we would like to tune every parameters in an efficient way. So it's really challenging, and due to this huge number of parameters, so it is really common for people to use first-order method. For example, stochastic gradient descent or gradient descent to tune and to have all these large models. But the problem is that training this type of neural network model with a lot of layers is naturally a non-convex optimization problem. So even in the most simple setting, where we have a single hidden layer, so we have 2 weight matrices, W1 and W2, and it's a linear, and even it's a linear network. So this is still a non-convex problem in the sense that we can have many equivalent pairs, W1, W2, and they share the same loss function. So in the eye of the loss function or objective function, all this pair of solutions are equivalent. And in this non-convex scenario, when we use first-order methods, we will naturally stop at the so-called critical points where gradient is equal to 0. So here in this figure, we have 3 typical a configuration of critical points where your gradient is approximately equal to 0. So we can have local minimum and local maximum, and perhaps very unfortunately we have also saddle points where you can go up and also go down as well. So these are just a very local behavior of the loss function. And if we consider a more global point of view, we can have, in fact, different types of local minimum. For example, still measured by the loss function, we can have a very bad local minimum. So in fact, it's a local minimum because it has a lower loss value than its neighborhood, but its loss value is much higher than for example, other local minimum. We can have global minimum, basically achieving the lowest loss value for the loss function. And we can also have so-called good local minimum in the sense that, so it's not really global because it's still a kind of larger loss value compared to the global minimum, but it's pretty close to the value of global minimum. So we don't know, for example, when we use gradient descent, we do not know to which point we're going to converge to. And in this sense, it's really, so the performance of gradient descent is really sensible to initialization. For example, if we're starting the gradient descent from some point here that is close to the local, this bad local minimum, then naturally we're going to be stuck here. So we know it's very sensitive, and the initialization plays a very important role in this non-convex setting of training deep neural network with gradient descent. So can we still obtain some general theoretical result in this very kind of difficult case? And that's the main objective of this work. Okay, so some notations. So I guess I'm going to skip most technical details. So please refer to the long talk and our preprint. But the idea is, so we have this loss function, and we're going to focus on a linear deep neural network model. So we have many layers, but there is no activation function. So basically, it's still a linear transformation. And we're going to focus on so first we're going to define the state space. Basically, we're going to consider this gradient dynamic as points that are moving in the state space of all the W's, and as a function of the time. And the dynamic is given by this differential equation where basically we are moving in the opposite direction of the gradient. So it's a continuous times analysis, and we're trying to understand, even in this very naive, simple setting of linear networks, but in a deep case, where are we going to converge? And the conjecture is global convergence to global minimum. So we would like to prove that for almost every data target pair and for almost every initialization in the state space, then by following the gradient descent, we're going to converge to a global minimum of the loss function. And we haven't yet able to prove this in the general case, but there are already some very nice structures, that's what we'll say. Okay, so first, some Euro working conditions. We assume the data to be kind of full rank, and up to some SVD, we can in fact reduce the data matrix to be kind of identity matrix, and also reduce a target to be a diagonal matrix, and with some zero block. And then we can write the dynamic. So basically, this prod W will denote the product of many W's, and we can write the dynamic of the gradient descent that takes this form. So, and then we're going to define our critical points where basically the gradient equal to 0. So it's in fact this matrix equal to 0. And those are candidates to which we make convergence true. But again, we know that it can have local minimum and global and even local maximum, and fortunately a saddle points. So we'd like to say if we can converge to, for example, local minimum and avoid all those saddle points. So first is our first result is this array trajectory. So under our working assumption, array trajectory is going to converge to an element of critical point. So this is very, I mean, not really surprising, very natural. And it's only needs to notice the fact that, so this gradient system is in fact analytic. So we can apply Loya-Switch theorem that is recorded here. So which basically says that if the gradient system is analytic, and then every bounded trajectory is going to converge to critical points. So now it remains only to prove that every trajectory is bounded. And that's the magic of using gradient descent in neural network model, because there are some very crucial invariant structure when we use gradient descent in, at least here, linear neural network. So in fact, the difference of these two matrices at any time t, so this whole matrix difference is going to be conserved along the trajectory. So basically, this matrix only depends on its value at initialization. So in fact, intuitively speaking, we say that when we use gradient descent on this kind of cascade neural network model, there are very particular structures in this dynamical system. So here is only holds for linear neural networks, but a very somehow weaker but very similar relation also holds for nonlinear neural network, for example, with the ReLU activation. So in fact, there's very special property when we use gradient descent in learning neural network models. And as a consequence of this proposition of invariant structure, we know that in fact every weight matrices, so the Frobenius norm of every weight matrices is going to be directly related to the Frobenius norm of the last layer, last weight matrices, plus some constants that only depends on the initialization. So it's going to be, so this constant is going to be finite, and therefore only needs to prove the boundedness of the trajectory, only needs to prove the boundedness of the last layer, for instance, by writing the following differential equation. So, okay, so basically we notice this very nice invariant structures in the gradient descent dynamic of learning neural networks. And this allows us to prove that the trajectories are all bounded, and thus every trajectory goes to an element in the critical points. And even playing with this invariant itself, we can construct, so with already this tells us we are going to converge to critical points with some rate of convergence guarantee. And even by still playing this initialization matrix that is going to be conserved along the trajectory, we can show that by carefully choosing this initialization and assuming some very particular structure of the network, we can achieve, in fact, exponentially convergence rate. So I'm going to skip the proof here, but the key ideas is that, in fact, this things we're going to conserve this quantity by choosing it to be very specific type. We can control the behavior of our gradient descent dynamics. So this all comes from this very particular nice invariant structure in neural network structure. So, okay, we know that we're going to converge to an element in this critical points. And now it remains to understand how these critical points behave, okay? We define, so basically, again, it's kind of linear transformation, this whole matrix product. And we're going to define the rank of some of the matrix product. And then we can discuss, in fact, we can decompose this critical points according to the rank we just defined here, okay? And we will show, in fact, so according to the rank of all these matrices, we can decompose, we can discuss the quality of these critical points. So first of all, the number of critical sets of critical value is finite. And then we know that when the rank is maximum, so when the rank is maximum equal to D1, then it gives us the set of local and also global minimum. So basically we can show that for this linear neural network model, all local minima are global. And this is given in the case where the rank is maximum and correspond to the case where the loss function equal to 0. So that's good, but there are also the rank deficient case. So if the rank of these matrices are not maximum, okay, then for example, that's something smaller, strictly smaller than dy, then it's all saddle points. So in fact, we have a huge set of saddle points that correspond to the rank deficient case of this matrix product. But the good thing is that we know in some cases, if some particular condition is satisfied, then the Hessian of the corresponding critical points has at least one negative eigenvalue. So this is very crucial to help us understand, prove at least the convergence to global minimum conjecture in very simple case. So basically, by studying all these critical points, we can conclude according to the rank of this matrix product, we can conclude and discuss many property of this set of critical points. And now our conjectures, so the global convergence to global minimum now becomes to prove that in fact the union of the basins of attraction of all saddle points is of measure 0 in the state space. Things we already know there's going to be no local maximum and every local minimum is global. So it remains to in fact deal with those that converge to saddle points. And this is proved in the case of a single hidden layer. So in fact, we have two matrices. So it's still a two-weight matrices, still a non-convex problem. And in this special case, we can find we can guarantee a negative eigenvalue for the Hessian, and which allows, together with the normal hyperbolicity argument, allows us to prove that when we count the dimension of the union of basins of attractions of all saddle points, it's still of measure 0 in the state space. So I have a very nice figure to illustrate, but perhaps no time for that. But intuition is that with the idea of normal hyperbolicity allows us to, in fact, reduce some dimension counting when we try to count the union of basins of attraction for all saddle points. But unfortunately, we somehow find perhaps it only works in the case of H equal to 1. So if we really want to study the deep case, perhaps we need some stronger and more powerful tools. And okay, so here comes to our conclusion. So the takeaway message is that we have very nice invariant structures when we use gradient descent in both linear and nonlinear neural networks. And this allows us to prove convergence to critical points and also kind of get very strong exponential convergence rate to global minimum with some calculated initialization. And this tells us very particular geometry property of this gradient system when training neural network models. And in the case of linear network, we reduce the global analysis of the union of all the basin of attractions for all saddle points. And we've done this for H equal to 1, the single hidden layer network case. And this is a continuous time analysis with no particular assumption on the gradient or the norm of the Hessian, etc. And I think that's all. And here's the reference. And thank you all for your attention.
All right, thank you very much. So Soon, are you here?
Yes, I'm here.
Oh, yeah. Can you please share your screen and then start talking? Yeah.
Sure. Can you see the screen now?
Yes. Yeah, can you go to the next page just in case?
Does it work?
Yeah, it's working. Yeah, thank you. Yeah, you can go.
So today I'm going to tell you about a recent work on understanding recurrent neural networks using response theory. So I guess we have seen in earlier talks so what recurrent neural networks are. So in particular, recurrent neural networks are specially designed to handle sequential data. So basically, these data are collection of elements where the order matters. The elements are typically not, oh, I forgot to start my video. All right, sorry about this. Okay, anyway, so okay, where the order of elements matters, elements can be repeated, and the number of elements can even be infinite or vary. And obviously, there are many applications And the question is how to model and learn sequential data. So as I mentioned earlier, recurrent neural networks is specially designed to handle this. They are basically brain-inspired models in machine learning and neuroscience. And one particular useful way to think about RNNs is to think about them as open dynamical systems. So open here is in the sense that the systems are interacting with some external signal. And so today we will focus on machine learning framework using recurrent neural networks. In particular, we will consider the following supervised learning frameworks. So let's say that we have label data given as follows. And so by using RNN, which is really a non-autonomous discrete time parametric systems, we mean system of the following form. So in these equations, the variable h is a so-called hidden state, which basically encodes the historical informations of the sequential data that we feed in. And the variable y denote the output of the network. And this is something that we're interested in. So just give you some very basic example of recurrent neural networks. So there's a so-called vanilla recurrent neural networks where the activation functions A, so this is a function A here in the hidden state equation. So where A is basically just hyperbolic tangent applied component-wise. And so F, so the function F in the equation for Y is just simply linear in H. And the learnable parameters here can be W, U, B, and V. So, so just to give you a very simple idea of what RNN is, there are other types of RNNs and so on. So to do learning, we need to choose the loss functions. So typically we deal with empirical loss functions or risk. And to optimize, so to do learning, we basically want to optimize these loss functions. So to minimize this using, for example, stochastic gradient descent and back propagation through time. So this is very basic, big picture of the machine learning using RNN. So now I'm going to tell you something a little bit different. So in particular, I would like to walk you from RNNs to SDEs. So first thing is the following observations. It turns out that we can actually transform so RNN of this type. So here you see that A can be non-linear in U. So you can actually turn these equations into something that is linear in U by enlarging the state space of the system. And the second step, so this is the first step, we can do this. And then second step is usually people will add the so-called leaky integrator, or you can think of it as some sort of damping term. So where you add this alpha H here into the hidden state update equations. And usually people also add noise for various benefits and motivations. So for example, in this case, one thing is that you can think of the noise as the source coming from the data, or you can think of the noise as some sort of regularizor to stabilize the learning dynamic and so on. And also noise is, if you think about this, not from the machine learning perspective, but from the perspective of biological neural network, noise is there naturally. So this seems to be a natural update equations for the hidden state. And then if you look at this closely, you realize that this is essentially just the Euler-Marie-Rama approximation of the following stochastic differential equations. So this means that by taking the point of view of continuous time models, we can actually borrow tools from SDEs to study recurrent neural networks. So more generally, in this talk, we are going to consider the following the so-called stochastic recurrent neural networks, which essentially, again, this is a continuous time version of the RNNs, where there's a noise term here. And then, so the phi here in the equations is the so-called drift term, if you know SDE. So in this drift term, there are three distinct terms. So the first one is sort of like damping term. The second one is nonlinear activation function. And the last one is due to the sequential data, or here is just input signal. So, so this is the model that we will look at. And so we are interested in the following output functional of the SRNN. So this basically, you take the expectations of the output of the networks at some terminal time t. So imagine if you run the network many times and then you average the output and then you get this. And there are two fundamental questions that I would like to understand, at least for me, before trying to do something more complicated. So the first question is, how does this output functional respond to a driven input signal that we feed into the network over time? And second, is there a universal mechanism underlying the response? So in this talk, we will basically just try to answer these two questions using response theory originated in statistical mechanics. So this is mainly deal with the representation problem for recurrent neural networks. And we are not going to say anything about other problems like optimization, generalization, expressiveness, although this is something that we are looking at currently. And to make our life easy, let's just say that the output functional is scalar, so p equals 1. So one useful way to think about the system is to view it as a perturbation of some unperturbed system. So here is my notation. So in equation 12, so this is our original SRNN. And in 13, there's a H bar here. So this is a system without the input. So a good idea to think about this problem is to view H as a perturbation of H bar. Especially when the input signal is small, then we can do some perturbative analysis. So, so when we talk about SDEs, it's natural to talk about generators and transition operators. So here again, I'm just trying to introduce my notation. So, so again, there are two processes here, right? H and H bar. So we can associate with these processes the family of generators as follows. So here we are using Einstein summation notations. So this is, so L is a notation for generator. And then for a transition operator, the notation is that is Tx T here. And so we can also define the corresponding L2 adjoint of these operators. So for the adjoint of L, I'm going to call them A. And for the adjoint of P, I'm going to call it A P star. Okay, so this is just to introduce notation. And so because we have limited time here, so I will just give you a big picture of how we can use response theory to analyze SRNN from a physicist's point of view. So again, the key assumption here is that the input amplitude is sufficiently small so that we can do the perturbation analysis. So again, associated with the SDE, we have we can define the probability density, right, which satisfy Fokker-Planck equations as follows. And because the epsilon, so this is this guy here, the amplitude of input is small, we can see a perturbative expansion for the probability density rho. So we can write it in this expansion. And so what we do, so we just plug this expansion into the Fokker-Planck equations and then rearrange and then by matching the orders in epsilon, we get the following hierarchy of equations for the row 0, row 1, row 2, and so on. And then at least formally, like what physicists would do, you could try to solve this formally, at least write this down formally. So then we see that the higher order terms, row n, are related to the previous order term, row n minus 1, via a recursive relation like this. So we get all the formal expressions for row n, and then we sum them out, we get the perturbative expansions for the probability density row. So this is a solution to the Fokker-Planck equations. And it turns out that we can transfer all these to also the observables. So the key idea here is that so there are really two types of averages here. The first type of average is the average with respect to perturb dynamics.
We don't hear you. Are you there?
And the second one is sorry.
Yeah, we got disconnected for a few minutes, for 1 minute or so. Yeah.
Oh, okay. Can you hear me?
Yes, yes.
Okay, sorry. Okay. Anyway, so then we can also have the following perturbative expansions for the output functionals. So this is what we have here. So now we are going to look at each term here one by one. So n equal to 1, n equal to 2, and so on. So for n equal to 1, this is physicists' favorite regime, the so-called linear response. So basically, when n equal to 1, the corresponding term will be linear in the input u. And in fact, it's just a convolution term here. And with a memory kernel, okay, so I call this response kernel here, that can be expressed as averages with respect to the initial measure of a functional of only the unperturbed dynamics. So this is in fact the so-called non-equilibrium fluctuation dissipation relations in classical mechanics. And in the case of, in the special case of stationary invariant distributions, we will cover the famous fluctuation dissipation relations. So, so this is, at least this is very interesting from the perspective of classical mechanics. So usually physicists will just stop here at the linear response, and because usually this is already a good approximations when the input amplitude is small. But let's say that what happens if we go beyond the linear response regime and look at the higher order term, right, n equal to 2, 3, and so on. And in this case, so after some derivations, you can arrive at some recursive relations. And then in the end, we get these expressions in square bracket here, in the box here, sorry. So what we see is that this is a perturbative expansions, but it has some certain structure in these expressions. So namely, we see iterator integrals. So iterator integrals with some sort of a memory kernel here. So this time-dependent response kernel that I call it, defined recursively via this formula. So again, don't pay attention to these expressions here. The idea is that the structure that comes out in 36 is what matters. So it's sort of like generalized convolution integrals. So this sort of answers our questions number 1, right? So how to get representations for the output functional. And it is basically generalized convolution integrals that looks like this with some response kernels. All right. So now let's go to the second questions. So this is what I call the memory representation. So memory in the sense that we have this kernel here that depends on time. So now, so far, so this memory kernel here depends on time. So we can try to remove the time dependent here by basically do more expansions. So let's say the eigenfunction expansions of the adjoint generator corresponding to the unperturbed dynamic axis and is well defined. Then we can do expansions in eigenfunctions basis, and then also we expand the exponentials that appear after that, and then we can derive the following representations. So you see that there's also some sort of structure appearing in the equations in the box here. So again, they are basically linear combinations of some iterator integrals of some sort of like time little input, because here you have that like time to some power and then multiplied by some component of the input. And so here, Q, P, N, K, N, this is just some coefficients, constant coefficients that is independent of time and the signal. So again, we see some structure here. And in fact, we see that these expressions, this entangle the input signal. So remember, input signal is like U here, from the network architecture in a systematic order by order manner. So I guess I only have 3 minutes left, but I think I have managed to tell you the a big picture of these two representations. So the remaining work is to how to make all this rigorous, because here we basically have some infinite series and so on. And it turns out that indeed we can make this mathematically rigorous. So there are some formulations in terms of the so-called response functions that I define here. Basically, it involves some sort of functional derivative, and we need to be able to define this appropriately on some test function space. I'm not going to go over all these technical details. You can find this in my pre-recorded talk in YouTube, or you can refer to my paper. So then, okay, we can also prove some theorems after we made sense of all these stories. So I'm going to skip all this for now, and then, okay, I'm going to, since we don't have enough time, but I just want to mention that there's a connection to the representation just now to the so-called signature or path. So signature is an object in rough path theory, and I think there will be a session on how to use signature for machine learning later in this symposium, and it's an interesting object that we can link to the representation just now, but because we are out of time now, so I'll just skip all this formalism here. But the point is that we can represent the second representation, the memoryless representation, in terms of signature of some transform inputs. So I'll just leave it like this for now. And then also it turns out that we can relate this to some kernel machine. And I'm going to skip this also. There are some technical details and so on. So I will skip this. But again, you can find all the details in my paper or the YouTube talk. So to conclude, I have managed to tell you two representations of SRNN, the so-called memory and memoryless. The memory representation can be made sense as Volterra series, and the memoryless representation is the iterator integrals of some time transform signal. And I didn't tell you all this, but you can find all the details in this paper. And if you have any questions, please let me know. Thank you for listening.